Okay, let's unpack this. Imagine you're looking at a scatter plot of points, maybe from an image, maybe sensor data, and you suspect some of these points actually lie on lines. Finding those lines and grouping the points that belong to them, that's the line clustering problem.
It sounds simple, right? Just draw some lines.
If only it were that easy. It's a really common challenge in fields like computer vision, robotics, analyzing trajectories. But the moment you try to tackle it with standard data analysis tools, especially those based on graphs where you only consider pairs of points, you hit a fundamental problem.
And what's that wall you hit?
Well, think about it. Any 2 points, anywhere in the plane, define a line. Whether they came from the same underlying structure or are just random noise, you can always draw a line between them. So if your method only looks at pairwise relationships like how close 2 points are or the angle of the line connecting them, you can't actually tell if they're part of a larger collinear group. That pairwise view just doesn't capture the crucial geometric structure of points lying together on a line. Ugh, the aha moment right there. Pairwise isn't enough because any pair fits a line, so you need to look at more than just 2 points at a time.
Precisely. You need what the paper we're diving into calls higher-order interactions. Considering groups of 3 or more points at once, this is the core idea. Instead of a graph, they propose using a geometric hypergraph to model the data.
A hypergraph, that's like a supergraph, right? Where connections called hyperedges can link more than 2 vertices.
Exactly. And in this paper, they make it geometric by baking in the property of collinearity. We'll get into the specifics, but the basic idea is if a group of points is approximately collinear, you create a hyperedge connecting them in this special graph structure.
Got it. And to give this a really solid theoretical grounding, they focus on a specific, clean statistical model. Points generated by 2 latent line segments in the plane, messed up by simple additive Gaussian noise.
They call it the Gaussian line mixture model, or GLMMN for short. It's a defined environment where you can rigorously analyze performance. It lets you ask, what's fundamentally possible.
Okay, so our mission today is to take this paper, Consistent Line Clustering Using Geometric Hypergraphs, by Alaluusua, Avrachenkov, Kumar, and Leskelä Fresh Research, dated June 2, 2025, and really understand it.
Yeah, dig in.
We want to grasp the fundamental limits of line clustering in this GLMMN setting, see how they build this specific geometric hypergraph, dive into the spectral algorithm they developed to find the lines, understand the theoretical guarantees they provide, and how they handle practical challenges like unknown noise levels.
It's about extracting the key nuggets, understanding why the method works and what its limits are, not just the what, but the why and how.
Absolutely. Our source material, as mentioned, is that paper. We'll be exploring its sections, understanding the ideas, the math at a conceptual level, and the significance of the results, sentence by sentence if needed.
Sounds good. Let's start right where the paper does, page 1, with the title and authors.
Right there at the top. Consistent line clustering using geometric hypergraphs. And the authors are Alaluusua, Konstantin Avrachenkov, B.R. Vinay Kumar, and Leskelä.
And below their names, we see their affiliations. Aalto University in Finland, INRIA in France, and Eindhoven University of Technology in the Netherlands. So a collaborative effort spanning multiple European institutions.
And the date, June 2, 2025. This grounds us in the current state of research. It's pretty recent stuff we're looking at.
Definitely. Moving down to the abstract on page 1, this is like a high-level summary laying out the landscape, the bird's eye view.
First sentence. Traditional data analysis often represents data as a weighted graph with pairwise similarities, but many problems do not naturally fit this framework. This immediately confirms our starting point, the limitation of standard graph methods.
Yes, it sets the context. Graphs are powerful, sure, but not a universal hammer. They have limitations.
Sentence 2 defines the problem. In line clustering, points in a Euclidean space must be grouped so that each cluster is well approximated by a line segment. That's the goal we discussed. Clear enough.
Simple, clear objective. This is what they're setting out to solve.
Sentence 3 explains the core challenge and their proposed solution. Since any 2 points define a line, pairwise similarities fail to capture the structure of the problem, necessitating the use of higher-order interactions modeled by geometric hypergraphs. There's our aha, again reinforced. Pairwise breaks down, need hypergraphs.
This is really the pivotal statement, I think. It crystallizes why they need a new tool and introduces the tool. geometric hypergraphs that capture higher-order interactions. And higher order here just means interactions involving more than 2 points at a time.
Right, looking beyond just pairs. Sentence 4 describes how they build this hypergraph. We encode geometry into a 3-uniform hypergraph by treating sets of 3 points as hyperedges whenever they're approximately collinear. Okay, so not just any number of points, but specifically 3 points. And the condition is approximately collinear.
A 3-uniform hypergraph means every single hyperedge connects exactly 3 vertices, or 3 points in our case. They chose triples because 3 points provide the simplest geometric test for collinearity. I mean, you can fit a line to 3 points and see how well they align, right?
Makes sense.
This directly captures the geometric aspect of the hypergraph construction. It's not just abstract connections, it's based on geometry.
Sentence 5 links the hypergraph structure back to the problem. The resulting hypergraph contains information about the underlying line segments, which can then be extracted using community recovery algorithms. So the line structures are somehow encoded in the hypergraph's connections.
Exactly. The hope is that points belonging to the same true line segment will form these dense, interconnected groups. Communities is the technical term within this hypergraph. Why? Because triples of points from that same line should pass the collinearity test often and form hyperedges.
And community recovery is just finding those groups.
Yep. It's the task of finding these clusters or communities of vertices in the hypergraph, which ideally correspond directly to the points on the different lines.
Okay, now sentence 6 points out a key theoretical challenge. In contrast to classical hypergraph block models, latent geometric constraints in this construction introduce significant dependencies between hyperedges, which restricts the applicability of many standard theoretical tools. So this isn't just applying standard hypergraph theory off the shelf. The geometry makes things complicated.
This is a really important point, especially for researchers in this area. You see, standard models, like the hypergraph stochastic block model I mentioned, often assume a level of independence between the hyperedges. Maybe they appear randomly, conditioned on the community labels, but kind of independently otherwise.
But not here.
Not here. The fact that hyperedges are formed by geometric properties, collinearity, means they aren't independent at all. Think about it. If points I, j, f, a, k are nearly collinear and form a hyperedge, and points I, j, l are also nearly collinear and form a hyperedge, well, that tells you something about the relative positions of k and l, right? Their positions aren't independent given I and j.
Ah, I see. The geometry ties them together.
Exactly. This geometric structure creates complex dependencies that break the assumptions baked into many existing theories for analyzing hypergraphs. It's a novel challenge.
Sentences 7 and 8 state the paper's overall goals. We aim to determine the fundamental limits of line clustering and evaluate hypergraph-based line clustering methods. So, both understanding the theoretical boundary and testing a practical approach.
A classic dual objective in theoretical ML and stats. What's possible in principle, and how well does our proposed method actually achieve it?
Sentence 9 gets specific about the theoretical findings. To this end, we derive information-theoretic thresholds for exact and almost exact recovery for data generated from intersecting lines on a plane with additive Gaussian noise.
Right. Information-theoretic thresholds are key here. You can think of them as representing the absolute best-case scenario, the fundamental limit. No algorithm, no matter how clever, can perform better than these limits.
Why not?
Because these limits are dictated solely by the information present in the data itself. Given the data generation model, the noise level, the number of points, the line separation. It's about whether enough information exists to solve the problem, regardless of how you try to extract it.
Okay. And they define exact recovery and almost exact recovery. We'll get rigorous definitions later, I guess, but conceptually.
Yeah, conceptually exact means perfectly classifying every single point with high probability as your data set gets larger. Zero error.
And almost exact.
Almost exact is a bit more relaxed. It means the fraction of misclassified points goes to 0 with high probability. You might misclassify a few, but the error rate vanishes as n increases.
Okay. Exact is 0 error. Almost exact is vanishing error rate. Got it.
Precisely.
Finally, sentence 10 introduces their algorithm. We develop a polynomial-time spectral algorithm and show that it succeeds under noise conditions that match the information-theoretic bounds up to a polylogarithmic factor.
Lots to unpack there. Polynomial time basically means it's computationally efficient enough to run on realistic datasets. It's running timescales reasonably, like n squared or n cubed with a number of points n, not exponentially.
Good. And spectral algorithm.
That usually means it relies on the eigenvalues and eigenvectors, the spectrum of some matrix derived from the data structure. In this case, a matrix derived from their geometric hypergraph.
And matching the IT bounds up to a polylogarithmic factor, what does that mean in practice?
That's actually a very strong result. It means their algorithm's performance comes incredibly close to that fundamental information-theoretic limit we just talked about.
How close?
The difference is only by factors involving logarithms of n, like log n or log n squared. Logarithms grow extremely slowly compared to n itself. So for all practical purposes, the algorithm is nearly optimal in terms of the relationship between the noise level it can handle and the number of points needed for recovery.
Wow. Okay. So the abstract gives us the whole story in miniature problem, why it's hard for standard tools, their clever idea using geometric hypergraphs, the theoretical challenges due to dependencies, the fundamental limits they found, and an efficient algorithm that nearly hits those limits.
Exactly. A concise and powerful summary of their work.
All right, let's expand on this. We need to move into section 1, the introduction, which spans pages 1 through 3.
Right. This section provides more background, motivation, and formally defines the problem and their specific model. Let's dig in.
The first paragraph on page 1 basically reiterates the limitation of standard graph methods we just discussed. It says traditional data analysis often represents data as a weighted graph. However, these methods fundamentally rely on the assumption that pairwise interactions can capture the structure of the data.
Yeah, and it calls out line clustering specifically as illustrating the fragility of the assumption.
Because, again, a graph-based framework that incorporates pairwise similarity scores does not help since every pair of points forms a line.
It really drives home the point. A graph where connection strength is based on, say, how close 2 points are, or maybe the angle of the line segment connecting them, it just won't differentiate points belonging to a true underlying line from just random pairs that happen to be close or aligned.
So you absolutely need something that looks at groups.
Which leads them back to the need for higher order interactions.
Gotcha. Okay, the second paragraph, moving on to page 2, this is where they formally introduce the specific model they study, the Gaussian line mixture model, GLMMN, L1, L2 says.
Right. This is where they define their clean mathematical sandbox, the controlled environment for doing rigorous theoretical analysis. Let's break it down. We have n data points, which they call xi, living in a 2D plane.
R2. Okay, n points in 2D.
These points are assumed to come from one of two underlying hidden line segments. Let's call them L1 and L2.
So each point secretly belongs to either L1 or L2.
Exactly. And they use a community membership vector, Z, to keep track of this. It's a vector Z equals Z1, Zn, where each Z is either 1 or 2, telling us if point I truly belongs to line L1 or line L2.
Okay, so Z holds the ground truth labels.
Correct. Then there's a parameter, which is just a positive number controlling the noise level. Higher SEV means more noise.
Makes sense. And how are the actual observed points xi generated?
The generative process is defined by the equation xi ue plus ci. Let's look at each piece.
Okay.
Ue is the true position of the point. It's a point chosen uniformly at random from the line segment ci. So if Z1, ue is a random point on L1. If Z2, ue is a random point on L2. This is the point's ideal noiseless location.
Right, where it should be if there were no noise.
Exactly. Then you have E. This is a random noise vector in 2D. Specifically, it's drawn from a standard bivariate normal distribution. That means each component, like the x and y deviation, is independently sampled from a standard normal distribution, which has mean 0 and variance 1. Think of it as a random nudge in a random direction.
Okay, standard Gaussian noise.
And so it just scales that noise vector.
Yeah.
So Cia is the actual noise added to the true point UE.
So each observed point E is just its true location on one of the lines, plus some scaled Gaussian fuzz added to it.
Precisely. And a crucial assumption is that all the true locations E and all the noise vectors Y are independent of each other across all the points.
Got it. Independence makes the math tractable.
Very much so.
Yeah.
So GLMN, L1, L2, done Z, describes the probability distribution of the observed point cloud X, given the true line segments L1, L2, the noise level Z, and the true assignment Z.
And they also mentioned GLMN, L1, L2 without the given Z? What's that?
That's just the case where the true assignment Z are also considered random. Specifically, they assume each Z is chosen independently and uniformly from 1, 2. So each point has a 50-50 chance of belonging to line 1 or line 2, independently of all others. This is a common simplification for analyzing average case performance.
Okay, clear model. Now, the third paragraph on page 2 circles back to the main goal. Our goal is to estimate the community membership vector z and consequently the corresponding line representation based on the observed data x. So, given only the noisy points x, figure out which point belongs to which line, estimate z, and also figure out what the lines L1 and L2 actually are.
Yep. And they immediately connect this goal back to needing to capture those higher-order geometric relationships.
Which brings them again to hypergraphs. They reintroduce the idea. Hypergraphs generalize graphs, hyperedges connect more than two vertices, and they state their contribution, establishing theoretical consistency of a hypergraph-based algorithm for line clustering. They frame it explicitly as a community detection problem on a hypergraph, saying they draw on literature from that field.
Right. Leveraging existing tools and ideas from community detection, but adapting them to this specific geometric setting.
The fourth paragraph on page 2 then surveys some of that prior work in community detection, both on standard graphs and on hypergraphs. They mention a couple of references, 113.
And they bring up a standard theoretical model for hypergraphs with communities, hypergraph stochastic block models, or HSBMs. They note that these often involve tensors, which can be computationally challenging to work with directly.
So what's the common workaround?
A very common technique is called clique projection, or clique expansion.
Clique projection. What does that mean, again, conceptually?
Okay, imagine you have a hyperedge connecting 3 points, say I, J, and K. In clique projection, you basically replace that single three-way connection with all possible pairwise connections within that group.
Ah, so you'd add a regular edge between I and J, another between I and K, and a third between J and K.
Exactly.
Yeah.
You do this for every hyperedge in your original hypergraph. You essentially flatten the higher order structure down into a standard graph structure.
And the similarity matrix W we saw in the abstract comes from this projected graph.
Often, yes. A common way to define the similarity between two vertices I and J in the projected graph is simply to count how many original hyperedges contain both I and J.
I see. So pairs that co-occur frequently in the original hyperedges get a high similarity score in the projected graph.
Precisely. And once you have this similarity matrix W, or an adjacency matrix A, you can then apply standard graph algorithms to it. They mention spectral algorithms 15, 29, and semi-definite programming, SDP algorithms 3, 14, that operate on matrices derived from this projected graph. They also mention modularity-based approaches 9.
But then they immediately circle back to the critical challenge for their specific problem, line clustering, they say. While several recent works treat line clustering as a motivating example for hypergraph clustering algorithms 8, 17, their theoretical guarantees typically rely on independence assumptions between hyperedges.
And here it is again, the core issue they're tackling. Standard hypergraph theory, even for HSBMs, often assumes that hyperedges appear kind of independently, maybe conditioned on the communities, but without these strong structural ties between them.
But their geometric hypergraph violates this.
Violates it fundamentally. As they state, the line clustering problem inherently violates this assumption, as the geometric structure induces strong dependencies between hyperedges. That example we discussed, if IJK and IJL are both hyperedges, because of collinearity, there's a dependency. This makes applying those standard theoretical results directly very difficult or even invalid.
Right, you can't just plug and play.
Definitely not. You need analysis that explicitly handles these dependencies.
Okay, the fifth paragraph on page 2 continues discussing previous work specifically on line clustering itself. They mention earlier hypergraph representations 2, 21, 30, often using spectral methods on these graph projections we just talked about.
And also more recent work using things like modularity maximization 17 and expectation maximization EM algorithms 8. But then they interestingly contrast these relatively recent hypergraph approaches with methods that came even before hypergraphs were widely used for this.
Like the classic Ho transform, right? Mentioned going into page 3, attributed to Duda and Hart back in the 1970s, 12.
Yeah, the Ho transform is a really elegant idea from computer vision, a classic piece of applied geometry. The core concept is to transform the problem from the image space, where you have points, to a different space, a parameter space.
Parameter space.
Yeah. Think about a line in the z-plane. You can describe it uniquely using different parameters. One common way is using its angle, theta, relative to the x-axis, and its perpendicular distance from the origin. So any line corresponds to a point in this parameter space.
Okay.
Now, take a single point, x, y, in the original image space. How many lines pass through it?
Infinitely many.
Right. And each of those lines has a different palm. It turns out that the set of all the pairs for lines passing through a fixed point, x, y, forms a specific curve in the O parameter space. Specifically, it's a sinusoid, O equals the plus Borasina.
Ah, okay. So one point in image space maps to a curve in parameter space.
Exactly. Now, here's the clever part. Suppose you have several points in the image space that are all collinearies, meaning they all lie on the same line, which has specific parameters. Say, what happens in the parameter space?
Well, each point maps to a curve. And if they're all on the same line, then that point must lie on all of those curves.
Precisely. The curves corresponding to the collinear points will all intersect or be concurrent at the single point in the parameter space.
So finding collinear points in the image becomes finding a point where many curves intersect in the parameter space. That's very cool.
It is. As the paper says, the Hot transform maps the points to sinusoidal curves and reduces the problem of finding collinear points to that of locating concurrent curves in the transform space. It's been a workhorse in Computer Vision 16 for decades.
But it has limitations, right?
Yeah, the main practical limitation mentioned is memory and computation. The Hot transform requires a prohibitive amount of memory to work with parameterized curves. Typically, you have to discretize the parameter space into a grid of bins, an accumulator array. For each point, x, y, you trace its curve through this grid and increment the count in each bin it passes through. Bins with high counts correspond to potential lines.
And that grid can get huge.
It can, especially if you need high resolution and often, or if you're dealing with more complex shapes than lines, which might require higher dimensional parameter spaces.
Got it. Okay, moving on. The sixth paragraph on page 3 talks about related statistical work, specifically citing Arias Castro and colleagues 5. How does that relate?
It's related because it also deals with finding geometric structures in noise, but the goal is slightly different. Their focus was on detecting the presence of a faint geometric object, such as a line, curve, or disk, in a noisy image.
Detecting the presence. So more like a yes-no question. Is there a line here or not?
Exactly.
Right.
It's framed as a hypothesis testing problem. The null hypothesis is that the data is just pure noise. For example, uniformly random points or pixels with random intensities. The alternative hypothesis is that there's noise plus some faint underlying geometric structure. Their goal was to develop statistical tests to distinguish between these two possibilities.
And they use multi-scale scan statistics. What's that?
It's a technique where you essentially scan the data with windows or regions of different sizes and shapes, hence multi-scale. Within each window, you compute some statistic that measures how much evidence there is for the structure you're looking for, like how many points fall in a narrow rectangular window suggesting a line. Then you look at the maximum value of this statistic across all possible windows. If that maximum value is unusually high compared to what you'd expect under pure noise, you reject the null hypothesis and conclude that a structure is likely present.
Okay, so their work is primarily about detection, saying, yes, based on the statistics, it looks like there's a line segment hidden in this noise somewhere. It doesn't necessarily tell you exactly which points belong to it or precisely estimate its parameters like center and orientation.
Precisely. As the paper notes, even though the location of the window with the maximum statistic might give you a hint about where the object is, the accompanying theory considers the detection problem and gives no guarantees on point-wise labeling of the data or consistent estimation of the object's geometry. Their subsequent work, 4-6, apparently improved the detection algorithms and analysis, but the focus remained on detection rather than precise recovery.
Which brings us neatly to the 7th paragraph, still on page 3, where they explicitly contrast this paper's focus with that detection work. In contrast, our work addresses the distinct problem of community recovery in a structured mixture model.
Right. They emphasize their goal isn't just detection, but recovery. They state their dual objective very clearly here.
Okay, what are the two parts?
First, accurately assign each observation to its true line segment, achieving exact or almost exact recovery. That's the point-wise labeling problem, getting the vector z correct.
And second,
consistently estimate the center and orientation of each line segment. That's getting the geometric parameters of L1 and L2 right.
And they call these complementary regimes, detection versus recovery.
Yeah. The idea is that you might be able to detect the presence of a line even when the signal, the points actually on the line relative to the noise, is quite faint. But to accurately recover which points belong to the line and estimate its properties precisely, you might need a stronger signal or lower noise. It's plausible that detection is possible in regimes where recovery is not.
Makes sense. You can tell something is there before you can perfectly outline it.
Exactly.
Okay, finally, before we leave the intro, the contributions section on page 3 summarizes their key achievements. Let's walk through those.
Sure. They list three main contributions.
Number one.
Contribution 1. We derive conditions on the model parameters that determine the statistical limits of recovery. They specifically mention the GLMMN model with intersecting lines and Gaussian noise, and they state the key result. Exact recovery is possible if and only if, and A1, almost exact recovery is possible if and only if AD1. This is Theorem 1, which we'll dive into more formally soon.
Okay, so these are the fundamental limits based purely on the model's information content. Exact recovery, 0 errors, needs noise to vanish really fast, faster than 1n. Almost exact recovery, vanishing error rate, just needs SIF to vanish at all as n grows. We need to remember that suff n notation means uff n goes to 0.
Exactly. These are the necessary and sufficient conditions derived from information theory. If your noise is higher than these thresholds relative to n, no algorithm, no matter how good, can achieve the corresponding type of recovery.
Got it. Contribution number 2.
Contribution 2. We introduce a geometric hypergraph representation based on total least squares, TLS residuals, over all triples, capturing latent collinearity.
So this is their specific way of building the hypergraph. Using triples of points, calculating a TLS score for each triple, which measures how well they fit a line, and creating a hyperedge if that score is low enough.
Yep, that's the core construction. We'll need to define TLS properly later.
And contribution number 3.
Contribution 3. We propose a polynomial-time spectral algorithm based on the geometric hypergraph, requiring no prior knowledge of the underlying line structure.
Okay, this is the practical algorithm. It runs efficiently, polynomial time, uses the hypergraph they just defined, and importantly, you don't need to tell it where the lines are supposed to be beforehand.
Right, and they immediately state its performance guarantees.
Yeah. If a threshold for forming hypergraphs is chosen so that slog NATA n all n, the method achieves exact recovery, matching the information-theoretic threshold up to a polylogarithmic factor. This is Theorem 2, Part B.
This is the really strong theoretical guarantee for their algorithm. It says there's a sweet spot for choosing the hyperedge threshold t. It has to be related to the noise and the number of points n in this specific way, larger than pol times log n, but smaller than 1n log n, if you can pick t in that range.
Then the algorithm achieves perfect exact recovery.
Exactly. And crucially, it matches that fundamental Seuss limit for exact recovery we saw earlier, up to those polylog factors, like log n and log n. It's computationally efficient and nearly information-theoretically optimal for exact recovery.
That sweet spot for t depends on Seuss, the noise level, right? What if you don't know Seuss? That seems like a major practical issue.
It absolutely is. And they address it directly in the next part of Contribution 3. Moreover, we provide a data-driven rule that selects t from the empirical distribution of the TLS residual. This requires no prior knowledge of the codes and guarantees almost exact recovery when O1. This corresponds to their Algorithm 2 and Theorem 3.
Okay. So they have a way to let the algorithm figure out a good threshold too, just by looking at the data itself without needing the user to input the noise level.
Exactly. It's a data-driven threshold selection method.
And with this data-driven T, it guarantees almost exact recovery as long as the noise is vanishing.
Which perfectly matches the information-theoretic threshold for almost exact recovery from Theorem 1.
That's a crucial practical piece. It means the algorithm can be used effectively even when you don't know the underlying noise parameters, and it still achieves the fundamental limit for getting the error rate down to 0.
It makes the whole approach much more applicable in real-world scenarios.
Okay. The concluding sentence just ties it all together, saying this work illustrates how geometric constraints can be encoded in hypergraphs, highlights the impact of the resulting hyperedge dependencies on the analysis, and offers broader insights for other geometry-aware community recovery problems.
Yeah, the lessons learned here about handling these geometric dependencies might be useful in other domains where structure isn't just random pairwise connections.
All right, great overview. Before we dive into the theorems themselves, let's get the notation straight. Page 4 has remark 1 on notation. These symbols, are going to appear everywhere.
Absolutely essential to understand these precisely. They're all about comparing how sequences behave as n, the number of points, grows towards infinity.
Okay, first, bold letters for vectors and matrices. Standard enough.
Then for two sequences depending on n, say an and bn. First notation. an, bn, n. This means the limit of the ratio an divided by bn as n goes to infinity is 0.
So an becomes negligibly small compared to bn for large n.
Exactly. Like if they say n are 1, it means the noise level n must approach 0 as n increases. If they say ANN, it means n must go to 0 even faster, such that NN still goes to 0.
Got it. What about NaN with the slash?
That means the opposite. The limit of the ratio AN/BN as n goes to infinity is strictly greater than 0. It might be a positive constant, or it might even go to infinity. The key is the ratio does not go to 0.
So AN does not become negligible compared to BN. If NNN, it means NN stays bounded away from 0 or grows.
Correct. And the last one is an NAB/BN, the little squiggle underneath.
Yeah, what's that? It's like less than or approximately equal to.
Kinda. It means n is less than or equal to BN up to a constant factor. More formally, there exists some positive constant c, such that an NSEBN for all sufficiently large n.
Ah, okay. So it ignores constant multiples, just focuses on the growth rate. AN grows no faster than BN.
Precisely. It captures the dominant scaling behavior. And you could define an NNOBN similarly, meaning an NAOCBN for some C0. And NABN would mean both an NOBN and an NOBN hold they grow at the same rate, up to constants.
Okay, notation clear. Now we can tackle the technical meat. Let's start with the information-theoretic bounds, section 2, starting on page 4.
Right. This section aims to quantify the absolute fundamental limits of the line clustering problem within their chosen GLMMN model. The core task, remember, is estimating the true community membership vectors, S, based only on observing the noisy data points, X.
And to measure success, they first need precise definitions. Definition 1 on page 4 gives us exact and almost exact recovery. These rely on a specific distance measure, right?
Yes, the permutation invariant Hamming distance denoted. Let's break that down. Hamming distance normally just counts the number of positions where two sequences differ.
So the number of points misclassified.
Right. But here, the cluster labels themselves, 1 and 2, are arbitrary. We don't care if we call the first line cluster 1 and second cluster 2, or vice versa. We only care if we put points from the same true line into the same estimated cluster.
Ah, so the distance needs to account for potentially swapping the estimated labels.
Exactly. Ham's I calculates the minimum Hamming distance between estimated labels and Z, true labels, over the two possible permutations of the labels. 1. You either compare O directly to Z, or you compare O with swapped labels, 1s become 2s, 2s become 1s to Z, and take the smaller number of mismatches.
Okay, so it's the minimum number of misclassified points allowing for label swapping.
Precisely. Now, using this distance, they define the two main notions of consistency or successful recovery as n goes to infinity.
First, exact recovery.
Exact recovery holds if the probability that Ham's is exactly 0 goes to 1 as n approaches infinity. Lim NP is 1.
Meaning, with very high probability, you get every single point classified correctly, up to swapping the overall cluster names. Perfect labeling. Asymptotically.
Yes, the strongest possible guarantee.
Second, almost exact recovery.
Almost exact recovery is a bit weaker. It holds if, for any small positive number, epsilon, the probability that the fraction of misclassified points, Ham A as n, is less than or equal to 4 goes to 1 as n approaches infinity. Lim NA 1 for all 0.
So the error rate goes to 0. You might still misclassify some points, maybe even a growing number, but the proportion of errors becomes vanishingly small.
Exactly. Vanishing error rate is the key for almost exact recovery.
Okay, definition's clear. Now, theorem 1, stated right there on page 4. This gives the fundamental limits, but in a simplified oracle setting, right?
Yes, the oracle setting is crucial here. It assumes that the equations of the two true line segments, L1 and L2, are known to the algorithm. You don't have to estimate the lines themselves, only assign the points E to the correct known line.
Why make that assumption? It seems unrealistic.
It's a standard technique for finding lower bounds. If you can't succeed even when you're given the true lines, you definitely can't succeed when you also have to figure out the lines from the noisy data. So the performance limit in this easier oracle setting provides a necessary condition, a lower bound, for the harder, more realistic problem.
I see. If it's impossible in the easy case, it's impossible in the hard case.
Exactly. So in this oracle setting, the problem simplifies. For each point sheet, you just need to decide, is it more likely to have come from L1 plus noise or L2 plus noise? This becomes a standard binary hypothesis test for each point.
And theorem 1 states the result for this hypothesis testing problem. Assuming the specific GLMMN setup, two lines L1, L2, and R2 equal length, intersecting at their midpoint with noise n. The subscript n reminds us the noise might depend on n, and the algorithm knows L1 and L2.
Correct. Under those conditions, theorem 1 states, 1. Exact recovery is possible if and only if sen 2. Almost exact recovery is possible if and only if sen 1.
If and only if. So these are type bounds. They define precisely when recovery is possible and when it's impossible in this oracle setting.
Exactly. Noise n must vanish faster than 1n for perfect labeling. Noise n just needs to vanish at all, but can do so much slower, like 1n or even 1 log n, for the error rate to vanish.
And the theorem also mentions that the maximum likelihood estimator, MLE, achieves these bounds.
Right. The MLE is the optimal decision rule for this hypothesis testing problem, by the Neyman-Pearson lemma, essentially. The fact that MLE achieves these bounds confirms that they are indeed the true information-theoretic limits for this oracle problem. If SEN doesn't satisfy the condition, no algorithm, not even the optimal MLE, can achieve the corresponding recovery.
Okay. The discussion below Theorem 1 adds a couple of nuances. First, it notes that this threshold, or SEN G1, is actually independent of the angle between the lines as long as the angle is fixed and not zero or teal.
Yeah, that's interesting. Intuitively, you might think perpendicular lines are easier to distinguish than lines at a very small angle. And maybe they are for finite n. But asymptotically, as n gets large, the fundamental threshold condition on n only depends on n, not the angle, as long as it's fixed. The angle affects the constant factors, but not the scaling law.
And they also mention that for their algorithmic analysis later, in Section 6, they'll often focus on the special case where the lines are perpendicular.
Right. That's mainly for algebraic convenience. The math often simplifies nicely when things are orthogonal, but they stress that the information-theoretic bounds themselves hold more generally.
Okay, so we have the fundamental limits. Now, to really understand why these specific thresholds and 1 pop up, we need to look at the derivation, which involves the MLE analysis detailed back in Section 4, titled Information-Theoretic Analysis, starting on page 7.
It's exactly. Section 4 provides the mathematical justification for Theorem 1. As we said in the oracle setting, estimating the community label Z for a single point, xi, boils down to a hypothesis test. Did xi come from distribution F1, generated via L1 plus noise, or F2, generated via L2 plus noise?
And the MLE is the optimal test here. It decides based on the probability density functions, FKX. Page 7 gives the formula for FKX. It looks like an integral.
It is FKX 1 UDO. Let's decode that.
Yeah.
Is the length of line segment LKX is the probability density function of the 2D Gaussian noise 2-on. It's basically 1 XPSY.
Okay, the Gaussian bell curve density in 2D.
Right. So FKX is saying the probability density of observing point X, given it came from line LK, is the average density you'd get by picking a true point uniformly along the line segment LK, that's the one L do part, and then seeing the probability density of the noise XU, accounting for the difference. That's the XU part.
And so it's like smearing the Gaussian noise kernel all along the line segment LK and averaging.
That's a great way to visualize it. It's the density generated by that process. The MLE for a given point, she then simply calculates F1 EY and F2's Y and assigns G to the label K, for which FK is larger. Ties can be broken arbitrarily. It doesn't affect the asymptotic result.
Okay. Now, the error probability for classifying a single point, which they call per. Page 8 relates this to the total variation distance, DTV, between the two distributions, F1 and F2. It says per extolled 1 DTV F1 F2.
Right. The total variation distance, DTV, F1, F2, measures the maximum difference in probability the two distributions assigned to the same event, or set A. It ranges from 0 if F1 and F2 are identical to 1 if they assign probability to completely disjoint regions.
So if DTV is close to 1, the distributions are very distinct, and the error probability per is close to 0. If DTV is close to 0, they're very similar, and per is close to 12, like guessing.
Exactly. The formula per F1 AC sheet connects it directly to the geometry. AC key is the region in R2 where the density F2x is greater than F1x. Per is the probability that a point truly from line 1 happens to land in the region where line 2 looks more likely.
Okay. Now, the absolute key to Theorem 1 is lemma 1 on page 8. This lemma tells us how per behaves when the noise is small.
Yes, this is the core calculation. Lemma 1 considers two lines L1, L2 of equal length, intersecting at their midpoint at an angle A, specifically in 0, 2 for the formula, but the idea holds for 0. It gives a formula for per involving an integral equation 2, but critically, it gives the limit as VISA goes to 0.
And that limit is lim sur up, where C is some constant depending only on the line length and the angle up. Specifically, C A plus kaup plus za.
This is the punchline. For small noise, the probability of misclassifying a single point per is approximately linearly proportional to hus per CA. Doubling the noise roughly doubles the single point error rate, when SU is small.
And the constant of proportionality C depends on the geometry and of.
Right. Longer lines, or lines closer to perpendicular, might have smaller constant C, meaning less error for the same, but the scaling with SUD is linear.
The proof of Lemma 1 spans pages 8 to 10 and looks pretty intense mathematically. Lots of integrals, coordinate transformations, changes of variables.
It is. We probably shouldn't try to replicate every integral step here, but we can outline the strategy.
Okay, what's the high-level approach?
First, they simplify the geometry without loss of generality, WLG. They align the lines symmetrically around the axis, as shown in Figure 2. L1 might be along y equals x tan, and L2 along y equals x f1x.
Makes sense. Coordinate simplify things.
Then they identify the decision region AX, where f2x, f1x. Due to symmetry in the setup, it corresponds to the second and fourth quadrants, where x and y have opposite signs. Per is the probability that a point generated from L1 lands in AT.
Okay.
They write this probability as an interval. A point from L1 has true position on L1 and observed position x equals u plus y. It lands in ATT if its x component is positive and y component is negative, or x is negative and y is positive. They express this condition in terms of u, parameterizing L1, and the noise components y1, y2.
So it becomes a probability involving the random u and the standard normal y1, y2.
Exactly. This leads to an integral expression for per involving the complementary CDF of the standard normal distribution. It looks like equation 2 in the paper.
Right. Per u is 1 do.
Then comes the asymptotic analysis as E0. They perform a change of variables, letting ES use, the integral limits change, and the ES comes out as a factor. As E0, the integration range effectively becomes infinite.
So they need to evaluate some combination of E's functions die.
Correct. This involves evaluating 3 types of integrals involving A. They use techniques like changing the order of integration, for Beanie's theorem, and switching to polar coordinates in one case. The results involve terms like 1/8 and 4/u.
And when they combine all the pieces.
After some algebraic simplification, the constant factor C emerges, matching the statement in Lemma 1. The details are technical, involving careful evaluation of Gaussian-related integrals, but the outcome is that crucial linear dependence.
Okay, so we accept Lemma 1. The single point error rate scales linearly with so small. Now, how does this lead to the proof of Theorem 1 back on page 11?
Right, the proof of Theorem 1 leverages this per result for n independent points.
Let's take exact recovery first. Why is n necessary? The only if part.
Okay, necessary condition for exact recovery. We need PM as n1. This means the probability of making at least one error must go to 0. What's the probability of at least one error? For small per, it's roughly bounded by n per, using a union bound or 1 as x.
Okay, probability of 1 area n per?
From Lemma 1, we know per SNC, using Ken now since it depends on n. So the probability of at least one error is approximately n sen c.
If sen, it means sen n does not go to 0.
Right. It stays bounded above 0 or goes to infinity, which means n per also does not go to 0.
So the probability of making at least one error does not go to 0. The MLE, which is the optimal algorithm here, fails to get 0 errors with non-vanishing probability.
And if the optimal algorithm fails, no algorithm can succeed. Therefore, exact recovery is impossible if sun o no.
Makes perfect sense. Now, the sufficient condition for exact recovery, if sun o, why is it possible?
Well, if sun o no, then sun o n does go to 0.
So n per n sen c also goes to 0.
Right. The probability of making at least one error goes to 0, which means the probability of making 0 errors goes to 1. The MLE succeeds WHP. So exact recovery is possible.
Okay, that covers exact recovery. Now for almost exact recovery, M error A 0 in probability. Let's start with a sufficient condition. If sin were 1, why is it possible?
This uses Markov's inequality. Let B be the number of errors. We want to show PBN or 0, 0 for any sin row.
What's the expected fraction of errors EZN?
Since the errors are independent Bernoulli trials in this Oracle MLE setting with probability per, the expected number of errors EB is n per. So the expected fraction is EBN per.
Okay, and if I'm a row 1?
The number 1 tells us if n arrow 1, then per also, either since per and since c.
So EBN E0. Now apply Markov's.
Markov's inequality states PXAALRO for a non-negative random variable x. Here XEN and O, so PEAAN EO.
So PAAAMA equals per O.
Since per EO, per also goes to 0 for any fixed or 0.
Exactly. The probability that the fraction of errors exceeds any small constant goes to 0. That is precisely the definition of almost exact recovery. So sun arrow 1 is sufficient.
Great. Finally, the necessary condition for almost exact recovery. This way is it impossible.
Okay, if deno 1, it means NU does not go to 0 as NU. It might approach some positive constant or even grow.
And if n doesn't go to 0, what does lemma 1 tell us about per?
It tells us per also does not go to 0.
Yeah.
Because per AAC, if sen and a is bounded below by some positive constant, then per is also bounded below by some positive constant. Let's call it C ASIO.
So the expected error rate EBN per O0, how does this prevent almost exact recovery? We need PBN ain't O for all 0. But if the expected error rate is C, intuitively, the actual error rate BN should be close to C pretty often. The paper uses a slightly more refined argument than just Markov's here, referencing page 12, end of proof. It essentially argues that if EBN at A is bounded below by C, then PBI will also be bounded below by some positive number for any chosen small enough, specifically CO.
So the probability of having at least a small fraction of errors does not go to 0.
Correct, which means the condition for almost exact recovery fails. It's impossible if Marsen doesn't vanish.
Wow. Okay, that nails down theorem 1 completely. The conditions NA-no and SENA-1 really emerge directly from the linear scaling of the single-point error probability per with psi, combined with how errors accumulate over n independent points.
Precisely. It's a beautiful connection between the local error rate and the global recovery guarantees.
That was a deep dive into the theoretical bedrock. Foundational limits established. Now let's shift gears from what's possible in principle, especially in that Oracle setting, to how they actually build an algorithm to achieve recovery in the realistic setting where the lines are unknown. We need to go back to section 3, algorithms, starting on page 5.
Right. Having established the targets, the IT bounds, now they need a constructive method. They start by formally defining the tool they use to measure collinearity. Total least squares, TLS.
Yes, page 5. Given 3 points x1, x2, x3 are 2, we seek to estimate a line L that best fits the points by minimizing the sum of squared orthogonal distances between she and L.
This is different from standard linear regression or ordinary least squares, OLS, which typically minimizes the sum of squared vertical distances, errors in Y for given x. TLS minimizes the sum of squared perpendicular distances from the points to the fitted line.
Why is TLS more appropriate here?
Because in their GLMMN model, the noise Y is isotropic. It affects both the x and y coordinates. There isn't a preferred dependent variable direction. TLS treats errors in both coordinates symmetrically, which matches the noise model better. It finds the line L that passes closest to all 3 points in terms of orthogonal distance.
Okay. And equation 1 gives the TLS score, so TLS x1, x2, x3 equals min IOA, I or 1, where DAJL is that orthogonal distance.
So sol TLS is a non-negative number. A small value means the 3 points Shay, xj, xk lie very close to some common line. A large value means they don't.
And this score is the key ingredient for building their hypergraph, right?
Exactly. As described on page 5, they construct a 3-uniform hypergraph H. The vertices V of the hypergraph are simply the n data points x1, xn. The hyperedges E are defined based on the TLS score. A set of 3 distinct points at CK forms a hyperedge if and only if their TLS score is below some threshold 2. That is IEA AE if stadius J X A J 2 TIA.
So the threshold T acts as a gatekeeper. Triples that are collinear enough, TLS score to get connected by a hyperedge. Triples that are too scattered don't.
Precisely. Figure 1 gives a nice visual. The blue points are tightly clustered. Their TLS score is low, so they form a hyperedge represented by the triangle connecting them. The red points are more spread out relative to any single line. Their TLS score is high, above TLS, so they do not form a hyperedge.
Okay, hypergraph constructed based on TLS and threshold T. Now, algorithm 1, the spectral method presented on page 6. This is their core algorithm that uses this hypergraph. Let's walk through the steps.
Sure.
The n data points x1.xn and a chosen threshold parameter t0.
An estimated community membership vector 1 to n.
Step 1.
Step 1. Construct the TLS hypergraph H, VEE, using the input points in the threshold T, just as we discussed. Find all triples I, J, A, such that TLSI says xj, xe2. Step 2. Construct the similarity matrix W. This is an AN matrix, where the entry we is defined as the number of hyperedges in E that contain both vertex I and vertex J. We are Annie, she, JE1.
Ah, so this is exactly that clique projection similarity count we discussed earlier. If points I and J frequently belong to the same good, low TLS triple, they get a high similarity score, we.
Exactly. It captures how often pairs of points are involved in approximately collinear triples.
Step 3.
Step 3. Compute the leading eigenvectors. Find the two eigenvectors, let's call them V1 and V2, of the similarity matrix W that correspond to the two largest eigenvalues, 1 and Alaluusua. They form a matrix U area Rn2, whose columns are V1 and V2. This is the spectral part of the algorithm.
Why the top two eigenvectors?
The intuition, which needs rigorous proof later, section 6, is that if there are two underlying line clusters, the structure of W should reflect this. The eigenvector associating with the very largest eigenvalue often corresponds to the overall density or average connection strength related to the all ones vector. The second largest eigenvalue and its corresponding eigenvector V2 are expected to capture the primary community structure distinguishing between the two groups. So the spaceband by the top two eigenvectors should contain the essential clustering information.
Okay, so U contains rows, where each row U represents point Y in this 2D eigenvector space. Step 4.
Step 4. Assign labels U using k-means clustering. Take the n rows of U, which are points in R, and apply the standard k-means algorithm with k2. K-means will partition these n points in R row into two clusters. The cluster assignment for the ith row becomes the estimated label U for the original data point Y.
So construct hypergraph, compute pairwise similarities based on shared hyperedges. Find top two eigenvectors, run k-means, on the points projected onto those eigenvectors. That's algorithm 1.
That's the recipe.
Now, does it work? Theorem 2 on page 6 provides the theoretical guarantees for algorithm 1. It assumes the specific setup. Lines L1, L2 are perpendicular, equal length, intersect at midpoint. Data from GLMMN L1, L2, and a threshold Tn is used.
Right. Under those conditions, it gives two main results.
Part A.
Part A. If the noise n and threshold Tn satisfy Tn at 1, then algorithm 1 achieves almost exact recovery.
Okay, so if noise is vanishingly small, and you pick a threshold Tn that's also vanishingly small but still significantly larger than the noise, then the error rate goes to 0. This n at 1 condition matches the information-theoretic limit for almost exact recovery from Theorem 1.
It does. It shows the algorithm can achieve the optimal rate for almost exact recovery, provided Tn is chosen correctly in this range.
And Part B.
Part B. If the noise and threshold satisfy the stricter conditions Tn log n, then algorithm 1 achieves exact recovery.
Whoa. Okay, this requires noise n to be even smaller relative to n, since Tn must be smaller than n log n. No, it must be considerably smaller still. And the threshold Tn has to live in this quite narrow vanishing window. But if these conditions hold, the algorithm gets 0 errors, WHP.
Yes. And importantly, this condition for exact recovery, n log n or, essentially matches the information-theoretic threshold Tanoian from Theorem 1 up to those polylogarithmic factors, log n and log n.
So algorithm 1 is nearly optimal for both almost exact and exact recovery if you can pick the threshold Tn correctly within the specified ranges.
That's the crucial caveat highlighted in the discussion right below Theorem 2. A key limitation of algorithm 1 is that the optimal choice of Tn depends on sun. If you don't know the noise level sun, how do you select a Tn that falls into the required range, especially the very narrow range for exact recovery?
Yeah, that seems like a significant practical hurdle. If sun is unknown, you might pick a Tn that's too large or too small, and the guarantees of Theorem 2 wouldn't apply.
Exactly, which motivates their next step, algorithm 2.
Right, algorithm 2. Spectral method with threshold selection, also on page 6. This one aims to pick T automatically from the data.
This algorithm's main innovation is this data-driven threshold selection. The core idea is to find a threshold T that does a good job of separating the within-community triples, which should have low TLS scores, from the between-community triples, which should have higher TLS scores, on average.
And how do they estimate where that separation point should be without knowing the true labels?
They cleverly exploit the expected fraction of within-community triples. Remember, if we just pick 3 points, I, J, K, completely at random from the endpoints, and assume the true labels are independent Bernoulli, equal chance for line 1 or 2, what's the probability that all 3 come from the same line, i.e. C equals dk?
Let's see, probability Z1 is 12, so PZ1, Z2, Z3, 1 is 12 Adini. Probability there, all 2, is also 12 as well, so the total probability is 2, 18, 14.
Exactly. On average, about 1/4 of all possible triples should be within community triples. The other 3/4 involve points from both lines.
So algorithm 2 tries to find a threshold T such that roughly 14 of the triples have a TLS score below T.
That's the intuition. Here's how algorithm 2 works.
Points x1, point xn, m number of triples to sample, target fraction, usually 14.
Estimated labels us.
Step 1.
Step 1, sample m triples.
M.
Independently and uniformly with replacement from all possible n choose 3 triples. M is typically much smaller than n choose 3.
Okay, get a random sample of triples, step 2.
Step 2. Let M be the set of all nodes, indices I, that appear in any of the sampled triples 1. Let MIC be the remaining nodes, MC, 1M. They do the main clustering only on MIC-P to avoid potential biases from the sampling process itself.
Okay, sample triples, identify nodes involved, set them aside. Step 3.
Step 3. For each sample triple tie, compute its TLS score, C subtle S. Then sort these M scores in non-decreasing order, S1, S2, SM.
Got the sorted TLS scores from the sample. Step 4 is the key threshold selection.
Step 4. Threshold selection. Calculate the target index K, OM. Round M to the nearest integer, if OE 14, K is roughly M4. Set the threshold T to be the K the smallest score, T is OM, or S1 if K1.
So T is literally the TLS score at the thick percentile, e.g. 25th percentile, if 8 of 14 of the sampled scores. It's the value that cuts off the bottom fraction of the observed TLS scores in the sample.
Exactly. It's automatically determined for the data distribution.
Exactly.
Step 5. Now run the original spectral method, algorithm 1, but only on the data points corresponding to the nodes in MIC-C, the ones not involved in the sampling, and use the data-driven threshold T found in step 4 as the input threshold for algorithm 1. This gives estimated labels OE for all I in MIC-C.
Okay, run ALD1 on the non-sampled points using the learned threshold. What about the points in M that were set aside?
Step 6, optional. For the nodes IM, the small number involved in sampling, the paper suggests assigning their labels O uniformly at random. Since M is small relative to N, this doesn't significantly affect the overall error rate for almost exact recovery.
Okay, that's algorithm 2. Sample triples, find the score at the 14th percentile, use that score as the threshold for algorithm 1 run on the remaining points. Seems plausible. Does it work?
Theorem 3, on page 7, provides the guarantee. It assumes the same perpendicular equal-length line setup, data from GLMN, L1, L2, SEN. It's our 1, algorithm 2 with parameters 1, L or N, and LM 14 achieves almost exact recovery.
That's a fantastic result. It says if the noise is vanishing, LA1, which is the IT limit for almost exact recovery, and you sample a reasonable number of triples M, growing with N but not too fast, like NO, then algorithm 2 automatically finds a threshold T that allows algorithm 1 to achieve almost exact recovery.
Yes, it achieves the optimal IT threshold for almost exact recovery without requiring any prior knowledge of the model parameters, particularly the noise level SEN. That's the big practical advantage.
Very nice. What about the computational cost? Remark 2 on page 7 discusses complexity, mainly for algorithm 2 since it includes algorithm 1.
Right. The threshold selection part, steps 1 to 4 of ALG2, involves sampling M triples, computing MTLS scores, each takes constant time for 3 points, and sorting them. That's dominated by sorting, roughly OM log M. If M is chosen small, like MN cool is required by Theorem 3, this part is very fast compared to the rest.
Okay, so the main cost comes from step 5, running algorithm 1 on the remaining MIT N nodes. What's the cost there?
Algorithm 1 has several parts. 1, constructing the TLS hypergraph H. This potentially involves checking the TLS condition for all n choose 3 possible triples. Since n choose 3 is O, N, N, and each TLS calculation is O1, this step is ON. 2, constructing the similarity matrix W. You iterate through all the hyperedges found, at most O, N, 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 O, and for each hyperedge I, J, K, you increment Wij weak and Wij K. This also takes roughly ON time in the worst case. 3, eigenvector computation. Finding the top 2 eigenvectors of the Nean matrix W typically takes ON time using standard methods, although faster methods might exist if W is sparse. 4, k-means clustering. K-means on endpoints in 2D can be done very efficiently, often close to ON time using approximation algorithms.
So the overall complexity seems dominated by the ON steps for building the hypergraph and the similarity matrix, and maybe the eigensolver.
Correct. The paper states the total complexity is ON. This is polynomial time, which is good theoretically, meaning it's not exponential, but n can still be quite slow for very large data sets. However, it's computationally feasible for moderately sized problems.
Okay, so we have algorithms to cluster the points, algorithm 1 with known T, algorithm 2 with learned T, but the original goal also included estimating the lines themselves. That's algorithm 3, right? Page 8, line recovery.
Yes. Once you have the estimated cluster assignments O from algorithm 1 or 2, algorithm 3 tells you how to estimate the geometric properties, center, and orientation of the corresponding line segments.
Let's see algorithm 3.
Points x1, xn, and the estimated labels O1, 2n.
For each estimated cluster x1, 2, an estimated center xk air r2, and an estimated direction vector VOOC r2 with VOOC 1.
Step 1.
Step 1. For each estimated cluster k, first, identify the set of points assigned to it. Let ning-hic be the number of points in the cluster. Then, compute the sample mean centroid of these points, xk xi, and compute the sample covariance matrix. Okay, such standard multivariate statistics for the points within each estimated cluster. Calculate their mean and their covariance matrix. The covariance matrix JIC captures how the points in cluster K spread out around their mean xk.
Exactly. It's a 2x2 matrix summarizing the variance in x, the variance in y, and the covariance between x and y for the points in IC.
Step 2.
Step 2. Obtain the estimated direction vect. This is chosen as a leading eigenvector of the sample covariance matrix IC. That is, find the eigenvector corresponding to the largest eigenvalue of IC. Normalize it to have unit length.
Why the leading eigenvector of the covariance matrix? The leading eigenvector of a covariance matrix always points in the direction of maximum variance of the data. If the points in AC truly come from an underlying line segment, plus noise, the direction of maximum spread should be along that line segment. The perpendicular direction should have much less variance, ideally just the noise variance, so the principal component, given by the leading eigenvector, should align with the direction of the line.
Using principal component analysis, PCA, effectively on each cluster. Makes sense.
Pretty much, yes.
And does this work? Theorem 4 on page 8 gives the guarantee. It applies more generally now. The lines L1, L2 can be arbitrary segments, not just perpendicular, equal length, etc. The main condition is that you start with an estimator that achieves almost exact recovery, like algorithm 2 does when it's in L1.
Right. Theorem 4 states that if SEN-A1 and your UP achieves almost exact recovery, then algorithm 3 provides consistent estimates of the line parameters. What does that mean? For every tolerance odor 1, the estimated center xk converges in probability to the true mean ek of the points originating from line lk. Formally, pska or as is na. ACO would be the midpoint of lk if points u are uniform on the segment. 2. The estimated direction of O converges in probability to the true direction VK of line LK, formally P sin 1 as angle. Sin angle for small angles, this means the angle difference goes to 0.
So the theorem says, if you can cluster the points accurately enough, almost exact recovery, then simply calculating the mean and the principal component of each cluster gives you estimates of the line center and orientation that get arbitrarily close to the true values as you get more data.
Exactly. It confirms that accurate clustering, solving the assignment problem for Z, is the crucial first step. And once you have that, estimating the geometry is relatively straightforward using standard statistical estimators like sample mean and sample covariance PCA. Consistency holds.
Fantastic. So we've covered the problem setup, the information-theoretic limits, Theorem 1, the algorithms, Alg 1, 2 for clustering, Alg 3 for line recovery, and their performance guarantees, Theorems 2, 3, 4.
Yeah.
That's the main story of the paper.
It is, but underpinning theorems 2, 3, and 4 is a significant amount of mathematical analysis to handle those geometric dependencies and prove concentration bounds and perturbation results. We should probably touch on the key ideas in those proofs, drawing from sections 5, 6, 7, and 8.
Good idea. Let's start with section 5, bounds on hyperedge probabilities, pages 12-19. This seems critical, as the whole hypergraph construction depends on the probability of forming hyperedges.
Absolutely. The analysis hinges on understanding the behavior of two key probabilities defined in equation 3, PLX e to j equals to zx. The probability that a randomly chosen triple of points from the same line, a within community triple, satisfies the TLS threshold condition and forms a hyperedge. The probability that a randomly chosen triple involving points from different lines, a between community triple, satisfies the TLS condition.
And for the algorithm to work well, we want PL to be high, close to 1, and Q to be low, close to 0. Right? We want to mostly accept the good triples and reject the bad ones.
Exactly. The goal of section 5 is to derive bounds on 1p, the probability of rejecting a good triple, and Q, the probability of accepting a bad triple, to show that there exist thresholds that achieve this separation.
Okay, section 5.1 looks at the within community probability PL of P. Specifically, lemma 2 on page 12 gives an upper bound on 1p.
Right. It considers a triple G, xj, xk, where z store g1, wlog, they're all from line L1, assumed to be the x-axis. Each eue plus psi, where ue is on the x-axis. The TLS score, psi TLS x, is the minimum sum of squared orthogonal distances to any line. This score must be less than or equal to the sum of squared distances to the true line, the x-axis.
What's the distance from xi to the x-axis?
It's just the absolute value of the y component of the noise, y-u-u-l-s.
Okay.
So the probability of rejecting this triple, pect less xe, is less than or equal to y2.
Which is the same as pa2. Now, y1 and y2 are independent standard normal variables. The sum of squares of independent standard normals follows a chi-squared distribution with Play degrees of freedom. Here we have 3 points, so IA of UI2 follows a chi-squared distribution with 3 degrees of freedom.
So bounding 1p reduces to finding a tail bound for a chi-squared distribution. Precisely. Lemma 2 uses a standard Chernoff-style tail bound for chi-squared variables.
Correct.
References inequality 58 in the appendix. It shows that if it's 3/4, then 1p decreases exponentially fast as tries increases. Specifically, 1pe xp nas 32.
Where Planck 1 log dar.
The key takeaway is exponential decay. If the threshold t is just moderately larger than the noise standard deviation, the probability of rejecting a good within-community triple becomes extremely small very quickly.
Yes. Making pretty close to 1 is relatively easy.
Okay, now the harder part. Section 5.2, bounding the between-community probability q, pages 13-19. We want q to be small.
This is much trickier. Consider a between-community triple, say x1, x2 from L1 x-axis and x3 from L2. When would this happen? When could points from different lines look collinear?
It happens if, by chance, the noise vectors y1, so y2, so y3, happen to align xi xjx reasonably well along some line L, even if it's not L1 or L2. The condition, so TLSXT, means there exists at least one line L such that the sum of squared distances is less than 2. A necessary condition for this is that each individual distance, dxl, must be less than t.
Okay.
Geometrically, this means the line L must pass through the disk bxit centered at xi with radius t for all 3 points I1, 2, 3.
So a bad triple gets accepted only if there's a line that simultaneously intersects these 3 noise disks.
That's the core geometric picture. The analysis then bounds the probability of such a line existing. It relates the disks around the observed points G to disks around their true locations UI. If L intersects bxit, it must also intersect a slightly larger disk around UI bui, where the radius accounts for the noise component perpendicular to L.
This sounds complicated.
It is. The proof involves several technical lemmas and a sophisticated geometric argument using common tangents to disjoint circles.
Maybe give us the flavor. Lemma 3 on page 13 bounds the probability that 2 of these enlarged disks around U1 and U2, which are on the same line, intersect.
Right. If U1 and U2 are far apart, the disks BU1 or R1 and BU2 R2 are unlikely to intersect unless the radii R1 R2 are large, due to large noise U. Lemma 3 quantifies this, showing the intersection probability is small, roughly proportional to t plus.
Lemma 4, page 14, gives a lower bound on Q, showing it's definitely not 0.
Yes, it shows Q is at least roughly proportional to t, confirming that between-community triples can get accepted, especially if it's not small enough.
The main workhorse seems to be Lemma 6, pages 16-19, which gives an upper bound on Q when Q are both small.
Lemma 6 is where the heavy geometric machinery comes in. It aims to bound the probability of that event E1. There exists a line L intersecting the 3 disks BU1 R1, BU2 R2, BU3 R3.
How do they do it?
They condition on whether the first 2 disks around U1, U2 on the x-axis are disjoint of at E2 or not, EC2. The probability of them intersecting EC2 is small by Lemma 3, so they focus on bounding PE1 and E2.
What happens if B1 and B2 are disjoint?
This is where Lemma 5 and Corollary 1, pages 15-16, come in. They show that if 2 circles on the x-axis are disjoint, any line L that intersects both of them must lie underneath the upper envelope formed by their 4 common tangent lines. Visualize 2 separate circles. They have 4 common tangents.
Okay, that makes geometric sense. The line is constrained.
So B1 and B2 are disjoint, event E2. Any line L intersecting B1, B2, and B3 must lie below this envelope of common tangents, Tmax, can, maxical. The third point U3 is at the origin, 0, 0, in their setup. For its disk BU3, R3 to intersect such a line L, the center U3 must be close enough to the region below the tangents.
This constrains the possible noise radius R3 or equivalently the noise Y3.
Essentially, yes. It leads to an upper bound on PE1 and E2 that involves integrating over the possible positions of U1, U2, and the random radii R1, R2, R3. This involves analyzing the geometry of the common tangents, equations 10, 11, and evaluating some tricky expectations involving logarithms and square roots.
And the final result of Lemma 6.
After a lot of careful bounding and integration, they arrive at the result that for small son and t, QO t plus 1 t plus.
Okay, so Q vanishes, but much slower than the exponential decay of 1p. It goes down roughly like x log 1x, where x was t plus.
Exactly. This slower decay of Q compared to the fast decay of 1p is crucial. It implies that you can find a threshold t that is large enough compared to SAW to make 1p tiny by lemma 2, but still small enough to make Q also reasonably small by lemma 6. This possibility of separation is what makes the hypergraph approach viable.
That's a very technical section, but the takeaway is, within community rejection, 1p drops off exponentially fast with TIS, while between community acceptance, Q drops off much slower, like t plus 1, t plus.
Precisely. That difference in decay rates is fundamental.
All right, now let's move to section 6, analysis of the spectral algorithm, pages 20-26. This is where they prove theorem 2, showing algorithm 1 actually works under the conditions stated.
The overall strategy is quite standard in spectral clustering analysis, but the details are complicated by the hypergraph structure and the dependencies. The main steps are: 1. Show the observed similarity matrix W is highly concentrated around its expected value, W equals EW. 2. Analyze the structure of the expected matrix W and show its top eigenvectors reveal the true community structure, the vector Z. 3. Use matrix perturbation theory, specifically the Davis-Kahan theorem, to argue that since W is close to W, the top eigenvectors of W must be close to the top eigenvectors of W4. Show that if the eigenvectors of W are close enough to the true community structure vectors, then k-means applied to the rows of the eigenvector matrix U will correctly recover the clusters. Labels.
Okay, step by step. First, concentration of W around W, section 6.1, pages 20-23.
They need to show that the difference matrix E equals WW is small in some sense, usually measured by a matrix norm like the Frobenius norm, EF, the square root of the sum of squares of all entries.
They use several preliminary lemmas. Lemma 7, page 20, just confirms that the number of points in each true community, N1, N2, is close to N2 W at HP, using standard Chernoff bounds for binomial distributions.
Lemma 8, page 2021, extends this to counts of pairs and certain types of triples, showing they also concentrate around their expected values, WHTA. This uses Chernoff and union bounds over all pairs. These lemmas establish that the underlying combinatorial structure, number of within-between community pair triples, is well behaved.
Then lemmas 9 and 10 are the main concentration results for W itself. Lemma 9, pages 21-23, handles the exact recovery case. Lemma 10, page 23, handles the almost exact recovery case. Let's look at Lemma 9.
Lemma 9 assumes the conditions for exact recovery from theorem 2b emit TA. Under these conditions, they leverage the bounds from section 5, lemmas 2 and 6, to show that both 1p and quare are very small. Specifically, they are AA.
Tiny probabilities of error.
Yes. Using this, they bound the variance of each entry we. Recall we, or 1A way, where AG is the indicator that IIIG forms a hyperedge. The variance of we involves variances and covariances of these indicator variables AG. Because 1p and quare are so small, these variances and covariances turn out to be small, like ON.
Okay.
They sum up the variances of all Weege entries to bound the expected squared Frobenius norm EW-EWF est. Using the concentration results for pair triple counts, lemma 8, and the small variance estimates, they show EW-EWF SEON.
ON, smaller than N.
Right. Then, applying Markov's inequality, PW-EWF, or N known, this means W-EWF and no. This means W-EWF is bounded by N no 1 and 8p for any small N, or was close to EW in this sense.
And lemma 10 does a similar calculation for the almost exact recovery case, finding the W-EWF at N node AWSP. The bound is weaker, N versus N, because pet quare only guaranteed to be small, not vanishingly small.
Correct. So step 1 is done. We concentrates around EW.
Now step 2, analyze the expected matrix, WEW, section 6.2, pages 23-24.
They first calculate the expected value of we. If I and j are in the same community, the expected number of hyperedges connecting them depends on p, probability of connection if k is also same community, and q, probability of k is different community. If I and j are in different communities, z, the expectation only involves q.
This leads to the structure of W shown in equation 21. It looks like a block matrix structure.
Yes. W il win plus wout 2 j plus win wout 2 z jag. Here, J is the all-ones matrix, Z is the true one community vector, and when EWZ what equal EZA, the key is that W is a combination of the identity matrix, the all-ones matrix, and the outer product Z, which explicitly encodes the community structure.
And what are the eigenvectors of such a matrix?
Because of this structure, the top two eigenvectors are known. The eigenvector corresponding to the largest eigenvalue 1 is essentially the all-ones vector 1. The eigenvector corresponding to the second largest eigenvalue, we, is essentially the true community vector Z, or NIZI. All other n2 eigenvalues of 3n are smaller and equal to each other.
So the true community structure is perfectly encoded in the second eigenvector of the expected matrix, W.
Exactly. They calculate the eigenvalues explicitly, equations 23, 24. Importantly, they calculate the spectral gap, areas it's 2, 3. This gap represents how well separated the community representing eigenvalue 2 is from the rest. It turns out EN for PQ, a large difference between P and Q leads to a large spectral gap.
Okay, so EW has the right structure. Now, step 3. Use Davis-Kahan to link W's eigenvectors to EW's eigenvectors.
All right, the Davis-Kahan theorem is a fundamental result in matrix perturbation theory. It provides a bound on the difference between the subspaces spanned by the top eigenvectors of two matrices, say W and W, in terms of the norm of the difference between the matrices EF equals WWF and the spectral gap of the original matrix W.
How is the difference between subspaces measured?
Often using the sign of the principal angles between them, summarized by sin UEF, where U holds eigenvectors of W and U hold eigenvectors of W.
And the Davis-Kahan bound looks like?
In this context, it gives something like sin U UFC EF. Equation 27 uses a specific form. A smaller perturbation E or a larger gap year means the subspaces are closer.
And closeness of subspaces implies closeness of the eigenvectors themselves.
Up to rotation within the subspace, yes. They show that this implies UAS CEFU for some optimal rotation matrix O, equation 28. Since U contains the true community vector Z, this means that the computed eigenvectors U are close to the true structure, rotated potentially.
Excellent. So W close to EW. EW has structure. Therefore, W's eigenvectors U are close to the structured eigenvectors U. Final step 4. K-means on U, section 6.3, page 25.
Now we need to argue that applying K-means to the rows of U, which are points in R raw, will recover the communities defined by U, and thus by Z.
They use lemma 11, page 25, adapted from prior work. What does it say?
Lemma 11 provides a guarantee for K-means. Let V equal O be the rotated true target matrix whose rows represent the ideal cluster centers. If the input matrix U is sufficiently close to V, measured by UVF relative to how well separated the true cluster centers are and the minimum cluster size, N-min, then the number of misclassifications made by K-means, HAM, is also bounded.
So if U is close enough to the ideal V, K-means works well. The condition is roughly UVF area N-min constant, equation 29, and the error bound is HAM UVF ABF A, equation 30.
Exactly. It connects the matrix approximation error from spectral perturbation to the final clustering error from K-means.
Okay, now the proof of theorem 2, pages 25 to 26, just needs to plug everything together.
Pretty much. They set K2. V is the rotated ideal eigenvector matrix UO. They use the bound on UVF from Davis-Kahan, equation 31, which involves EF area. They calculate the separation between the two cluster centers in the U space. It's constant for n, equation 32. They use lemma 7 for the minimum cluster size n-min nn2, equation 33.
They plug these into the condition, 29, for lemma 11. This gives a condition on how small EF needs to be relative to would n for K-means to work, equation 34.
And they plug them into the bound, 30, for lemma 11. This gives a bound on the number of misclassifications, ham all Z, in terms of EFS and n, equation 35. Roughly ham ed EF or art. Since n PQ4, this becomes ham S EF2.
Now they just need to consider the two cases of theorem 2. First, part A, almost exact recovery, page 26.
Conditions are AF from lemma 10, we know EF W EWS NE4, also P AAF since pen. Plugging EFE into the ham bound gives ham S or n.
So the number of misclassifications is bounded by roughly n.
Right. The fraction of misclassifications ham is bounded by A. Since we can make A arbitrarily small, the fraction of errors can be made arbitrarily small, W and TEPU. That's almost exact recovery.
Okay. Now part B, exact recovery, page 26.
Conditions are slog in tem. From lemma 9, we know EF FE a.
Plugging EFGA into the ham bound gives ham hino no nonio.
So the number of misclassifications ham UA is bounded by a constant ken that doesn't depend on NWHP.
But the number of misclassifications must be an integer. How can it be bounded by an arbitrarily small constant?
That's the key. If an integer random variable, ham, is bounded above by some constant k1 with probability approaching 1, then the variable must actually be 0 with probability approaching 1, because the only integer less than 1 is 0. Since we can choose has small enough to make shu 1, the number of errors ham z must be exactly 0 WHP.
So the constant bound forces the error to be 0. That's how exact recovery is achieved.
Exactly. That concludes the proof sketch for Theorem 2.
Brilliant. That lays out the logic for why algorithm 1 works when t is chosen correctly. Now, section 7 tackles the proof for algorithm 2, where t is chosen data-drivenly, pages 27 to 33. This proves Theorem 3.
The core idea here is to show that the data-driven threshold tool selected by algorithm 2 is, with high probability, a good threshold in the sense required by the analysis of algorithm 1, specifically for Theorem 2a almost exact recovery.
Remind us how t is chosen. Sample n triples, compute their TLS scores S1, SM, sort them S1, SM, and set t where KM4.
Right. T is the score at the 25th percentile of the sampled scores. Let FMT1FAS be the empirical cumulative distribution function, ECDF, of the sampled scores. Then T is chosen such that FMT is 14.
Why 14?
Because, as we calculated, the expected fraction of within community triples in a random sample is 14. The algorithm implicitly hopes that the threshold T separating the lowest 14 of all sampled TLS scores will roughly correspond to a threshold that separates the within community triples, mostly low scores, from the between community triples, mostly higher scores.
Okay, that's the intuition. How do they prove it works?
First, a technical point on page 27-28. They argued the sampled scores psi are almost surely distinct, so the k-score k is well defined. This uses arguments about the analytic properties of the TLS score function.
Then lemma 12, page 28, shows that if m is small relative to n, the m-sampled triples are likely to be disjoint, not share any vertices, w.hp. This helps ensure independence later.
Now, the core is section 7.1 on concentration inequalities related to T. Lemma 13, pages 28 to 29, is key. It shows that the empirical distribution FMT concentrates around its expectation EFMPs. If M is large enough, 1 FMT, EFMT, MT, FMT, where EM can be made small by increasing M.
And what is EFMT?
It's the probability that a single randomly chosen triple has stochastic. Since a random triple is within community with probability 14 and between community with probability 34, we have EFMT plus 34 QB.
Okay, so FMT is close to 14 plus 34 QB.
Right.
Algorithm 2 selects T such that FMT, so T should be such that 14P few 15.
Exactly. Now, lemma 14, pages 29 to 30, explores what this implies about T. It shows two things, assuming Sanyo 1. 1. If Tn were bounded away from 0, OTN, Tn 0, then Qtn would also be bounded away from 0 by lemma 4, making EFMTN significantly larger than 14. So FMTN would also be larger than 14 WHP by lemma 13. This means the T chosen by the algorithm cannot be bounded away from 0. It must vanish, Tn WHP2. Conversely, it shows that there do exist vanishing thresholds, Sn, where SN01, for which EFM Sn is very close to 14 because both 1PSN and QSN are small.
So lemma 14 tells us the data-driven T will be small, vanish with n, and that it's possible for such a small threshold to make EFMT close to 14.
Yeah.
Now we need to know if making EFMT guarantees that Pn is close to 1 and Q is close to 0.
That's exactly what lemma 15, pages 31 33 does. It's a crucial technical lemma. It states roughly, if Tn is small, and we know EFMTN14 is small, where En14 is small, and if En sum is zero, and if SUNAT is sufficiently small relative to En, specifically Sn on Tn, then it must be the case that both Qtn and 1PTN are also small.
Wow, how does that work? How does EFMT being near 14 imply both PAN1 and CAND? Remember EFMT 14 equals 2014 plus 34Q. Couldn't a large Q be canceled by a large 1P?
That's the crux of the proof. It uses contradiction combined with the different rates at which 1P and Q depend on T and stat from lemmas 2 and 6. If both 1P and Q were significantly larger than AON, lemma 2 would imply it is small relative to T1, assuming T dominates. These conditions clash if it's small enough relative to Pgian. The log factor comes from resolving this clash. Therefore, the assumption that both 1P and Q are large must be false. They must both be small, N.
That's clever. It uses the distinct functional forms of the error probabilities.
It's a key insight derived from the geometric analysis in section 5.
Okay, so lemma 15 says, If the expected fraction EFMT is very close to 14, then PT must be close to 1, and QT must be close to 0, provided it's small enough.
Now we can finally prove Theorem 3, page 33 of the 34.
Let's recap the setup for Theorem 3. Sunny 1 Urani Brio, algorithm 2 runs.
Algorithm 2 selects T such that FMT, by lemma 13, FMT is close to EFMT, so EFMT must also be close to 14. Let M measure how close they are.
Now apply lemma 15.
Yes, we need the condition NL log on. Since study 1, we can always find a sequence N that vanishes slowly enough, for example, related to sun, such that this condition holds and EFMT is within a NA of 14 WHPT. So lemma 15 applies.
And lemma 15 tells us
that for this data-driven threshold T, we must have Qn and 101 BHAP.
So the threshold automatically chosen by algorithm 2 is guaranteed to make both types of hyperedge error probabilities small.
Exactly. Now, algorithm 2 proceeds to run algorithm 1 on the bulk of the points in Mario, using this threshold T. What are the conditions needed for algorithm 1 to achieve almost exact recovery according to Theorem 2a?
Theorem 2a required Sene 1.
We know Tn A0 by lemma 14. We know Sene 1. We need to ensure Sene 1. The analysis implicitly shows that for EFMT to be A14 when Sene 1 cannot be too small relative to Sen. It ends up satisfying Sene N. Also, the bounds Qt, A1, and 1pt are precisely what's needed for the concentration and perturbation arguments underpinning Theorem 2a to go through.
So the conditions for Theorem 2a are met WHP when using the T from algorithm 2.
Yes. Therefore, algorithm 1 run on McKee achieves almost exact recovery. Since McKee contains almost all the points, algorithm 2 overall achieves almost exact recovery. Theorem 3 is proven.
Fantastic. The data-driven threshold selection is rigorously shown to work and achieve the optimal rate.
It's a very satisfying result, connecting the empirical percentile to the required theoretical properties, small p and q.
Okay, one last section of proofs. Section 8, line recovery, pages 34-37. This is about proving Theorem 4, showing that algorithm 3, computing mean and PCA on clusters, consistently estimates the line parameters, given that we have almost exact recovery of the labels law from algorithm 1 or 2.
Right. Theorem 4 assumes we have a such that ham, Zn are in probability. We need to show that xk and vig in probability.
Let's take the center first. Xk is the sample mean of the points in the estimated cluster. Ek is the true mean of points from the true cluster sec. Why does xk converge to ak? Lemma 16, pages 34-36. handles this.
The intuition relies on the fact that almost exact recovery means ek is very similar to sec. Let A be the set of correctly classified points in the cluster and B be the set of incorrectly classified points from the other line that were wrongly put into ek. Let N, A, NB, NB, B.
So xk, 1 and xa plus nbn, xb, where xa and xb are the means of the points in A and B, respectively.
Exactly. Now, because we have almost exact recovery, the number of errors NBB is small relative to n. Since the cluster size n is roughly n2, the fraction nbn must go to 0 in probability.
Okay, the contribution from wrong points vanishes fractionally. What about xa, the mean of the correctly classified points?
A contains most of the points from the true cluster tech. By the weak law of large numbers, WLLN, the sample mean XA of these, mostly correctly classified points, should converge in probability to the true mean TK is XZ.
And XB, the mean of the few wrongly classified points.
XB is the mean of points actually from the other line. Since these points have finite variance, their sample mean XB will be stochastically bounded. It won't blow up.
So putting it together, XK 1, XA plus small fraction, bounded term.
Which means XK converges in probability to Squish. Lemma 16 formalizes this. Consistency of the sample mean holds despite the small fraction of errors.
Great. Now for the direction estimate VK, which is the leading eigenvector of the sample covariance UC calculated on NEC. We want to show VU converges to VK, the true line direction, which is the leading eigenvector of the true covariance matrix SEC.
Right. The true covariance matrix SEC for points on line cut with the direction VK looks like Cofi K plus I by 2. I is the variance along the line due to uniform sampling U along the segment. Eigenvector is perpendicular to the line due to noise Y. Its eigenvalues are 1 plus O cis eigenvector VK and Luke equals 1 eigenvector VK.
Okay. We need to show that the sample covariance U converges to phi in probability. If they are close, then Davis-Kahn applied to covariance matrices should imply their eigenvectors are close.
Exactly. Does Ook converge to Feek? We know from standard statistics that if we computed the sample covariance Clink only on the correctly labeled points, CKEK, it would converge to peak in probability, assuming finite fourth moments, which Gaussian noise has. The issue is that Ook is computed on Ik, which includes the misclassified points B.
So we need to show the difference between Ik and Sklink vanishes. That's lemma 17, pages 35-37.
Yes. Let Ik Sklink. Lemma 17 shows EKF E0 in probability. The proof involves decomposing Ook in terms of Sklink, call it SA, the sample covariance SB on the error set B, and a correction term R involving the difference in means XA, XB. It looks like Ik R plus NBN SB SA.
Similar logic as for the mean.
Very similar. R involves NA NBN, which goes to 0 because NDN goes to 0. SB and SA are stochastically bounded since they converge to true covariances. So NBN SBSA also goes to 0 in probability because NDN goes to 0, therefore EKF E0.
So Ik does converge to Sklink in probability.
Which means Ook also converges to Ek because Ik, Sklink plus X Sklink, and both terms on the right go to 0 in probability.
Now we can finish the proof of Theorem 4, pages 34-35.
We already showed XKE. For the direction Vuk leading eigenvector of Ik and VK leading eigenvector of Beck, we apply Davis-Kahan again. The sine of the angle between them is bounded by Ik Senk divided by the spectral gap of Ek.
What's the spectral gap of Ek?
It's O2 plus O2 3. This is the variance along the line segment, which is a positive constant, assuming the line has non-zero length.
Okay, so sin angle. Sinusoid is constant and Ook Firo-E in probability.
The sine of the angle, and thus the angle itself, must go to 0 in probability. The estimated direction Vuk converges to the true direction VK.
And that completes the proof of Theorem 4. Consistent estimation of line parameters follows from consistent clustering.
Yes. The whole chain of reasoning holds together.
We should probably briefly mention Appendix A, pages 38-39, concentration inequalities.
Right. This just lists some standard mathematical tools that were used throughout the proofs, like the CDF of the Rayleigh distribution, used in Lemma 4, tail bounds for chi-squared distributions, used in Lemma 2 and 3, and Chernoff bounds for sums of independent Bernoulli binomial variables, used widely in sections 6 and 7 for concentration results. These are standard tools, but essential for making the probabilistic arguments rigorous.
And the references section, pages 38-40, shows this work builds on a lot of prior research.
Absolutely. Community detection, spectral methods, hypergraph analysis, random matrix theory, geometric probability, computer vision. It connects to many threads.
Okay, let's try to summarize the whole journey we've taken through this paper.
We started with the line clustering problem, seeing why traditional graph methods based on pairs fail because any 2 points define a line. This motivated the need for higher-order interactions.
Then we saw the paper's core idea. Build a geometric hypergraph where hyperedges connect triples of points that are approximately collinear, measured by the total least squares, TLS score.
We delved into the theoretical limits of this problem in a specific Gaussian line mixture model, GLMMN. Theorem 1 established the information-theoretic thresholds. Noise must vanish faster than 1n for exact recovery, and just vanish at all for almost exact recovery.
Then came the algorithms. Algorithm 1, the spectral method, uses the TLS hypergraph structure via the similarity matrix W and its eigenvectors, combined with k-means to cluster the points. Theorem 2 showed it can achieve the IT limits, but requires knowing the right threshold T.
Algorithm 2 addressed this by introducing a data-driven way to select the threshold T based on the 25th percentile of sampled TLS scores. Theorem 3 proved this approach works, achieving the optimal, almost exact recovery rate without needing prior knowledge of the noise level.
And finally, algorithm 3 showed how to recover the line parameters, center and orientation, using sample mean and covariance of PCA on the estimated clusters, with Theorem 4 guaranteeing consistency given almost exact clustering.
And weaving through all the algorithm proofs was the careful analysis of hyperedge probabilities, P and Q, concentration of the similarity matrix W around its expectation, and perturbation theory, Davis-Kahan, to handle the noise and the dependencies inherent in the geometric hypergraph construction.
So what does this deep dive mean for you, our listener? You've now journeyed through the rigorous foundation for a modern approach to line clustering. You've seen how to move beyond pairwise interactions using hypergraphs, how to formally define and analyze the limits of recovery in the presence of noise, and how an algorithm can be designed and proven to meet those limits, even adapting to unknown parameters.
This knowledge isn't just about this one specific algorithm for lines. It provides a blueprint, a way of thinking. When faced with clustering problems, where the structure is inherently geometric or involves higher-order relationships, you can now ask, What are the fundamental statistical limits here? What kind of combinatorial structure, maybe a hypergraph, maybe something else, best captures the geometry? How do dependencies within that structure affect things? Can we build an algorithm, perhaps spectral or optimization-based, that leverages the structure? And can we prove it works, maybe even adapting to unknown noise?
And thinking about those dependencies, this paper really emphasized that the geometric constraints in line clustering introduce significant non-trivial dependencies between hyperedges, making the analysis much harder than for standard, more random hypergraph block models.
That's a really crucial point. The very geometry that makes the hypergraph useful also makes the theory challenging. But it also suggests that maybe this is the right way to model things. The dependencies aren't a nuisance to be assumed away, but are part of the essential structure.
Which leads to a final thought. What other kinds of complex data analysis problems out there involve fundamental geometric or physical constraints that induce strong dependencies between potential features or connections? Think about points constrained to lie on a manifold, particle trajectories influenced by fields, biological structures with physical interactions.
Could hypergraphs or similar higher-order structures analyzed with the kind of rigorous attention to dependency shown in this paper be the key to unlocking insights in those areas too? How do we move beyond models that assume independence towards methods that explicitly embrace and analyze the structure imposed by real-world geometry and physics?
Something for you to ponder. How can we build more geometry-aware, dependency-aware methods for understanding complex data?
A challenging but potentially very fruitful direction for future research.
Absolutely. Well, that brings us to the end of this deep dive into consistent line clustering using geometric hypergraphs. We hope you found this detailed exploration valuable.
Thanks for joining us. Until next time. Okay, let's unpack this. Imagine you're looking at a messy cloud of data chains story, maybe from a sensor or an image or some scientific experiment.
Yeah.
And buried within that mess are clear linear structures, points that should be grouped together because they all seem to lie along the same line.
Right.
This is the problem of line clustering, and it's surprisingly tricky.
It really is. Your first thought might be, great, I'll just build a graph.
Yeah.
Points are vertices, and maybe the weight of an edge between 2 points tells me how similar they are. Perhaps how well they lie on a line together.
But that approach, it immediately hits a wall, doesn't it?
It does.
Right, because any 2 points at all, they define a line. Maybe not the line you're looking for, maybe not one that fits other points well, but they do define one.
Exactly. So a simple pairwise similarity based on just lying on a line, it doesn't really distinguish points on the same underlying line from points on different underlying lines.
And you end up with this graph where everything feels connected and the real structure just gets lost in the noise.
Precisely. The problem, as this paper we're diving into defines it, is grouping points in Euclidean space so that each resulting cluster is well approximated by a line segment.
Okay.
And since those simple pairwise similarities fail to capture the, let's say, the necessary higher order structure, the fact that points have to align with multiple other points.
Right, not just one other point.
You need a different kind of mathematical tool.
And that tool, the core idea this paper explores, is the geometric hypergraph. Instead of just edges connecting pairs of points, hyperedges connect sets of 3 or more points. And that lets us encode these higher order relationships directly.
Exactly. Now, to make the problem analytically tractable, they focus on a specific kind of foundational statistical model.
Okay.
And we're going to really zero in on this model today. It's points generated by 2 latent or hidden lines in the plane with some additive Gaussian noise thrown in.
Ah, the Gaussian line mixture model, GLMMN.
That's the one, GLMMN. It's, a simplified setting for sure, but it's one that allows for really deep theoretical analysis.
So our mission in this deep dive then is to understand this GLMMN model intimately. We'll explore the fundamental limits of line clustering in this specific model, like what noise level makes recovery possible or impossible no matter what algorithm you use.
Right, the absolute boundaries.
And we'll see how the paper constructs a geometric hypergraph to tackle this, how their spectral algorithm actually works, and the theoretical guarantees they manage to prove for its performance. performance.
Including how they handle that really practical issue of, well, not knowing the noise level beforehand.
Yeah, that's key. We're going to do this by taking a really meticulous look at the paper itself. We'll be digging into the notation, the mathematical reasoning, and yes, even the derivation steps page by page to give you, hopefully, a complete picture.
Our source material is the paper Consistent Line Clustering Using Geometric Hypergraphs by Alaluusua, Konstantin Avrachenkov, B.R. Vinay Kumar, and Leskelä. It's dated June 2, 2025. We'll be working directly from this document.
Okay, so let's start right at the top, page 1. Title and authors. As you just heard, Consistent Line Clustering Using Geometric Hypergraphs. Authors, Alaluusua, Konstantin Avrachenkov, B.R. Vinay Kumar, and Leskelä.
And glancing at their affiliations here on page 1, we see they represent Aalto University in Finland, INRIA in France, and Eindhoven University of Technology in the Netherlands. So a nice mix of European research institutions involved.
And the date, June 2, 2025, places this work squarely in the recent research landscape. Pretty current stuff.
Right. So moving to the abstracts, still on page 1, the first sentence really sets the stage. Traditional data analysis often represents data as a weighted graph with pairwise similarities, but many problems do not naturally fit this framework.
Yeah, that's the starting point. We just discussed the limitations of those standard graph approaches for certain problems.
And the second sentence clearly defines the problem they're tackling. In line clustering, points in a Euclidean space must be grouped so that each cluster is well approximated by a line segment.
Right. That's the task. Find the groups of points that actually define lines.
And here's the crucial insight, sentence 3. The heart of why this problem is different. Since any two points define a line, pairwise similarities fail to capture the structure of the problem, necessitating the use of higher-order interactions modeled by geometric hypergraphs.
Okay, so this is the core motivation again, because that pairwise similarity is always high for some line between any two points.
It doesn't give you enough information. It can't distinguish points on the same underlying line from points that just happen to form a line by chance or points on different lines.
You need to look at how sets of points behave, like 3 or more points, to see if they are genuinely collinear.
Exactly. So higher order interactions means moving beyond just pairs to look at triples, maybe quadruples, and so on.
And a hypergraph is the mathematical structure that lets you draw connections between these larger sets of points, these vertices.
Precisely. And sentence 4 tells us how they build this hypergraph specifically for the line clustering problem. We encode geometry into a 3-uniform hypergraph by treating sets of 3 points as hyperedges whenever they are approximately collinear.
Okay, breakdown. Hypergraph generalizes a graph. Hyperedges can connect more than 2 vertices. 3-uniform means every hyperedge connects exactly 3 vertices.
Right, and their key idea is that a hyperedge exists between a triple of points, say I, J, and K, if those 3 points are approximately collinear, meaning they're close to lying on the same straight line.
Got it. So the hyperedges themselves encode a geometric property of the triples.
Yes, and sentence 5 connects this construction back to the goal. The resulting hypergraph contains information about the underlying line segments, which can then be extracted using community recovery algorithms.
So once you have this hypergraph where the hyperedges link these approximately collinear triples, the problem of finding the original lines becomes... what? Finding communities in the hypergraph?
Exactly. Finding densely connected groups of vertices within the hypergraph. The idea is that these communities should correspond directly to the points lying on the original line segments.
Okay, that makes sense. But then sentence 6 introduces a significant theoretical hurdle.
Right. In contrast to classical hypergraph block models, latent geometric constraints in this construction introduce significant dependencies between hyperedges, which restricts the applicability of many standard theoretical tools.
So standard hypergraph analysis often assumes hyperedges are formed independently, like flipping a coin for each potential hyperedge.
Sort of, yeah. But here, the geometric nature of the problem breaks that independence assumption completely. Think about it.
Yeah.
If points are sampled from actual lines, whether the triple 1, 2, 3 is collinear is highly dependent on whether, say, the triple 1, 2, 4 is collinear, especially if points 3 and 4 are actually on the same underlying line as points 1 and 2.
I see. If 1, 2, 3 forms a hyperedge, it makes it much more likely that 1, 2, 4 will too if they share that geometric structure.
Exactly. This creates dependencies between hyperedges that share vertices, and that makes the mathematical analysis much, much harder than for simpler sort of random hypergraph models.
That dependency is key then. It's not just any old hypergraph, it's a geometric hypergraph, and that geometry imposes structure and, crucially, dependence.
Precisely. And sentences 7 and 8 clearly state the paper's two main objectives. We aim to determine the fundamental limits of line clustering and evaluate hypergraph-based line clustering methods.
So 2 goals. First, figure out the absolute best any method could possibly do, the theoretical ceiling. And second, show how well their specific hypergraph method performs relative to that theoretical limit.
All right. Sentence 9 clarifies the theoretical part. To this end, we derive information-theoretic thresholds for exact and almost exact recovery for data generated from intersecting lines on a plane with additive Gaussian noise.
Okay, information-theoretic thresholds. That means limits based purely on the information available in the data itself, right? Like how much noise there is, how many points you have. These limits hold regardless of the specific algorithm you try to use.
Exactly. And they find these limits for two different notions of success: exact recovery,
which means getting every single point's group label exactly right,
and almost exact recovery,
where the fraction of misclassified points goes to 0 as you get more data, even if a few points are wrong.
Right. And they do this specifically for that GLMMN model, points from two intersecting lines with Gaussian noise.
And finally, sentence 10 in the abstract summarizes their main algorithmic result. We develop a polynomial-time spectral algorithm and show that it succeeds under noise conditions that match the information-theoretic bounds up to a polylogarithmic factor.
Okay, breaking that down. They propose an algorithm that's efficient. Polynomial time means its runtime scales reasonably, polynomially, with the number of points n.
And it uses spectral methods, which usually involve looking at eigenvalues and eigenvectors of some matrix derived from the data.
Yes, and crucially, its theoretical guarantee for success is very close to that fundamental limit we just talked about. It matches the information-theoretic bounds, differing only by a polylogarithmic factor.
Which is something like log n raised to some power.
Yeah, something that grows much, much slower than n itself. So it's considered nearly optimal performance in this theoretical sense.
Wow, okay. That abstract really gives us a solid roadmap. Let's turn back to page 1 and dive into section 1, the introduction, to flesh out these ideas a bit more.
Sounds good. The first paragraph basically echoes the abstract. A common approach in data analysis is to encode relational structure by constructing a graph. However, these methods fundamentally rely on the assumption that pairwise interactions can capture the structure of the data.
And they immediately bring it back to the problem. Naturally, a graph-based framework that incorporates pairwise similarity scores does not help, since every pair of points forms a line. This necessitates the use of higher-order interactions. It's that core challenge again.
Then, moving to the second paragraph, which actually extends onto page 2, they formally define the Gaussian line mixture model, the GLMMN.
Right. In this article, we study the problem of clustering data points generated by two latent lines in the plane, observed with additive Gaussian noise. Formally, our statistical model can be defined as follows. Let's break this down carefully.
Okay, so we have n points, denoted xi. Each xi is a point in R2, so just points in a 2p plane.
Got it.
Each point has a hidden community membership label, z, which is either 1 or 2, telling us which of the two underlying lines it truly belongs to.
Okay, like it's ground truth assignment.
Right. Then there's a noise level, represented by the standard deviation sus, which has to be greater than 0. And finally, there are two specific line segments, L1 and L2, residing in this 2D plane.
Okay, so we have points, their hidden labels, a noise parameter, and the actual line segments they come from. How are the observed points generated?
The data generation process for each point xi is given by the equation. Xi ui plus psi. This holds for each point I from 1 to n.
So xi is the point we actually see. Ui is what?
Yeah.
The true location.
Ui is the true noise-free location of the point on its assigned line segment.
Yeah.
And psi is the random noise that gets added to that true location.
Okay. And they specify the distributions for ui and u.
Yes, very clearly.
Yeah.
Where the point ui is selected uniformly at random from the line segment LZ. So point I is supposed to be from line 1, meaning Z1. Its true position, ui, is chosen completely randomly, uniformly, along the length of the segment L1.
Okay.
And the error term yi follows the standard normal distribution on R2. This means yi is a 2D vector where both its components are independent random variables drawn from a standard normal distribution, means 0, variance 1. This then scales this standard noise.
In independence.
Crucially, yes. And all random variables appearing on the right side above are mutually independent. All the true positions ui and all the noise vectors yi across all endpoints are independent of each other and of the labels z if the labels are also random.
Okay, that defines the generative process. How do they denote the distribution?
They define GLMN L1, L2, Z as the notation for the probability distribution of the observed data x, x1, x1, xn, given the true underlying label z. They call this the Gaussian line mixture model.
Right, conditioned on the true assignments. What if the assignments themselves are random?
Good point. They also consider that when the community memberships Z are first sampled independently and uniformly from 1, 2, we denote the probability distribution of XZ by GLMMN L1, L2.
So this is the scenario where before anything else happens, each point is just randomly assigned to line 1 or line 2 with a 50-50 chance independently for all points.
Exactly. And this is the model they primarily analyze in the paper, where both the noise and the assignments are random according to these rules.
Okay, makes sense. The third paragraph on page 2 then states the goal, right?
Yes. Our goal is to estimate the community membership vector Z and consequently the corresponding line representation based on the observed data X. Given only the noisy point C, the task is to figure out the hidden label Z for each point, and from that, figure out the properties of the lines L1 and L2 themselves.
And they explicitly link this back to the hypergraph idea again.
They do. Since each latent line inherently connects the data sampled along it, this estimation problem involves capturing higher-order geometric relationships. To do so, we represent the data as a geometric hypergraph. It reemphasizes that the linear structure itself is a higher-order relationship, not just a pairwise one.
Then they briefly introduce hypergraphs more generally, structures where edges can connect more than two vertices, and note that while they're used in various fields, the rigorous theoretical understanding is maybe still developing compared to standard graphs.
Right. And they state their contribution here is establishing the theoretical consistency, proving that it actually works under certain conditions of a specific hypergraph-based algorithm for this line clustering problem. They frame it as community detection on a hypergraph, and mention drawing on the existing literature for community recovery.
Okay. The fourth paragraph on page 2 then gives some background on prior work in community detection.
Yeah, they mentioned work on standard graphs and also on hypergraphs, including a theoretical benchmark model called the Hypergraph Stochastic Block Model, or HSBM.
And they touch on a practical challenge with hypergraphs representing them often involves tensors, which can be computationally difficult to work with.
Right. And a common workaround they mentioned is something called clique projection. The idea is if you have a hyperedge connecting, say, points I, J, K, you basically replace it with all the possible pairwise edges within that set. So you add edges I, J, I, K, and J, K to a regular graph.
So you sort of flatten the hypergraph into a standard graph, maybe a weighted one.
Exactly. Collecting the number of edges between different pairs of vertices results in a weighted matrix that is usually referred to as the similarity adjacency matrix. And then you can apply standard graph algorithms like spectral methods or STP, semi-definite programming algorithms, to this projected pairwise matrix. They also mention modularity-based clustering approaches.
But here's the crucial critique again, right? Highlighted as a limitation of prior hypergraph work when applied specifically to line clustering.
Yes. Their theoretical guarantees typically rely on independence assumptions between hyperedges,
which, as we keep saying, is violated here.
Fundamentally violated. In contrast, the line clustering problem inherently violates this assumption, as the geometric structure induces strong dependencies between hyperedges. This dependence is the core difficulty that this paper seems to really grapple with theoretically.
Okay. Paragraph 5 on page 3 mentions some prior specific hypergraph ideas for line clustering, and other recent methods like using modularity or expectation maximization, EM.
Then they take a step back to mention a classic pre-hypergraph method, the Hoe transform, which dates back to the 1970s.
Yeah, the Hoe transform. How does that work again?
The basic idea is quite clever. It maps points from the image space, like our R2 plane, to curves in a different parameter space. For lines, collinear points in the image space map to curves that all intersect at a single point in the parameter space. That intersection point's coordinates actually represent the parameters of the original line, like its slope and intercept or angle and distance from origin.
So finding collinear points becomes finding concurrent curves in this transform space.
Exactly. It's widely used in computer vision. But as they note, its limitation, especially for precise recovery or more complex shapes, is that it requires a prohibitive amount of memory to work with parametrized curves. The parameter space can get very large and complex to manage accurately.
Right, especially if you need high precision or are looking for more complex shapes than lines.
Paragraph 6 on page 3 discusses some related statistical work by Arias Castro and others. Their focus was slightly different, though.
How so?
They were more focused on the problem of detection. Like, Is there any faint geometric object, a line, a curve, a disk hidden in a noisy image? They used multi-scale scan statistics for hypothesis testing. Signal present versus signal absent.
So not necessarily recovering the object precisely or labeling which points belong to it, just detecting its presence.
Exactly. And they clarify this distinction clearly in paragraph 7. In contrast, our work addresses the distinct problem of community recovery in a structured mixture model.
Okay, so the current paper's goals are very specific.
Yeah.
I accurately assign each observation to its true line segment, and 2, consistently estimate the center and orientation of each line segment.
Right. It's the difference between detection, is there a line, versus recovery, which line is this point on, and where exactly are the lines. They see these as complementary regimes.
Got it. Now, the numbered list of their specific contributions still on page 3. Let's go through these carefully.
Number 1. We derive conditions on the model parameters that determine the statistical limits of recovery in the line clustering model under known model parameters. Exact recovery is possible if and only if, Zeta 1. Almost exact recovery is possible if and only if, Zeta 1.
Okay, these are those fundamental information-theoretic thresholds again. For perfect, exact recovery, 0 errors, the noise has to vanish extremely quickly, faster than 1 over n.
Right. But for almost exact recovery, where the error rate goes to 0, the noise just has to vanish eventually, say 1 is enough. And these limits hold even in the oracle case, where you magically know the true lines beforehand.
Okay. Contribution 2. We introduce a geometric hypergraph representation based on total least squares, TLS residuals, over all triples, capturing latent collinearity.
This is their specific construction method. They form hyperedges based on triples of points being approximately collinear, and they use the total least squares score as the quantitative measure of that collinearity. We'll need to define TLS properly soon.
Right. Contribution 3. We propose a polynomial-time spectral algorithm based on the geometric hypergraph, requiring no prior knowledge of the underlying line structure.
So the algorithm is efficient, polynomial time, and importantly, it doesn't need you to guess where the lines are ahead of time. It works directly from the point data.
And what about its performance?
That's the next part. If a threshold for forming hypergraphs is chosen so that solg n at, n log n ordinary, the method achieves exact recovery, matching the information-theoretic threshold up to a polylogarithmic factor.
Wow, okay. So if you can pick the hyperedge threshold t within this specific, somewhat tight range, which depends on both the noise and the number of points n, then their algorithm achieves exact recovery and does so almost optimally, matching the Solman limit up to those log factors.
Precisely. But then they address the practical issue of choosing t.
Because you usually don't know. Right.
Yeah, exactly. Moreover, we provide a data-driven rule that selects the empirical distribution of the TLS residual. This requires no prior knowledge and guarantees almost exact recovery when this sweep.
Okay, this is big. They have a version of the algorithm that figures out a good threshold just by looking at the data itself without needing you to know the noise level. And this data-driven version still achieves the theoretically optimal limit for almost exact recovery, working whenever necessary.
Yeah, that's a very significant practical contribution.
And the concluding sentence just summarizes the broader impact. This work shows how to encode geometry in hypergraphs, highlights the theoretical impact of that hyperedge dependence, and offers insights for geometry-aware community recovery in other areas too.
Okay, before we dive into the algorithms and the core theory, let's quickly check Remark 1 on page 4 for the notation they use. Getting this clear now will be crucial later.
Good idea. We use bold letters to denote vectors and matrices. Pretty standard.
Now, the asymptotic notation for sequences depending on n, the number of points. For two sequences, an n or 1 and bn il1, the notation in NEBN means that lim na and bn equals 0.
Okay, so NAEBN means an becomes negligible compared to bn. As n gets really large, the ratio goes to 0.
Right, and conversely, an and bn means that lim na and bn 0.
Meaning the ratio a and bn does not go to 0. It might go to a positive constant or even infinity, but an is not negligible compared to bn for large n.
Exactly. And the third one, we use the notation now to denote inequalities up to multiplicative constants. Specifically, NABN means that there exists a constant C0 such that an NACBN for all sufficiently large n.
So an is less than or equal to some constant times bn. For large enough n, it means n grows no faster than bn, ignoring constant factors.
Precisely. These notations are absolutely vital for understanding the precise statements of the theorems and lemmas about how things behave as n grows large.
Okay, notation nailed down. Let's move to section 2 on page 4. Information-theoretic bounds. This section asks the fundamental question. What are the absolute limits on recovery, based purely on the data's properties, regardless of algorithm?
Right. Our task is to estimate the community membership vector Z based on the observed data X when the pair is sampled from the Gaussian line mixture model.
And first, they need to rigorously define what recovery means. Definition 1 on page 4, exact and almost exact recovery.
Okay. Let's be the vector of true labels, C is 1 or 2, and D be the vector of estimated labels from some algorithm.
Uh-huh.
They define the permutation invariant Hamming distance, also called the absolute classification error, min pair Z and A11.
Okay, let's unpack that. S2 is the set of permutations of the labels 1, 2, so it's just the identity 1, 1, 2, 2, and the swap 1 to 2, 2, 1.
Right. The summation bods counts the number of points I where the estimated label is different from the true labels I after applying a potential swap to the true labels.
Ah, so you calculate the number of mismatches, assuming your estimated label 1 corresponds to the true label 1. And D, you calculate the number of mismatches, assuming your estimated 1 corresponds to the true 2. And Ham is the minimum of those two counts.
Exactly. It accounts for the fact that the algorithm might just get the labels swapped overall, which shouldn't count as N errors. It's the minimum number of actual misclassifications.
Okay, that makes sense. So based on this Ham error count,
They define the two levels of success. 1. Exact recovery if lim NE 0, 1.
the probability of getting 0 misclassified points after checking for swaps must go to 1 as the number of points N gets arbitrarily large. Perfect accuracy.
Right, the strongest condition. 2. Almost exact recovery if for every 0 NEZE, in close, 1 had.
Okay, here we look at the fraction of misclassified points, Ham. Almost exact recovery means that the probability that this fraction is less than any tiny positive number goes to 1 as N gets large.
So the error rate must go to 0. The total number of errors, Ham, might still grow with N, maybe like log N or something, but as a fraction of N, it becomes negligible.
Okay, clear definitions. Now, Theorem 1 on page 4 gives the thresholds for these, specifically in that oracle setting where the equations of the two line segments are known.
Right. This is a crucial theoretical benchmark. If you know exactly where L1 and L2 are, then for each observed point xi, figuring out its label Z just becomes a standard statistical hypothesis test.
Well, like calculating the probability density of xi, assuming it came from L1 with noise, calculating it assuming it came from L2 with noise, and picking the line that gives the higher probability.
Exactly. It reduces to a sequence of n independent Gaussian hypothesis tests.
And why is this oracle setting important?
Because since this same ratio forms a lower bound for the unknown line problem, any algorithm that matches it in the oracle case also achieves the information-theoretic threshold when the lines must be estimated. In other words, the oracle case represents the easiest possible version of the problem. If recovery requires certain conditions, like a certain noise level, even in this easiest case, then those conditions must be fundamental limits that apply to any algorithm, including those that have to estimate the lines too.
Makes sense. If you can't do it even when you know the lines, you definitely can't do it when you don't. So what are the conditions and results of Theorem 1?
Conditions. Lines L1, L2 have equal length, intersect at their midpoint. The data, Zx, comes from the GLMN L1, L2 plus N model. Noise levels N might depend on N. And crucially, the model parameters, lines L1, L2, noise N, are known to the estimator.
Okay. And the results?
Two key results. 1. Exact recovery is possible if and only if sun, year, and O. Perfect recovery requires noise tend to vanish faster than 1N. 2. Almost exact recovery is possible if and only if sen, air 1. Getting the error rate to 0 just requires the noise N to vanish as N increases.
If and only if that's strong. It means these are necessary and sufficient conditions in the oracle setting.
Yes. And they add, in each case, the maximum likelihood estimator achieves these results. The MLE, which makes the optimal per-point decision when lines are known, actually hits these limits, proving they are achievable.
And if the stated conditions are not met, no method can achieve recovery, proving they are indeed necessary limits.
Right. The discussion below the theorem notes that these thresholds are actually angle invariant for any fixed angle between the lines, as long as it's not 0 or. The difficulty depends primarily on the point density and noise, not the specific angle.
But they mentioned they focus on the right angle case for the algorithmic analysis later.
Yes, likely because the perpendicular case often leads to simpler algebraic calculations when analyzing the algorithm's performance. But the fundamental information-theoretic limits derived here hold regardless of the angle.
Okay, great. So Theorem 1 sets the fundamental benchmarks. Now, to understand why these thresholds hold, we need to look at the analysis. Let's jump ahead to section 4 on page 7, which provides the details behind Theorem 1.
Right. The first paragraph on page 7 explains how estimating the community for a single node xi boils down to a hypothesis test. The task of estimating the community of a single node xi reduces to a hypothesis testing problem, where the node could be from either of the two distributions, f1 and f2, where Fl is the probability distribution of a point generated from line k.
And they invoke a classic result. By the Neyman-Pearson lemma, the optimal test for such a hypothesis testing problem is the maximum likelihood estimate, MLE.
Right. The MLE is statistically the best way to decide which of two known probability distributions generated a given data point.
How is the density fkx defined? That's the probability density of observing point x, given it came from line k.
Yes, the formula is given just below that. Fkx is kx, 1 by 1 u1 du2. Let's break that down.
Okay. Ft is the standard 1D Gaussian probability density function. So by 1 u1 by 2 u2 looks like a 2D Gaussian density centered at u1 u2 scaled by Clay and evaluated at the observed point x by 1 by 2.
Exactly. It's the probability density of observing x if the true point was u and the noise was y. The integral akx, gku, then averages this probability over all possible true locations, u along the line segment lk, where g is the uniform probability measure on lk.
So fkx gives the overall likelihood of observing x if it came from line k, considering all possible starting points on the line segment and the Gaussian noise.
Precisely. And the MLE for a specific observed point g is then simply argmax to fkx. You calculate f1 and f2x and assign g to the line k that gives the larger value.
The decision rule is just assign to community 1 if f1 xi, f2 xi, otherwise assign to community 2. Ties happen with probability 0, they know.
Right. Now, paragraph 2 on page 8 defines the error probability per. The error probability for the MLE per is the probability, under a uniform prior, that an observation is incorrectly assigned to the wrong community. We call this the expected misclassification rate.
So if a point truly comes from line 1, what's the probability the MLE assigns it to line 2, and vice versa, averaged?
Yes, assuming a point is equally likely to come from line 1 or line 2 a priori, it turns out this is directly related to the total variation distance between the two distributions f1 and f2.
Ah, DTV. The formula is per 12, 1, 1, f2, called DTV f1, f2, superior f1a, where the supremum is over all possible regions A and R2. It measures how distinguishable f1 and f2 are.
Right. If DTV is 1, distributions are perfectly distinguishable. Per is 0. If DTV is 0, distributions are identical. Per is 12. Just guessing.
They also give another view. Per can be seen as f1ac or f2a, where A is the region in R2 where f1x, f2x.
Exactly. Per is the probability that a point drawn from f1 happens to land in the region A, where f2 is deemed more likely, or equivalently, the probability a point from f2 lands in A, where f1 is deemed more likely.
Okay, now lemma 1 on page 8 gives the actual formula and, more importantly, the asymptotic behavior of this per.
Right. Lemma 1, given two line segments of length, so 0, that intersect at their common midpoint at an angle, before 2 and let 0. Then the expected misclassification rate per is given by per p y1 or do 0, where 1 coarsin, where to 2 and a is the complementary CDF of the standard normal distribution.
Okay, that integral looks complex. It involves integrating over the possible true positions u along the line segment from act to 2. The terms inside p seem to involve the Gaussian noise components y1, y2 compared to thresholds that depend on u, the angle 1, and the noise level.
Yes, it captures the geometry. y1 and y2 would be noise components relative to the decision boundary between the two lines. The integral sums up the probability of noise pushing the point across the boundary, averaged over all starting positions in it, and they note per 0. So for any positive noise, there's always some chance of error.
But the crucial part is the limit as goes to 0, right?
Exactly. Moreover, as 0 lim per 1 plus cots.
So for very small noise, the error probability per point per is approximately proportional to sus. The constant of proportionality depends on the segment length and the angle via 0, 0.
This linear dependence on for small is the key takeaway for the proof of Theorem 1.
Okay, let's briefly walk through the proof sketch of lemma 1 on pages 8-10 to see where this limit comes from. It seems quite involved mathematically.
It is. They start by setting up the geometry conveniently, W, L, O, G. without loss of generality. They align the lines symmetrically with respect to the coordinate axis intersecting at the origin. Line 1 might be parameterized as u cos pachu seno, and line 2 as u cos pachu sen for in seno 2 od.
Where it has is half the angle between the lines, FO2.
Yeah. They identify the region as where f2x, f1x, or equivalently, where a point from line 1 would be misclassified. In this symmetric setup, AS turns out to be the union of the first and third quadrants, where by 1, by 2 over figure 2 illustrates this.
Okay, so per is the probability that a point generated from line 1, say x xl u plus y, where u is on L1, lands in x.
Right. They express this probability using the components. If u cos pachu seno, then x equals is on L0 so 1 plus y1 is sin plus y2. For x to be an AS, we need both components to be positive, OR, both to be negative. Due to symmetry, they calculate twice the probability of landing in the first quadrant. Per u cos pix 2 phi cos plus y1 at 0, u sino plus y5 feel.
Which simplifies to 2 pass y1 u or sin, where u is uniform on u at 2 and y1, y2 are independent standard Gaussians.
Yes. Then they write this probability as an integral over the density of u, which is 1 arrow on e or 2, 2. This gives the integral formula to involving the complementary CDF x p arrow x for a standard normal z.
Okay, so that establishes the integral formula too. Now, how do they get the limit as euro?
They perform a change of variables in the integral.
Yeah.
This makes the integration variable dimensionless. The differential d becomes u. The integration limits change from euro 2 for u to 2 for u.
Ah, and as u, the limits go to infinity.
Exactly. The integral expression for pair becomes, after some manipulation using symmetry and area ODX, something like 2 or 2 far plus u or sin replaces the upper limit, our root.
Correct. So limsar per involves evaluating uo of those three terms.
How do they evaluate it too? They use a neat trick involving changing the order of integration. Write e's-do, so the integral becomes yizu dd. They swap the order to yizu ddd. The integral ed is just za.
Ah, so it becomes EZDDZ, 1ZBZ, 1AZDZD.
And that integral dz is a standard Gaussian-related integral that evaluates to 1.
So EZD gives 1 a th.
Yes. Applying this, the first term, EZDDC, gives 1, EZ2. The second term, EZDD, gives 1, CDDD.
Okay, 2 down. What about the third term, MEDS2DD, CDD?
That one is more involved. Again, they write out the E functions as integrals, say involving variables, ED, DD becomes a triple integral, EZ, where the inner part is related to EU plus V. And the integration region involves GSCDDDDP, OPD2. They change the order of integration to integrate over Y first. The Y integral gives min U cos, V in 12, so they are left with a double integral over U and V from 0 to EO plus the U plus V2 min U cos axi.
Okay. How do they tackle that?
Polar coordinates. Let U r cos A, V to R cinder. The integral becomes an integral over R from 0 to cinder to 2. The term EU plus V2 becomes ER2. The Jacobian is R. The min term becomes min U cos sin quas there R sin deve.
So it separates into a radial integral and an angular integral.
Yes. The radial part involves ERO ER2. Dr. Singvaret is evaluates to cos.
Okay, and the angular part?
It's EUM tos EO cos sen de. This integral has to be split at EO because which term in the minimum is smaller changes there.
For ARO, sin is smaller. For ARO, cos is smaller.
Right, so they integrate sin to sin from 0 to bear and cos be from L to 2.
Sin day is icos. Icos is sin day evaluating these gives. 1 cos sin day for the first part and 1 sin day for the second part.
Exactly. So the angular integral evaluates to 1 cos sin fargard plus 1 sin fargard.
Now we combine everything to the third term. It had a prefactor of -212 radial integral result.
Right. -212 angular integral result, 1 Walgo sen vargari plus 1 sin fargas sen.
Okay, finally. Now combine the results for the three terms in lim for per, all scaled by the 12 one factor from the setup.
Actually, the limit expression was for 12 integral 1 plus integral 2 integral 3. We need to combine the limits we found, scale by 1r.
Let's recheck the limit factors. One where the third term limit was -1 for angular sum.
The overall limit was 1 for causi. The one factor came from the density in the integral. So lim for per plus 1 sim for angular sum per cos quarterly. Wait, the third term was mongos to unvergari. Let's reevaluate that coefficient.
-2. 12 ava. Du via no, we integrated one there first.
Yeah.
-2 dv fuller. -2 quover. Angular radial, Dr. Doe. Radial was near so 2, so coefficient is -2, 12 2 to 2.
Okay, yes. So lim means per 1 neaso plus 1 sins plus 1 sin bay trip -1 sin.
Let's simplify the term in brackets, pulling out one sin. We get 1 to posto plus 1 sin boxo sin bo sinsopi.
Grouping terms. 1 sinbos plus sinbos post plus seco.
Which is tan plus katso. Okay, we got there.
So limbos post 1 tanbos plus koso, matching the lemma statement. The derivation shows per is indeed proportional to san sumil.
Phew. Okay, remark 3 on page 10 just notes that the key quantity driving these results is the signal-to-noise ratio, which is effectively related to TU. Letting vanish with fixed A is equivalent to letting U grow with fixed A as long as LA.
Right. Now back to page 11 for the proof of theorem 1 using this lemma 1 result, per os const.
Okay, first, the necessary condition for exact recovery, MLSI.
We know the error probability for a single point is per a's constant. For n independent points, the probability of making at least one error is roughly bounded by n per, using a union bound or 1 per n for small per.
Okay. The condition for exact recovery and possibility is so NO. This means sun does not go to 0.
So n per n's constant 1 plus 1. Since nus does not go to 0, n per also does not go to 0.
If the probability of making at least one error does not go to 0, then the probability of making 0 errors cannot go to 1.
Exactly. So exact recovery is impossible if so and no. And since the MLE is the optimal classifier here, if MLE fails, any algorithm must fail. This condition is necessary.
Now, the sufficient condition for exact recovery, if so, NO.
This means NO1, so n per n constant 1 plus 01 goes to 0.
The probability of at least one error goes to 0. Therefore, the probability of 0 errors must go to 1.
Right. MLE succeeds with high probability, so exact recovery is possible under this condition.
Okay, that covers exact recovery. Now for almost exact recovery, Hammond, 0WHP. First, the necessary condition.
Suppose almost exact recovery is impossible. That requires seno. If does not vanish, example approaches a positive constant or sen is constant, then per approaches some positive constant C0 using the limit from lemma 1.
Let B be the total number of errors, ham in this case since labels are 1, 2.
Yeah.
B, E0 is per, where B is 1 if point I is misclassified, 0 otherwise. The expected number of errors is EB equals N per.
The expected fraction of errors is EBN per. If pose bounded below by C0, then EBN to C.
How does this show impossibility? They use Markov's inequality.
Yes, PBN or EBN per is per. This gives an upper bound, but we need to show the probability is bounded away from 0.
Maybe think about the probability of success. Let's reconsider. If T1 per converges to some C0, EBN per makes C. Can we use law of large numbers? PN should converge to EBN equals C.
Yes, by the weak law of large numbers, since B are independent Bernoullis, BN converges in probability to per. If per converges to C0, then BN converges in probability to C.
This means for any small error, PBN C. If we choose IC2, then PBN SC to 0, the fraction of errors is very likely to be close to C, not close to 0.
Exactly. So PBN S does not go to 1 for small, like thing. Therefore, almost exact recovery is impossible if day 1.
Okay, that works. Now, the sufficient condition for almost exact recovery if SI1.
If is 1, then by lemma 1 per Mia 0.
By Markov's inequality, PBN is ABN befound since per euro for any fixed OR, this upper bound pairs goes to 0.
So PBN 0, this is equivalent to PBN 01. Wait, the definition was PBN 1. Is V is important here?
Since BN is discrete, it doesn't really matter for the limit. PBN 0 implies PBN 01. If we need O, PBN at A, since PBN O, that also goes to 0. So yes, PBN 01.
Okay, so the fraction of misclassified nodes goes to 0 in probability. This is precisely the definition of almost exact recovery. And that completes the proof of Theorem 1. It rigorously establishes these fundamental limits based on the noise level relative to n. Exact recovery needs so n. Almost exact needs so 1 in the oracle case.
Great. Now let's move to section 3 on page 5, which introduces the algorithms designed to work without knowing the lines and aims to approach these limits.
Right. In this section, we introduce a polynomial-time algorithm that achieves exact recovery up to a polylogarithmic factor of the information-theoretic threshold, and almost exact recovery up to the threshold.
The core component is using the total least squares, TLS score, to quantify collinearity for triples. Page 5 gives the definition.
Given 3 points x1, x2, x3, r2, we seek to estimate a line L that best fits the points by minimizing the sum of squared orthogonal distances between G and L. This is referred to as the total least squares TLS problem.
The score is denoted so TLS x1, x2, x3, mil I10, 3 to so O1. Here, L is the set of all lines in R2, and DLN is the shortest perpendicular distance from point G to line L.
So you find the single line L that minimizes the sum of squared perpendicular distances from the 3 points to that line. The minimum value achieved is the TLS score, so that's TLS. A small score means the points are collectively close to lying on some single line.
And this score is used to build the hypergraph.
Yes. In particular, given endpoints J are 2, the corresponding TLS hypergraph H with threshold parameter T0 is the three-way hypergraph, where I, J, J, E, H for each I, J, K, and choose 3 if and only if TLS, J, XJ, SK2.
Okay, so you consider every possible triple of points I, J, J, aka. You calculate their TLS score. If that score is less than some threshold value 2, you add a hyperedge connecting I, J, and K to your hypergraph A.
Exactly. Figure 1 on page 5 gives a nice visual. A triple that's nearly collinear gets a blue hyperedge because its TLS score is below 2A, while a triple forming a clear triangle gets rejected, red, because its TLS score is above 2A.
So the threshold T determines how strictly collinear a triple needs to be to form a hyperedge.
Precisely. Now, algorithm 1, the basic spectral method, is described on page 6. Let's walk through the steps.
Okay, step 1. Input is the set of points x1.xn and the threshold parameter T0. The output should be the estimated membership vector.
Step 2. Construct the TLS hypergraph H using this threshold T, as we just defined. Find all triples I, J, K with SOT TLS2 and add them as hyperedges.
Step 3. Construct a similarity matrix W. This is an NXN matrix. How are its entries we defined?
We E I J 1 E E A day. It's the sum over all hyperedges E in the hypergraph H. The condition EEIJ means the sum is only over hyperedges E that contain both vertex I and vertex J. The term 1EEH is just 1 since we sum over edges in H. So we simply counts the number of hyperedges that are incident to both node I and node J.
Ah, okay. So if points I and J are on the same true line, they'll likely be part of many collinear triples I, J with other points K on that same line. Each such triple forms a hyperedge containing both I and J, contributing 1 to E.
Exactly. Whereas if I and J are on different lines, they're less likely to form collinear triples with a third point K, so we would be expected to be smaller. This matrix W is designed to capture pairwise similarity using the higher order hyperedge information.
Makes sense. Step 4. Compute the leading eigenvectors. Let U, RNA2, be the matrix whose columns are V1, V2, where V1 and V2 are the eigenvectors of W, corresponding to the two largest eigenvalues, 1, 1, V2, corresponding to the largest two eigenvalues. Stack these two column vectors in descending order and take the two eigenvectors, V1, V2, corresponding to the largest two eigenvalues. Stack these two column vectors side by side to form the n by 2 matrix U.
Why the top two?
The intuition, which comes from spectral graph theory, and which they'll prove later, is that for a matrix constructed this way from data with two underlying communities, the community structure is primarily encoded in the subspace spanned by the top two eigenvectors.
Okay, so each row of U gives a 2D representation of the original data points. Yes. Row I of U, let's call it U row, is a vector in R2. The idea is that if points I and J were in the same original community, on the same line, their corresponding rows, U row and U row, should be close together in this 2D eigenvector space.
Which leads to the final step, step 5. Assign labels 1, 2 for each I, 1, and using k-means clustering with k2 on the rows of U.
Right. You treat the n rows of U as n points in a 2D space and apply the standard k-means algorithm to partition them into two clusters, k2. The cluster assignment k-means gives to row I becomes the estimated community label I for the original data point J.
Okay, so the overall process is find collinear triples I, build similarity matrix, find top two eigenvectors mono k-means on eigenvector rows. Seems plausible. Now, what are the guarantees? Theorem 2 on page 6.
Theorem 2 gives the performance guarantees for this algorithm 1. Conditions are lines L1, L2 are perpendicular, equal length, intersect at midpoint, the algebraically simpler case. Data comes from GLMN, L1, L2 on. A threshold Tn is used.
And the results? Two parts again.
A, if Sunye Tn A1, algorithm 1 achieves almost exact recovery.
Yeah.
So if the noise as is small, goes to 0, and you choose the threshold Tn to be larger than the noise but also small, also goes to 0 but slower than Sun, then the algorithm achieves almost exact recovery. Error goes to 0.
Okay, and part B.
If Sun lug the Tnn, algorithm 1 achieves exact recovery. For perfect recovery, 0 errors. The condition is tighter. Noise n needs to be even smaller relative to n, and the threshold Tn must fall within this specific narrower range, which also vanishes quite quickly as n increases, like 1m.
Comparing this to the I-key bounds, Sun1 for almost exacts in Tn and A, it looks like the almost exact recovery condition matches perfectly.
Yes, provided you can choose some Tn such that Sun A and A1.
And the exact recovery condition, on log n and on log n, implies on log n must be roughly an unknown. The IT bound was unknown and no. So the algorithm achieves exact recovery under slightly stricter conditions than the absolute theoretical limit. It loses that log n factor.
And also, the threshold Tn needs to be chosen very carefully within a range like n. This matches the IT threshold up to polylogarithmic factors, log n terms, so it's considered near optimal.
But the discussion below highlights the practical catch again.
Right. A key limitation of the algorithm is that the optimal choice of Tn depends on sen. Both conditions, A and B, require setting Tn relative to the unknown noise in un. If you don't know un, how do you choose Tn to fall in the right range?
If you did know sun, they note you could select Tn appropriately to get exact recovery when in lun, doing the algebra to find where the ranges overlap, which matches the IT threshold unlong up to log factors.
And importantly, the condition for almost exact recovery just requires finding some Tn between sun and 1. This seems more achievable even without knowing Kanaan precisely, which motivates the next algorithm.
Right. Algorithm 2 on page 6, spectral method with data-driven threshold selection. This is designed specifically to overcome the need to know beforehand.
Exactly. In algorithm 2, the threshold selection is based on counting observed triples in the TLS hypergraph. It tries to learn a good threshold directly from the data.
What's the core idea? How does it work?
It cleverly exploits the expected structure. Remember, in the GLM-MMM model, with uniform random labels, the probability that a randomly chosen triple IJ comes entirely from the same community. Alls is 14.
Why 14?
2 communities. Probability all 3 are from community 1 is 12,
Like
18. Probability all 3 are from community 2 is also 18. So total probability is 18 plus 18 was 14.
Okay, 14 chance a random triple is within community.
Right. The algorithm hypothesizes that within community triples will generally have low TLS scores, while between community triples, with points from both lines, will have high TLS scores. So it tries to find a threshold T such that roughly 14 of a sample of triples have a TLS score below T.
It uses the expected fraction of within community triples, 14, as a target quantile for the TLS scores. The threshold T corresponding to the 25th percentile of observed TLS scores should hopefully be a good separator.
That's the intuition. Let's look at the steps.
1. Input. Points x1 off xn, m, the number of triples to sample, and a target fraction, which they suggest setting to 14. Output is the estimated label so.
2. Sample M triples. Independently and uniformly at random with replacement from all possible. Choose 3 triples.
3. Let M be the set of all nodes that appear in any of these sampled triples. Let MC and M be the set of all other nodes, those not involved in the sampling. They'll do the main clustering on McKee.
Compute the TLS score psi for each sampled triple P. Sort these M scores S1, S2.
5. Threshold selection. Calculate the target index K, rounded to the nearest integer. Set the chosen threshold T, SK, or S1 if K1, just to be safe. So T is the TLS score at the K-auth position in the sorted list, where K corresponds to the target fraction, e.g. the 25th percentile if fifth 14.
6. Now run algorithm 1, the spectral method, but only on the subset of no's in McKinley, those not used for threshold selection, and use the data-driven threshold T found in step 5. This gives estimated labels I for all in Achille.
What about the nodes in M that were part of the sampled triples?
Step 7. Optional on the paper, but needed for full labeling. Assign labels A for IM uniformly at random. The analysis assumes this doesn't significantly affect the overall error rate if M is small compared to N.
Okay, so it samples to find T, then clusters the rest using T. What's the guarantee for this? Theorem 3 on page 7.
Theorem 3 states, assume L1, L2 are perpendicular lines of equal length intersecting at their midpoint. Let the pair ZX be samples from GLMMN, L1, L2. If SANI L1 algorithm 2 with parameters 1 AM, NN, and MNM14 achieves almost exact recovery.
This is the key practical result then. Algorithm 2 achieves the information-theoretic threshold for almost exact recovery without needing prior knowledge of the noise N or other model parameters. It learns the threshold successfully from the data itself.
Exactly. The condition 1 MN ensures that the sampling phase is computationally efficient. M is much smaller than N, and that the set M of nodes involved in sampling is also small, relative to n at most 3m nodes. So excluding them or assigning them randomly doesn't spoil the almost exact recovery guarantee for the whole dataset.
What about the complexity? Remark 2 on page 7.
Threshold selection involves m triples. Calculating TLS for m triples takes OM time, since each TLS on 3 points is O1. Sorting the m scores takes OM log m. If mn, this is negligible compared to the clustering part.
And the clustering part is algorithm 1 run on my K, which has about n nodes.
Right. The bottleneck there is constructing the hypergraph, checking sut TLS for all ON triples on next C, which takes ON time, and constructing the similarity matrix W, also ON, adding contributions for each hyperedge. Computing the top 2 eigenvectors of the NXN matrix W can also be done in ON time using iterative methods. K-means on the NOs of U is relatively fast, maybe ON logs in using approximations.
So the overall complexity is dominated by ON.
Yes, it's polynomial time, which is good theoretically, but N can still be quite computationally expensive for very large data sets.
Okay, so we have algorithms to cluster the points. What about finding the lines themselves? That's the second goal. Section 8, pages 34 to 37 covers this, with algorithm 3 on page 8 for line recovery.
Right. Once you have the estimated labels from algorithm 1 or 2, you want to estimate the actual line segments L1 and L2.
Algorithm 3 steps. 1. Input. Points x1 on xn and the estimated labels OM. Output. For each estimated cluster, find a center xk and a direction vector vector.
How? First, calculate the sample mean center for each cluster. xk is the size of cluster k.
Okay, average of points in the cluster.
Then, calculate the sample covariance matrix for each cluster. This is a 2x2 matrix capturing the variance and covariance of the points within cluster k around their sample mean xk.
Got it. Sample mean and sample covariance for each estimated cluster. Then what?
Step 2. Obtain VUC, which is defined as a leading eigenvector of the sample covariance matrix Euc.
Why the leading eigenvector?
The intuition is that for points clustered around a line, the direction of maximum variance will be along the line itself. The leading eigenvector of the covariance matrix points in the direction of maximum variance. So VUC should estimate the direction of the underlying line segment, LK.
Okay, that makes sense. Sample mean estimates the center. Leading eigenvector of covariance estimates the direction. Does this work theoretically? Theorem 4 on page 8 gives the guarantee.
Yes. Theorem 4 states, consider arbitrary line segments L1, L2 doesn't require perpendicular equal length here. Let the pair Z, X be sampled from GLMM and L1, L2 come with set A1. Suppose that an estimator like ALG1 or 2 achieves almost exact recovery. Denote K, AGZA, the true mean of points from line K, and let VK be a vector aligned with LK. Then for every AZ, we have sin and X, with high probability as NAE.
Wow, so if you can cluster the points mostly correctly, achieve almost exact recovery, which algorithm 2 does when Vroon 1, then this simple procedure of calculating sample mean and leading eigenvector gives you estimates of the true line center and true line direction VK that get arbitrarily accurate as n increases.
Exactly. With high probability means the probability that the error in angle sign or center distance is less than e goes to 1 as NE. So algorithm 3 provides consistent estimation of the line parameters, provided the clustering was successful. Sin angle implies the angle itself goes to 0.
That's a really nice closing result. It connects the clustering success to the success in estimating the geometric objects themselves.
It does. So we have the full pipeline, use hypergraphs, built from TLS on triples, and spectral methods, possibly with data-driven threshold, to cluster the points. Then use basic statistics, covariance, eigenvector, on the clusters to find the lines.
Now, to really understand why these algorithms work and formally prove theorems 2, 3, and 4, we need to dive into the deeper analysis sections. This seems to involve understanding the probabilities P and Q, section 5, analyzing the spectral properties of W, section 6, and understanding how statistics behave on the estimated clusters, part of section 8 proofs.
Precisely. Let's go back to section 5 on page 12. Bounds on hyperedge probabilities. This is critical for understanding the structure of the hypergraph H and the resulting similarity matrix W.
Right. They define P and Q. Let's restate them.
This is the probability that a triple drawn entirely from one line, a within-community triple, gets accepted as a hyperedge. Its TLS score is below 2 bench. I want pick to be close to 1.
And Q, P or Z equals. This is the probability that a triple involving points from different lines, a between-community triple, gets accepted as a hyperedge. We want Q to be close to 0.
The goal of this section is to derive bounds on 1P, the probability of rejecting a good triple, and Q, the probability of accepting a bad triple, to show that we can indeed choose a threshold T that separates them well. Makes P high and Q low.
Section 5.1 on page 12 looks at the within community link probability, aiming to bound 1p.
How do they analyze this?
They consider a triple A xj xk where z's k1 wlog. They can assume the true line L1 is the x-axis. So the true points UA, UE, EK are on the x-axis. The observed points are G, UA plus psi, etc., where Y are Eden 2D standard Gaussian noise vectors.
Okay.
They decompose the noise, see it into components parallel and perpendicular to the true line, the x-axis. The key insight is that the TLS score, which measures deviation from the best fit line, is primarily influenced by the perpendicular noise components, UA.
What's the distribution of that perpendicular noise component?
Since the 2D Gaussian noise Y is isotropic, same variance in all directions, the perpendicular component UE, which is just the Y component if the line is the x-axis, is a standard 1D Gaussian. Its magnitude UE follows a half-normal distribution.
Okay. So lemma 2 on page 12 gives an upper bound for 1p.
Yes. Lemma 2. Let P be defined as in 3. For any 2D, we have 3 with 1 year log 3.
Let's unpack that bound. It shows that if the threshold is larger than the noise, specifically 3, which means F1, then the probability of rejecting a true within community triple 1p decays exponentially fast as the ratio increases.
Right. The larger it is compared to beyond 3, the smaller 1p becomes very rapidly.
How do they prove this? The sketch seems to rely on bound in the TLS score.
Yes. The true TLS score CLSX is the minimum sum of squared distances to any line. This must be less than or equal to the sum of squared distances to the true line L1, the x-axis.
And the distance from an observed point xi UE plus psi to the true line L1 x-axis is just the magnitude of the perpendicular noise component CO or SY2 if L1 is the xi.
Exactly. So SOT CLS xi xj xk plus y2 v2 plus SOT yk2 v1.
Ah, okay. So the probability of rejection is P TLS CO, which is less than or equal to P.
Which simplifies to P y2 oo.
And Y2, YT2, YQ2 are independent standard normal variables. So the sum of their squares follows a t-squared distribution.
Yes, a chi-squared distribution with k 3 degrees of freedom, sum of squares of 3 independent standard normals.
So they just need a tail bound for the chi-squared distribution.
Precisely. They apply a known tail bound, inequality 58 in Appendix A, for the upper tail of a chi-square distribution. That bound involves the term threshold, degrees of freedom variance per term.
Yeah.
The bound has the form xp2 duxmol for sp231, which matches the lemma statement with k3.
And the condition 2-3 ensures that bill trees is indeed greater than 1, so the bound applies.
Exactly. So the conclusion is, within community triples are very likely to be accepted, 1p is small, if the threshold is significantly larger than the noise standard deviation.
Okay, that handles the good triples. Now, section 5.2, between community link probability, pages 13 and 19. This is about bounding Q, the probability of falsely accepting a bad triple involving points from different lines. This looks much more involved.
It is, considerably. They primarily analyze the case of a 2-5-1 split 2 points from L1, 1 point from L2. Again, for simplicity, they assume L1 is the x-axis, L2 is the y-axis, perpendicular intersecting at origin, though the results are intended to hold more generally for the 2-3-1 regime.
Okay, so we have x1 equal u1 plus y1, x2 equals u2 plus v2 with u1, u2 on x-axis, and x3 with 3 plus y3 with u3 on y-axis. We want to bound Q, pull TLS, x1, x2, x3.
They use a geometric containment strategy. Recall means there exists some line L such that DE she A LS2. This implies that for this line L, the distance DE she L must be less than T for each individual I1, 2, 3.
Okay.
Geometrically, this means the line L must intersect the open disk BE she LA centered at J with radius T for all I1, 2, 3.
Right.
Now, they relate this to the true locations UI. Using the triangle inequality, the distance from the true location UI to the line L, DUIL, is bounded. DUIL plus DEI plus DUIL plus SU. Since DUIL2, we have DUILT plus Y. Let Ri2 plus Y be a random radius depending on the noise for point I.
So if the line L passes within distance T of G, it must also pass within distance D of the true location UI.
Yes. Therefore, the event is contained within the event such that L intersects the disk for all I1, 2, 3. Let's call these disks B1, B2, B3, centered at U1, U2, U3 with random radii R1, R2, R3.
Okay, so bounding Q becomes bounding the probability that there exists a line intersecting these three random disks, B1, B2, B3.
Right. Now consider the disks B1 and B2, which are centered on the x-axis at U1, U2. If these two disks happen to be disjoint, i.e. the distance u1, u2 is greater than r1 plus r2, then any line L that intersects both b1 and b2 is geometrically constrained.
How so?
This is where the geometry of common tangents comes in. Lemma 5, pages 15-16, proves a key result. For two disjoint circles, A and B on the x-axis, any line that intersects both must have a y-intercept that is less than or equal to the y-intercept of one of their common tangents. It basically says the line can't stray too far vertically if it has to hit both disjoint horizontal circles.
Okay. And corollary 1, page 16, generalizes this.
Yes, it says that for such disjoint circles A, B, any line gx intersecting both must lie entirely below the upper envelope of their four common tangents. That is gx, at max for all x, where 2 max is the pointwise maximum of the four common tangent lines.
So if b1 and b2 are disjoint, any line L hitting b1 and b2 must lie below this envelope T max. If that line L also has to hit B3, centered on the y-axis at U3, what does that imply?
It implies that the disk B3 must intersect the region, XYYA. Since B3 is centered at U3 on the y-axis, this puts a constraint on how large U3 can be. U3 can't be too far from the origin if B3 has to reach down to touch the region capped by Tmax.
I see. So the probability Q can be bounded by considering the probability that B1 and B2 are disjoint, AD, that U3 is close enough to the origin for B3 to intersect the constrained region.
That's the core idea behind the proof sketch of lemma 6, pages 16-19, which gives the upper bound on Q for small sus and T. They bound Q intersecting B1, B2, B3. They split this based on whether B1 and B2 are disjoint, event E2, or not, event EC2.
What's the probability they are not disjoint, EC2?
Lemma 3, page 13, bounds this probability by something like 7, T plus sus. This is small if T and suc are small. So the case where they overlap contributes relatively little to Q.
So they focus on bounding. PL intersecting B1, B2, B3, and B1, B2 are disjoint.
Yes. Using corollary 1, this event implies that U3 must be within some bound B plus related to the maximum height of the common tangents, 2 max, and the radius R3. They analyze the geometry of the common tangents, equations 10, 11 give their formulas, and derive bounds on this B plusic.
Okay.
Then they bound the probability PU3AB plus E2 by integrating over the distributions of U1, U2, which determine the distance between B1, B2 centers, and the random radii R1, R2, R3, which depend on noise. This involves some very complex calculations, including bounding expectations of terms involving logarithms and square roots using Jensen's inequality and properties of the noise distributions.
And the final result of all this?
Lemma 6, page 16. For CE1, they get Q4 plus O4 plus O1. This is the key bound for the between community probability. It shows Q is small when interior is small, vanishing roughly like x log 1x, where x equals T plus.
Oh, okay. They also have lemma 4, page 14, which gives a lower bound on Q, showing Q doesn't vanish too quickly either, but the upper bound is more critical for the algorithm analysis.
Right. So to summarize section 5.
1p, rejecting good triple, is small if T is large enough.
Q, accepting bad triple, is small if T and SA are small, roughly T plus log 1, 2.
For the algorithm to work well, we need both 1p and Q to be small simultaneously. This means P1 and Q is 0.
Which requires choosing the threshold such that it's significantly larger than T to make 1p small, but also small in absolute terms to make Q small. This is precisely the kind of condition S is tall 1 that appeared in Theorem 2a for almost exact recovery.
It all ties together. Okay, let's move to section 6 on page 20, analysis of the spectral algorithm. This section aims to formally prove Theorem 2 by analyzing the similarity matrix W and using matrix perturbation theory.
Exactly. The goal is to show that the eigenvectors of W, computed in algorithm 1, are close enough to vectors representing the true community structure, allowing k-means to succeed.
Section 6.1, pages 20-23, focuses on the concentration of the similarity matrix W around its expectation EW. They need to show that W, which is built from random data, is very likely to be close to its average behavior.
Lemma 7, page 20, is a standard concentration result for the sizes of the two communities, N1 and N2. Since labels Z are at Bernoulli 12, N1 is binomial, N12. Using Chernoff bounds, inequality 59, they show that N1 is very close to N2 with high probability. Specifically, N1, N2 at NNWHP if NLE is not too small.
Lemma 8, page 20-21, looks at counts of pairs and triples. Pen is the number of within-community pairs. 2a yin is the number of nodes k that form a within-community triple with a given within-community pair.
idea. They show these counts also concentrate around their expectations. Pin and N4, T idea in N2, using Chernoff bounds and union bounds over all pairs. This holds WHP if the deviation N is not too small. Let En be the event where all these counts are close to their means.
Okay, these lemmas establish that the underlying counts related to the true communities are well behaved. Now, lemma 9, pages 21-23, uses this to show W concentrates around EW, specifically for the exact recovery regime.
Right. Conditions are the exact recovery ones. Slowly. NTA. Under these conditions, they first note that the bounds from section 5 imply QO and 1 PA, since day is large and is small.
Okay, PO very strongly here.
They want to bound the expected squared Frobenius norm of the difference. EWFO EEJ, EWFO. They split this sum based on whether the pair IJ is within or between communities. EWFO or then 2ST. Pin var, J, plus pout var, IJ.
Where pin N4 and pout N4 are the number of pairs, now they need the variances.
Var depends on the variance and covariance of the indicator variables. IWFA is a hyper AA. The variance involves terms like varake and cove I. They define vin, vout, sin, kaut, c, ros, based on whether k share the community of ij, equations 17-18.
Using the very strong bounds on PA1 and QO, specifically N for this regime, they show that all these variance and covariance terms, vin, vout, sin, kaut, seg, ros, are very small, specifically O and...
Then, conditioning on the event Eden, where the counts, pin, pout, tn, etc., are concentrated, on, or on, the variance varween, en, comes out as on.
Summing over all n-vane pairs, roughly EWF 40n, is just on.
They also argue the contribution from the complement event E10 is negligible, so overall, EWF equals on.
Finally, apply Markov's inequality. PWEWF, ON idiom.
This proves concentration for the exact recovery case. WEWF is very likely EN for any AVP.
Lemma 10, page 23, does the analogous calculation for the almost exact recovery regime. 21.
Here, the bounds on PN are weaker, 1 PO1 and QO1, but not necessarily ON.
So the variance terms, vin, vow, etc., are only O1.
Right. Following similar steps, varween comes out as ON.
Sum over pairs gives EWF equal ON equal N,
Yeah.
already applying Markov, EWF here, we imply EWEF for. So for almost exact recovery, WEWF is likely AN mud, WHP, a weaker concentration bound, N mud versus N mud, consistent with the weaker conditions.
Okay, so W is close to EW. Now, section 6.2, pages 23-24, analyzes the structure of the expected matrix W equals EW and its eigenvectors.
They derive the structure of W in equation 21. It depends on when to EVZ and Y, expected weight for within community pair, and WOUT VBZ by its expected weight for between community pair. W of U, win plus WOUT 2, J plus with no WOUT 2, Xi diag, where J is all one's matrix, Z is the one community vector.
They calculate win and WOUT based on P and Q, equation 22. For a pair unwhale with ZJ, there are N2 nodes K with ZZ and N2 nodes K with CZ. A triple IGK with ZZ forms a hyperedge with probability P. A triple IJK with ZZ forms one with probability Q. So win N2P plus N2Q. Similarly, we U and no P mixed plus N2 mix.
Let's reread EQ22. Vi gashage. If CJ1, then for K with CK1, echo KP. For K with CK2, EKQ. If N or N2, NCO go, then win N2 1P plus N2Q. If Z1, ZJQ, then for K with CK1, IJK is between ECO Q. For K with ZK2, IJK is between each Q. So if N2 1Q plus, N2 NQN, let's check the paper.
Equation 22 has win N1 2Q plus N2Q if ZJ1 and what N2 plus N2 NQ is Z1 Z22. Assuming N1 N2 N2, win N2P plus N2Q and WOUT N2Q plus N2Q NQ. You need to be careful with the -1 or -2. Let's assume N large, win N2P plus Q. Why should I use their notation win WOUT?
Okay. The key is the structure of W allows them to find its eigenvalues and eigenvectors easily. Equations 23-24. The top two eigenvalues of D1 dual correspond to eigenvectors related to the all ones vector 1 and the true community vector Z, or rather Anani inversion.
Right. The subspace spanned by these top two eigenvectors, U captures the true community partition. All other N2 eigenvalues ECN are smaller.
The difference between the second and third eigenvalue, EL23, is the spectral gap. Equation 26, win vout N2, assuming N1, N2, N2. Wait, let's rederive. Vingam const J plus gap term is 2. Eigenvector Z gives eigenvalue related to gap term Eigenvector 1 gives eigenvalue related to const n. Other eigenvectors orthogonal to 1 and z get eigenvalue from the diagonal term. Paper says 1 and 2 win han, and 2 win what? No, edit 2 win what 2's, sis utts. This requires careful algebra. Let's trust their result. N, N2, 4, PQ, if N1, N2, N2.
Okay, the spectral gap is proportional to n row 10. Since we need pan 1 and k, the gap should be large, around O n twist. A large gap is good. It means the community structure is strongly encoded and the eigenvector should be stable to noise.
How do they quantify stability? Davis-Kahan theorem.
Yes. It bounds the distance between the subspace U spanned by the top two eigenvectors of W and the true subspace U spanned by the top two eigenvectors of W. The distance is measured by sin, UUF, where I is the matrix of principal angles between the subspaces.
The theorem states, sin UFS, they CWWFF, where E equals WWFF, where E equals the perturbation matrix and E is the spectral gap.
They use C2F2F.
This directly relates the error in the eigenvectors seen on the error in the matrix, EF, scaled by the inverse of the spectral gap.
Right.
1. If EF is small and error is large, the subspaces U and U will be close.
They also relate the sin distance to the Frobenius norm distance between the matrices U and U, up to an optimal rotation O.
EUOF, SSTAUF.
Combining these gives the key perturbation bound equation 28. UOF CUF, paper uses 2, 2. This shows that the matrix U computed by the algorithm is close, in Frobenius norm, to the true community subspace U up to rotation, provided EFE is small.
Okay, so the eigenvectors are close. How does this guarantee that k-means clustering works? Section 6.3, page 25.
They use a result, LEM11, that connects the performance of k-means on the perturbed data U to the distance UVF, where VUO is the optimally rotated true subspace, and the properties of the true clustering in V.
LEM11, adapted from prior work, basically says, let U be the data fed to k-means, our eigenvector rows. Let VZX be the true cluster structure. Z is membership, X defines centers. Let X be the k-means output for U. Let N-min be the size of the smallest true cluster. Let Dou be the minimum squared distance between the true cluster centers, rows of X.
If a perturbation is small enough relative to the cluster separation in size, specifically if 4, 2 plus U, VF, 4, and N-min, condition 29, then the number of k-means misclassifications, ham Z is bounded, ham 4, 2 plus U, V, F, 4, N, bound 30.
So if U is close enough to V, the true structure, k-means on U will give few errors. The amount of error depends quadratically on the distance UVF.
Now the proof of theorem 2, pages 25 to 26, puts all these pieces together.
They apply lemma 11 with K2, the true structure V, E away. The distance UVF is bounded using the Davis-Kahan result, EQ31, UVF, EF, E way, F.
They calculate the separation between the true cluster centers in the U space. These centers are related to phi n1, suit rotated. The squared distance comes out as dou n EQ32.
The minimum cluster size n-min is n4 w.p by lemma 7, EQ33.
Substitute these bounds into the k-means condition, 29. After simplification, it requires EF to be less than something proportional to N4 and N, paper EQ34, EF4, wait, let's recheck.
K-means condition 29, C1 UVF4 n-min substitute bounds, C1, C2 are EF4 and N4, Raves 2, EF4 to C3 N per N.
Okay, so condition is EF4 is C3, N4 as SE3, and NFE2. This looks different from EQ34 in the paper, which has N. Let's trust the paper's equation 34 for now. The condition needed is roughly EF4 and HFU.
Okay, and the misclassification bound 30 becomes ham EC5, EEVFU, EV6, NNC6, EV4, NDQ, matches in EQ35.
Right, so the number of error scales with EF and P.
Now, proof of theorem 2a, almost exact recovery, page 26. Conditions from lemma 10.
Lemma 10, EF and W get BAP also. PQ1 since Q1 P1.
Substitute into the error bound. Ham and C6, N1000 N run 3, and C6 and N.
The fraction misclassified is ham ye C6. Since we can make A arbitrarily small, we can make this fraction A for any desired D0 with high probability. That's almost exact recovery.
Okay. Proof of theorem 2b, exact recovery, page 26. Conditions, slug on and log n.
From lemma 9, EFAM as EC6, AMNE, she again, PQ1.
Substitute into the error bound. Ham SC6, EAEAT.
The number of misclassified points ham is bounded by a constant C6A WHP.
But ham must be an integer. If it's bounded by a constant C6A WHP and we can make arbitrarily small, doesn't that mean ham must be 0?
Yes. For any fixed A arrow, let the constant be C. We have P ham C, PE not concentrated, O1. If we choose A small enough so that C1, then the event ham is the same as ham 1.
The probability of having one or more errors goes to 0.
Which means the probability of having 0 errors goes to 1. That's exact recovery.
Okay, that completes the analysis for algorithm 1. It works near optimally if you can set the threshold t correctly. Now, section 7, pages 27-33, proves that algorithm 2, the data-driven version, works for almost exact recovery.
Right. Recall algorithm 2 samples M triples, calculates their TLS score psi, sorts them, and picks T, where K is the index corresponding to the FMT quantile.
It uses the empirical distribution function FMT1M. T is chosen, so FT at 14. The idea is it should align with the threshold where EFMT plus 34 key T is also close to 14.
First, a technical point on page 27-28. They argue the sorted scores SI are almost surely distinct, so the quantile T is well defined. This involves showing the TLS score function is analytic almost everywhere.
Lemma 12, page 28, shows that if M, N, and 9, the M sample triples are likely disjoint, don't share any points, which helps ensure independence for concentration arguments. Proof uses a simple union bound.
Section 7.1, pages 28-33, provides concentration results for this threshold selection process. Lemma 13 shows FMT concentrates around its expectation, MFT WWHP, uses Chernoff bounds, leveraging the likely disjointness from Lemma 12.
Lemma 14, pages 29-30, is interesting. It shows two things for the center 1 regime. First, if you pick a threshold Tn that stays bounded above 0, then FMTN will be bounded away from 14 WHP because QT will be non-negligible. Second, there does exist a vanishing threshold SN, like say SND, such that FMSN is close to 14 WHP.
This confirms that targeting the 14 quantile indeed forces the algorithm to select a vanishing threshold T1, which is necessary for the spectral method theorem 2a to work.
Lemma 15, pages 31-33, is the crucial link. It says roughly, if Tn is small, A and D FMTN is close to 14 within A and D. EFMTN is also close to 14 within ADN. ADN is sufficiently small relative to N, specifically centenary N log 1N, that it must be the case that both QTN and 1PTN are small, also within ON.
The proof is by contradiction. It assumes Q or 1P are large and shows this leads to contradictory requirements on Tn based on the bounds from lemmas 2 and 6, unless the condition SUN log 1 and ln is violated. So if that condition holds, Q and 1P must be small when FMT is near 14.
Okay. Finally, the proof of theorem 3, pages 33-34, puts this together for algorithm 2.
Algorithm 2 runs on input satisfying SUN 1 and 001. It selects T. By lemma 14, WHT is chosen such that FMT 14 is small. By lemma 13, WHT EFMT is also small.
So the condition FMT 14 plus FMMT EFM holds for some NO1 ion.
Now, does the condition 1 on N from lemma 15 hold? The proof argues yes. Since SUN 01, we can always find a sequence N1 that bounds En plus such that this condition is met. For example, pick N related to unknown for some N1.
Okay, so the conditions of lemma 15 are met by the chosen TWAP. What does lemma 15 conclude?
It concludes that Qn and 1PT, so QPT on 1 and 1P, so QA1 and 1P.
Now, algorithm 2 runs algorithm 1 on the nodes, aka NN nodes, using this threshold T. We need to check if the conditions for theorem 2a, almost exact recovery for alg 1, are met for McE.
The conditions were noise sen orum given threshold T ensured by lemma 14 and sen ora T that holds if T doesn't vanish too quickly, which is implicit. And we also need QT 1PT, which we just got from lemma 15.
So yes, the conditions for theorem 2a seem to hold W-AP for the execution of algorithm 1 within algorithm 2.
Therefore, algorithm 1 on McCarrick achieves almost exact recovery WAHP. Since the number of nodes in M, which were ignored or randomly assigned, is negligible, MEMNAAN, the overall error rate for algorithm 2 on all N nodes also goes to 0. Almost exact recovery is achieved.
Fantastic. That closes the loop on the clustering algorithms. Now, quickly revisit the proof for theorem 4, line recovery on page 34. This was about showing algorithm 3, sample mean sample covariance eigenvector, works if you have almost exact recovery.
Right. Theorem 4 claims consistency for estimating the center K and direction VK.
Lemma 16, pages 34 or 36, handled the center XK. It showed XK converges to coinc in probability. The proof involves splitting the estimated cluster Gish into correct points A and incorrect points B. Since BIC E0 by almost exact recovery, the contribution from B vanishes and the mean over A converges to coin by law of large numbers.
For the direction VUC leading eigenvector of sample covariance, IC, They need to show ik converges to the true covariance ik. The true covariance is Heger-Fingo plus ik, where tik is variance along the line vk. Its leading eigenvector is ek.
They use the fact that the sample covariance computed only on the correctly labeled points converges to K in Frobenius norm, standard result EQ50.
Then lemma 17, pages 35 to 37, shows that the difference between the full sample covariance ik and sklink also goes to 0 in probability. The proof again involves splitting into correct and incorrect points and showing terms involving the small fraction of incorrect points vanish.
So ik sin slinkography implies ik-keying probability.
Yes, by triangle inequality. Yuk moko, yuk sklinkovo plus u sklinkovo. Both terms on the right go to 0 in probability.
Now, proof of theorem 4, pages 34-35. Consistency of X-Canofi is lemma 16. For Vork, they apply Datascon theorem comparing the eigenvectors of Uk.
CO is bounded by a spectral gap of Uk.
The spectral gap of Fook is 1 pro. This is the variance along the line assumed positive constant.
And Uk goes to 0 in probability, as we just established.
So CNO term going to 0, 0 in probability.
Which means the angle between the estimated direction Vuk and the true direction Ryoko goes to 0 in probability. That proves consistency for the direction.
Okay, that covers the proof structure for line recovery too.
Hmm?
Appendix A just lists the standard concentration inequalities they used. Rayleigh CDF, chi-squared tailbound, Chernoff bound.
And the references show this work builds on a solid foundation of prior research.
All right, we have really dug deep into this paper now. It's been quite a journey.
It has. We started from that basic challenge line clustering where simple graphs just don't cut it.
Then we saw how the paper proposed using a geometric hypergraph, specifically building it from triples of points that are approximately collinear, using that total least squares or TLS score.
We spent a good amount of time on the theoretical limits, the information-theoretic bounds derived from analyzing the maximum likelihood estimator in the oracle setting for the GLMMN model. Understand exactly when exact recovery versus almost exact recovery is even possible.
Based on that meticulous MLE analysis and those tricky integrals in lemma 1.
Then we detailed their main algorithmic contribution, the polynomial-time spectral algorithm, algorithm 1, that operates on a similarity matrix derived from the hypergraph. We saw the analysis showing it can achieve performance close to those IT limits if the threshold T is chosen correctly relative to the noise.
Which led to the crucial algorithm 2, the data-driven version that selects the threshold automatically by sampling triples and targeting that 14 quantile of TLS scores. We walked through the proof showing this clever idea works, achieving almost exact recovery without needing to know beforehand.
That involved diving into those bounds on hyperedge probabilities, P and Q, using geometric arguments about common tangents and probability concentration inequalities. Quite sophisticated analysis there.
And finally, we close the loop by showing that once you have a good clustering, almost exact recovery, a simple follow-up method based on sample mean and sample covariance eigenvectors, algorithm 3, can consistently estimate the true parameters, the center and orientation of the underlying line segments.
So this deep dive has really given us, and hopefully you, a comprehensive understanding of the rigorous foundations laid out in this paper. You've seen the problem formulation, the hypergraph solution proposed, the fundamental limits derived, and how the algorithms and their guarantees connect back to those limits, all supported by detailed mathematical reasoning.
Yeah, what really stands out is the power of choosing the right mathematical representation. Here, the hypergraph was key to capturing those complex, higher-order geometric relationships that simple pairwise methods just completely miss.
Absolutely. But it also highlights the significant theoretical work required to actually analyze these more complex structures, especially when inherent dependencies, like the geometric dependencies here, break standard simplifying assumptions. Proving guarantees becomes much more involved.
Which leads us to a final thought, perhaps. This paper successfully modeled and analyzed geometric dependence within a hypergraph framework for line clustering. What other kinds of complex dependencies, maybe in different domains like social networks or biological systems or physical interactions, could be better modeled using higher-order structures like hypergraphs?
That's a great question. Where else do interactions fundamentally involve more than just pairs? And if we try to use hypergraphs there, what new theoretical challenges will arise from the specific nature of those dependencies, requiring new analytical tools beyond what we've seen here or in standard block models? Moving beyond pairwise thinking seems full of potential, but also full of challenges. Okay, let's unpack this. Welcome to the deep dive. Have you ever looked at a scatter plot of data? Maybe it's sensor readings or points extracted from an image or even GPS traces, and you notice that some of these points seem to line up.
Yeah, you just see it, right? They look like they belong together.
Exactly. You just know they should be grouped together because they form some kind of linear structure. It's a really fundamental challenge in data analysis. How do you programmatically find and group points that lie on the same line?
And it's definitely harder than it first appears, precisely because of the geometry of lines. If you try to model this using a standard graph, where you put an edge between 2 points based on some similarity, well, you run into a fundamental issue.
Which is
any 2 points, doesn't matter where they are in space, they define a line. Always.
right. So if your similarity score is based on whether 2 points are collinear, every single pair of points would get a high score because you can always draw a line through them.
Exactly.
So a standard graph based on just pairwise collinearity, it doesn't give you a structure that helps you distinguish points that belong to the same underlying line structure from points that are just, randomly aligned with one other point.
Traditional pairwise graph methods just aren't really well suited to capture that idea, the concept of points belonging to the same global line.
So the real problem is identifying groups of points where many points in the group are collinear, which indicates some underlying linear structure that generated them.
That's it. That's the line clustering problem we're diving into today, exactly as defined in this paper's abstract and introduction. Grouping points in a Euclidean space, think 2D or 3D space, such that each cluster, each group, is well approximated by a line segment.
And the paper's key insight to tackle this, as we'll see, is to move beyond just looking at pairs of points. They propose using higher order interactions.
Right, specifically modeled by what they call geometric hypergraphs. So instead of connecting pairs, they consider connections between sets of points.
Particularly sets of 3 points at a time, right?
Yes, triples, because higher order interactions are essential here. Collinearity, it's a property that's really only meaningful for 3 or more points.
Because any 2 points are always collinear.
Right, but 3 points, they're only collinear if they actually lie on the same line. So by checking triples for collinearity, you get a much more meaningful signal about the underlying lines in the data.
Okay, so our mission today is to take a really deep dive into this specific approach. We'll focus on a particular statistical model the authors use to ground their theoretical analysis.
The Gaussian line mixture model, or GLM-MM.
Right. The idea is points are generated by 2 latent or sort of hidden line segments in the plane, and then there's some additive Gaussian noise thrown in.
So each point gets assigned to one of the 2 lines, and then its true position on that line is perturbed, kind of bumped off, by random noise drawn from a Gaussian distribution.
Okay. And our goal in this deep dive is to really understand the fundamental statistical limits of line clustering in this specific GLM-MN model. Like, how much noise can the data tolerate?
And how many points do you need to reliably figure out which point came from which line? We'll dissect the specific geometric hypergraph approach they propose, which uses the approximate collinearity of triples.
And the spectral algorithm they developed based on the structure of this hypergraph.
Right, and the theoretical guarantees they provide for how well that algorithm performs compared to those fundamental limits we talked about.
And we're going to do this by meticulously reviewing the source material, explaining the concepts, the math, the notation, and the derivations as we go.
Getting into the weeds.
Exactly. Our source today is the paper Consistent Line Clustering Using Geometric Hypergraphs by Alaluusua, Konstantin Avrachenkov, B.R. Vinay Kumar, and Leskelä. And the date on this paper is June 2, 2025.
Very recent work. Let's start right at the beginning. Page 1, title and authors.
Page 1, right at the top. We see the title we just mentioned, Consistent Line Clustering Using Geometric Hypergraphs. The authors are Alaluusua and Leskelä from Aalto University in Finland.
Okay.
Konstantin Avrachenkov from INRIA in France, and B.R. Vinay Kumar from Eindhoven University of Technology in the Netherlands.
So a nice international collaboration. And the date, again, 2 June 2025, confirming it's fresh research.
All right, moving down to the abstract. That essential summary of the paper's contributions and findings, let's go through it sentence by sentence just to make sure we capture the essence. First sentence. Traditional data analysis often represents data as a weighted graph with pairwise similarities, but many problems do not naturally fit this framework.
Yeah, that sets the stage perfectly. Acknowledges the standard approach, but right away points out its limitations. It echoes what we were just saying about why simple graphs aren't always the right tool.
Which leads directly to the second sentence. In line clustering, points in Euclidean space must be grouped so that each cluster is well approximated by a line segment.
That's the problem statement.
Yeah.
Clear, concise. Points in space, group them into lines.
Then the third sentence explains the core difficulty and the proposed solution. Since any 2 points define a line, pairwise similarities fail to capture the structure of the problem, necessitating the use of higher-order interactions modeled by geometric hypergraphs.
And that's the core motivation right there. Pairwise collinearity is useless because it's always true. You need to look at groups of points, higher-order interactions, to detect that collective approximate collinearity that signals a shared underlying line.
So higher-order interactions means looking at groups, not just pairs. And the tool is a geometric hypergraph. What exactly is a hypergraph again?
It's basically a generalization of a standard graph. In a normal graph, an edge connects 2 vertices. In a hypergraph, a hyperedge can connect any number of vertices, 2, 3, 10, whatever.
Got it. And the geometric part comes in the fourth sentence. We encode geometry into a 3-uniform hypergraph by treating sets of 3 points as hyperedges whenever they are approximately collinear.
So this is the concrete construction. They build a 3-uniform hypergraph, meaning every single hyperedge connects exactly 3 vertices, or points in our case. And a hyperedge I, j, k exists if and only if the points gxj and xk are, close enough to lying on a straight line.
Approximately collinear. So the geometry of the points themselves defines the structure of this hypergraph.
Precisely.
Okay, so the hypergraph essentially records which triples of points are nearly aligned. The fifth sentence then connects the structure back to the clustering problem. The resulting hypergraph contains information about the underlying line segments, which can then be extracted using community recovery algorithms.
Right. The idea is if points belonging to the same line segment tend to form these approximately collinear triples, then the part of the hypergraph formed by just those points will be much denser with hyperedges.
Compared to triples that involve points from different lines.
Exactly. And community recovery algorithms, which are designed to find densely connected groups or communities in graphs or hypergraphs, can then hopefully pick out these groups that correspond to the actual line segments.
But then the sixth sentence introduces a crucial theoretical challenge. In contrast to classical hypergraph block models, latent geometric constraints in this construction introduce significant dependencies between hyperedges, which restricts the applicability of many standard theoretical tools.
This is a really key point. Standard models, like the hypergraph stochastic block model, often assume hyperedges form kind of independently based just on the community memberships. But here, because the points have actual geometric locations, even with noise, whether IIJK is approximately collinear is not independent of whether, say, IIJLs.
Because they share points I and j and their positions are fixed.
Exactly. This geometric structure creates dependencies between the hyperedges. It reflects the continuous nature of the lines. And this dependent structure makes the theoretical analysis much, much harder than for standard, more abstract block models.
Okay, that dependence is critical. Seventh and eighth sentences state the paper's main aims. We aim to determine the fundamental limits of line clustering and evaluate hypergraph-based line clustering methods.
So 2 goals. Find the absolute best possible performance theoretically possible, regardless of the algorithm. That's the fundamental limit. And second, see how well their specific hypergraph method performs against that limit.
And the ninth sentence details the limits they derive. To this end, we derive information-theoretic thresholds for exact and almost exact recovery for data generated from intersecting lines on a plane with additive Gaussian noise.
Okay, so information-theoretic thresholds. These are hard limits based purely on the information content of the data itself, given the noise. It's the boundary between what's possible and impossible to learn, no matter how clever your algorithm is.
And they derive these for the GLMMN model intersecting lines plus Gaussian noise for 2 types of success. Exact recovery.
Meaning you classify every single point perfectly.
And almost exact recovery.
Meaning the fraction of misclassified points goes to 0 as you get more data. Maybe not perfect, but asymptotically vanishing error rate.
Got it. Finally, the 10th sentence describes their algorithmic contribution and its performance. We develop a polynomial-time spectral algorithm and show that it succeeds under noise conditions that match the information-theoretic bounds up to a polylogarithmic factor.
So they propose an efficient algorithm. Polynomial time means its runtime doesn't grow exponentially with the data size. It's based on spectral methods, which usually involve looking at eigenvalues and eigenvectors of some matrix derived from the data, in this case from the hypergraph.
And the impressive result is that its performance nearly matches the theoretical limit, off by only a polylogarithmic factor. What does that mean exactly?
It's a factor involving logarithms of n, the number of points. Think things like log n or log n squared or maybe log n. These terms grow much, much slower than n itself. In theoretical computer science and statistics, matching a fundamental bound-up to a polylog factor is considered a very strong result. It means the algorithm is essentially capturing almost all the available information.
So it's very close to the best theoretically possible performance.
Exactly.
Okay, so the abstract lays out a compelling story. Deep theoretical analysis of the problem's limits, a novel hypergraph approach tackling tricky geometric dependencies, and a near-optimal algorithm with solid theoretical guarantees. This is definitely worth digging into. Let's move into the full introduction section, starting on page 1.
Section 1, paragraph 1, it basically just reinforces that initial point we discussed. Standard graph representations using pairwise similarities just don't cut it for line clustering because every pair of points forms a line.
Right, it hammers home that conceptual hurdle again. You can't just build a graph where edges mean collinear pair, because every pair is collinear. You need something that captures collective collinearity.
Which brings us to paragraph 2 on pages 1 and 2. This gives the formal definition of that statistical model they use, the GLMMM model.
Okay, let's break it down. They consider n points, let's call them G, living in R2, so just points on a 2D plane.
And crucially, there's an underlying unknown community membership vector. Let's call it Z. It's a list Z, Z1, Zn, where each Z is either 1 or 2. This tells us which of two hidden line segments the ith point truly belongs to.
Okay, so each point has a hidden label, 1 or 2. They also fix a noise parameter, which is greater than 0, representing the noise level. And they have two actual line segments, L1 and L2, defined in the plane.
Then the observed points, the she's you actually see, are generated like this. She E is UE plus 1.
Okay, let's unpack that. UE is a point.
U is the true noiseless position of the point. It's selected uniformly at random from the line segment LC. So from L1 of Z is 1, or from L2 of Z is 2.
And then psi I is the noise term.
Right. Y is a standard normal random variable in R2. That means it's a random 2D vector drawn from a Gaussian distribution centered at the origin, 0 mean, with an identity covariance matrix. Think of it as random jitters in both x and y directions, with variance psi-dum as each direction, and the x and y jitters are independent.
So isotropic Gaussian noise. You pick a true point UE on the correct line, then add some random Gaussian fuzz Z to get the observed point G.
Exactly. And all the UEs, the true locations, and E's, the noise vectors, are assumed to be mutually independent.
And the probability distribution of the observed data X, given the true membership Z, is what they denote GLMM L1, L2 side.
They also define GLMM L1, L2 without conditioning on Z. That's the case where the membership Z themselves are random specifically. Each Z is chosen independently and uniformly from 1, 2. So each point has a 50-50 chance of belonging to L1 or L2, independently of all others, before the noise is added.
Okay, that's the setup. Paragraph 3 on page 2 then restates the goal. You see the noisy points X, and you want to estimate the hidden membership vector Z, and maybe estimate the lines L1 and L2 themselves too.
And they reiterate that doing this successfully requires capturing those higher-order geometric relationships we talked about, because points on the same line are inherently connected through their collinearity.
Which naturally leads them back to the hypergraph representation. They formally define it. Hypergraphs generalize graphs by allowing hyperedges to connect more than two vertices simultaneously, and note their usefulness across different fields.
But they also point out that the theoretical analysis for hypergraphs, especially for community detection, isn't as mature as it is for standard graphs. So their contribution is to establish theoretical consistency guarantees for a hypergraph-based algorithm specifically designed for this geometric line clustering problem.
Makes sense. Paragraph 4 on page 2 then dives into prior work. Community detection on graphs is a very well-studied area. For hypergraphs, a common framework is the hypergraph stochastic block model, or HSBM.
And a typical way to analyze these HSBMs is through something called clique projection. Basically, you take each hyperedge, say, connecting points ij, k, and replace it with all the pairwise edges within that set, ij, ik, jk. This turns the hypergraph into a standard graph.
And then you can apply standard graph algorithms.
Exactly. They mention using spectral methods or semi-definite programming SDP algorithms on this projected graph, or sometimes modularity-based approaches directly on the hypergraph.
But here's the catch they emphasize. prior work on line clustering that did use hypergraphs often relied on assumptions like hyperedges forming independently.
Which, as we discussed, is violated in this geometric setting due to the underlying point locations creating dependencies. That's a key difficulty, and a differentiator for this paper. They tackle the dependency issue head-on.
Paragraph 5 continues discussing prior line clustering methods, mentions some earlier hypergraph approaches, and also nods to the classic Hough transform from way back in the 70s.
Ah yes, the Hough transform. The idea there is quite different. You map each point in your data space into a curve in a parameter space. Points that are collinear in the original space correspond to curves that intersect at a single point in the parameter space. So finding lines becomes finding points where many curves cross.
Clever idea. Used a lot in computer vision, they mention.
Very much so.
Yeah.
But it has limitations, particularly with memory usage when you have complex curves or higher dimensions.
Okay. Then paragraph 6 on page 3 contrasts their work with a related line of statistical research, specifically work by Arias Castro and others.
That line of work is more focused on detection. Imagine you have a noisy image, maybe mostly static. Is there a faint line segment or a curve or a disk hidden in that noise? They develop methods, often using multi-scale scan statistics, for hypothesis testing, basically, answering the yes-no question. Is there an object present?
So detection, not recovery. They mention later work improved detection algorithms too.
But the key difference they highlight is that this detection theory gives no guarantees on point-wise labeling of the data or consistent estimation of the object's geometry. It doesn't tell you which points belong to the line if one exists, nor does it estimate the line's parameters accurately.
Which leads into paragraph 7, clarifying their distinct objective, community recovery. They want to solve the clustering problem within this structured mixture model, the GLMMN.
Two main goals, again. 1, accurately assign each observation xi to its correct line. That's the exact or almost exact recovery of z. And 2, consistently estimate the properties of the line segments themselves, like their center and orientation. They see detection and recovery as complementary problems, often relevant in different noise regimes.
This brings us neatly to the numbered contributions listed on page 3. Let's go through them.
Contribution 1. We derive conditions on the model parameters that determine the statistical limits of recovery. Exact recovery is possible if and only if say. Almost exact recovery is possible if and only if say.
These are those fundamental information-theoretic thresholds again. The notations say n means the noise standard deviation needs to go to 0 faster than 1n as the number of points n increases.
Well, n1 just means tau needs to go to 0 as n increases, but it can do so much more slowly. These are the absolute best case scenarios, achievable only by an optimal procedure like the maximum likelihood estimator, MLE, assuming you knew the lines.
Okay. Contribution 2. We introduce a geometric hypergraph representation based on total least squares, TLS residuals, over all triples, capturing latent collinearity.
This is their core modeling idea. Build the hypergraph using triples, measure their collinearity using TLS, total least squares, which we'll define formally later. But it's basically a way to find the line that best fits the 3 points.
Contribution 3. We propose a polynomial-time spectral algorithm requiring no prior knowledge of the underlying line structure, and they state its performance guarantees.
Right. Exact recovery is achieved if the noise times log n is much less than the TLS threshold t, which in turn must be much less than n log n. This matches the IT threshold c up to those polylog factors, log n and log n.
And for almost exact recovery.
They show it works with a data-driven rule for selecting the threshold t, without needing to know c beforehand, as long as a true c1. This matches the almost exact IT threshold perfectly.
That's very impressive. Finding the limits, proposing an efficient algorithm, showing it's near optimal, and even making it practical for almost exact recovery without knowing the noise level.
Yeah, it's a solid package of results. The concluding sentence just summarizes that the work illustrates how encoding geometric constraints in hypergraphs can be powerful, and highlights the impact of those hyperedge dependencies, offering broader insights for geometry-aware community recovery problems.
Okay, before we dive into the math behind these claims, let's quickly nail down the notation from remark 1 on page 4.
Good idea. Bold letters are vectors and matrices. Standard stuff.
ANEBN means the limit of the ratio ANBN is 0 as n goes to infinity.
So AN becomes vanishingly small compared to BN for large N.
ANEBN means the limit of that ratio, ANBN, is greater than 0.
Right, doesn't go to 0. It might converge to a positive number, or it might even go to infinity. It just means an n doesn't become negligible compared to bn.
And ANEBN means AN is less than or equal to some constant c times bn for all sufficiently large n.
Bounded above by a constant multiple of. It's standard big O type notation, but hiding the constant factor. Useful for focusing on scaling behavior.
Perfect. Now we're equipped for the asymptotic arguments. Let's move to section 2, information-theoretic bounds, starting on page 4.
Right. The goal here is estimate the true community vector Z based only on the observed noisy data X. And the first step is to define exactly what we mean by success. Definition 1 on page 4 gives us those two notions, exact and almost exact recovery.
And they're defined using something called the permutation invariant Hamming distance. Ham. Let's break that down. A is our estimated label vector. Z is the true one.
Hamming distance usually just counts the number of positions where two vectors differ. Here, ham, OEC, is the minimum Hamming distance you can get after possibly swapping the labels 1, 2 in our estimate.
Why the permutation?
Because the labels 1 and 2 are arbitrary. If we perfectly separate the points but call the true line 1 points cluster 2 and vice versa, we still solve the clustering problem perfectly. We just flip the names. So Ham finds the best possible matching between estimated and true labels before counting errors.
Okay, so it's the minimum number of misclassified points accounting for the arbitrary labeling. The formula is ham z min mes 2 n I111, where S2 is the set of permutations of 1, 2, either identity or swap.
Makes sense. So with that definition, exact recovery is when the probability that ham equals 0 goes to 1 as n goes to infinity.
P-ham 1, perfect classification with high probability.
And almost exact recovery is when, for any small positive fraction, the probability that the fraction of misclassified points, ham OZ, is less than or equal to goes to 1 as n goes to infinity.
P-ham in awa, ara, for all, 0. A error rate vanishes.
Got it. Now, Theorem 1 gives the fundamental limits for these recovery goals, but in a simplified oracle setting.
Oracle setting meaning?
Meaning we assume we magically know the true line segments L1 and L2 and the noise level. We just don't know the membership vector Z.
Why assume that?
Because it simplifies the problem immensely. If you know the lines, then for each observed point G, the task of figuring out its label Z just becomes a hypothesis test, which she generated from the known distribution F1, points from L1 plus noise, or the known distribution F2, points from L2 plus noise.
Ah, so it breaks down into n independent decisions.
Exactly. And the performance in this oracle setting gives a lower bound on the difficulty. If you can't achieve recovery even when you know the lines, you certainly can't achieve it when you don't know the lines and have to estimate them too.
Makes sense. So what does Theorem 1 say?
Conditions L1, L2 are in R2, they have equal length, and they intersect at their midpoint. The data, ZSX, comes from the GLMM L1, L2 sen model, and importantly, the model parameters, L1, L2 sen, are assumed known.
Okay. And the results?
1, exact recovery is possible if and only if the noise then
has to vanish faster than 1n.
C, almost exact recovery is possible if C, if n.
Sen just has to vanish, can be slower.
And the theorem also states that the maximum likelihood estimator, MLE, achieves these bounds, and conversely, if these conditions on sen are not met, then no method can achieve the respective type of recovery. These are hard thresholds.
Wow. So even knowing the lines perfectly, if your noise is, say, proportional to 1n, you cannot guarantee exact recovery. The noise overlap is just too much relative to the number of samples.
Precisely. The limitation comes from the inherent statistical difficulty of distinguishing the two noisy line distributions.
They also note on page 4 that the threshold itself doesn't depend on the angle up between the lines, as long as it's fixed between 0 and tray and the lines have equal length and intersect at the midpoint.
Yeah, the angle affects the constant factor in the error probability, but not the scaling threshold itself. For their algorithmic analysis later, they'll often focus on the right angle case, because the algebra is simpler, but this information-theoretic threshold holds more generally for this setup.
Okay, so to really understand why these sen and sen on thresholds emerge, we need to dig into the analysis of the MLE, which is the optimal procedure here. That takes us to page 7 and onwards, particularly lemma 1.
Right, page 7 sets it up. As we said, estimating a single z based on xi reduces to a hypothesis test between two distributions, F1 and F2.
F1 is the distribution of points generated from L1 plus noise, F2 from L2 plus noise.
And the Neyman-Pearson lemma tells us that the optimal test, the one that minimizes the probability of error, is the maximum likelihood estimator, MLE.
How does the MLE work here?
For each point sheet, you calculate its probability density under each hypothesis, F1 HOA she of psi1 and F2 bar density of Z2. The MLE rule is simple. Assign A to whichever label gives the higher density.
So OEX argmax K macri. If F1 A she F2 guess 1, if F2 A she F1A guess 2.
Exactly. Ties can be broken arbitrarily, say assigned to 1. It doesn't really affect the outcome asymptotically because the boundary where F1, F2 is usually a lower dimensional set with probability 0.
What are those densities FKX exactly?
Good question. The density FKX for a point XR2, assuming it came from line LK with noise, involves averaging the Gaussian noise kernel over all possible true starting points on the line segment. LK. Formally, FKX is the integral over, and LK of weighted by the uniform probability measure on LK. If LK is length, it's 1 times that integral using arc length.
Okay, so it's like smearing the Gaussian noise blob along the line segment. Now, on page 8, they define the average error probability per point for the MLE, assuming a uniform prior, let's call it per.
Right, and they relate per to the total variation distance, DTV F1, F2, between the two distributions. The formula is per equals 12, 1 DTV F1, F2.
What's total variation distance?
It measures the maximum difference between the probabilities assigned to the same event by the two distributions, DTV F1, F2 sup over all measurable sets A of F1A, F2A. It ranges from 0 identical distributions to 1 completely separated distribution.
So if DTV is 1, the error per is 0. If DTV is 0, per is 12. Just guessing. Makes sense.
They also relate it to the MLE decision region. Let A be the set where F1x, F2x, and then 1 DTV F1, F2 equals 2 F1AC, where A is the complement where F2x, F1x, so per F1AC, which is the probability that a point truly from L1 gets classified as L2 by the MLE.
Okay, now we get to the crucial lemma 1 on pages 8-10. This lemma calculates the asymptotic behavior of this per point error probability per as the noise goes to 0.
Specifically, it considers two lines of equal length intersecting at their midpoint at an angle OCO 2. It gives the formula for per, equation 2, which involves an integral of products of Gaussian complementary CDFs. But the really important part is the limit.
What's the limit?
Lim per plus code 2. The limit is proportional to tan test code 0.
So this tells us that for small noise, the error probability per is approximately C's, where C depends on the line length and the angle. It vanishes linearly with.
Precisely. That linear dependence is key. Now, should we walk through the proof sketch on pages 8-10 to see how they get that constant?
Yes, absolutely. This is a core calculation. They start by assuming, without loss of generality, WLOG, a convenient coordinate system.
Right, as shown in figure 2, like HOPA 2. They align L1 with the vector, cos, sin, per, and L2 with cos, sin, per. Points on L1 are u cos, sin, buck, and on L2 spore, and for ranging from O2.
And in this setup, the decision region AC, where F2, F1, turns out to be the union of the first and third quadrants.
So per px in axx, F1. A point x from F1 is u cos s plus y1, u sin plus y2, where u is uniform on at R2 and y1, y2 are independent standard normals. We need the probability that this point lands in quadrant I or 3.
Due to symmetry, they calculate the probability for u in 0, A2, and multiply. The condition x in x becomes conditions on the noise terms relative to u. After some steps involving rotation and symmetry of the Gaussian noise,
they arrive at per A2 A2 plus if the 2 piece plus 2 what's in the assembly. This is the integral form at the top of page 9. Is the standard normal complementary CDF PS2.
Okay, now the crucial step, change variable to s, then do state the upper limit becomes per.
The expression becomes per cos becos plus 2 os cos fest.
Now, they want the limit of eo cos as phi cos multiplying by e cos. As phi recos, the upper limit goes to infinity. So the limit becomes lim sin per e cos plus e sin per e cos e sin pros.
Now we need to evaluate these three integrals from 0 to infinity. Let's take the first one. Mi cos c e cos sin bo. Let's see e cos quindo. We need e so sin cos 2.
We establish this integral evaluates to 1 sin.
All right, so 0 t sin 1 sin cos, and similarly e sin cos equals 1 sin bucosine.
Good. Now the third term. 9 is 2 e cos scumpo sin glucose. This involved changing order of integration and switching to polar coordinates.
The result was -1 woon cos d cosine bo cos.
And splitting that integral at the end gave 1 cos sin bo plus 1 sin bo cos sin bo cos.
Okay, now we put all the pieces together for the limit of sin to per. It's 2 times the sum of the 3 integral results. So 2 can sin sin fos plus 1 sin 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 fos plus 1 sin 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 fos, pulling out 1 in sopo gives 2 times 1 sin sin fos plus 1 sin sin fos.
Grouping terms by denominator. 2 can sin fos tempo.
Which simplifies to 2 plus sin plus sin fos plus 2 fos plus 10 speng fos.
Okay, wait. Let's check the lemma statement again. It says lim sin sec fos plus 3 fos per sos. It seems to be a factor of 2 difference between our derivation and the statement.
Let's reread the start of the proof calculation on page 8 to 9 very carefully. Per F1AC, they use symmetry to get per 2px in q1x F1u in 0 consent 2. This becomes 2 plus FO's p noise conditions for q1 u, okay? Then they substitute noise conditions leading to per 2u. Yes, that setup seems correct.
Then 10 sin fos 10 zebu. Yes, the limit is 2 pos so. Yes. The integral evaluation, 1 sin fos sos plus 1 plus sed fos spec fos.
Yeah.
So 2 r out by plus 2 r at 2 r percent. 10 muscles caught. This is the limit of so per.
Why does the lemma state the limit of so per is 1 part plus capo? If lim so per constans, then lim so per const con.
Ah, okay. So if const tan plus cot po, then const show tan plus cot, that still doesn't match the one factor.
Let's check the integral 0 and under 2 dt t1 again. Yes, that's correct. Maybe the radial integral dd hor sobro rer dr. Let's check gamma function over. Let 2 et t2 big d2 et t et et t12 et2 rd ele e2 rt2 d2 r2 and 12 e22. So the integral is told 2 out of 2. Yes, that's correct.
Okay, the calculation seems solid. Let's assume there might be a typo in the constant factor in the paper's lemma 1 statement, or our interpretation is slightly off. The crucial takeaway is the scaling. Per is proportional to so for small.
Agreed. Per c. That's the key input for proving theorem 1.
Right. Let's redo the proof of theorem 1, pages 11 to 12, using Pareca.
Necessary condition for exact recovery. Probability of at least one error is roughly bounded by n per error n te. For exact recovery, this must go to 0. N te requires not is 0, which means n not. If c till arrow, then un-o inio prob doesn't vanish, MLE fails, so any algorithm fails. Exact recovery, impossible.
Sufficient condition for exact recovery. If c hun ante nen per error, sex ea error, probability of at least one error goes to 0. MLE succeeds, WHHA, exact recovery possible.
Necessary condition for almost exact recovery. Hammond NEO improbability. We need the expected fraction of errorsehen on to go to 0. If m ham then per error does not go to 0, it's bounded below by a constant. If the average error rate doesn't go to 0, the actual fraction won't reliably go to 0 either by Markov or Chebyshev. Almost exact recovery impossible.
Sufficient condition for almost exact recovery. If say 1, then per a phase 0. Since a hem per a phase Markov's inequality p hem e a for any fixed 0, the fraction of errors goes to 0 in probability. Almost exact recovery possible.
Perfect. That rigorously establishes the threshold stated in Theorem 1 based on the linear dependence of per on us derived in lemma 1 up to the exact constant factor.
And remark 3 on page 10 just makes the simple point that the critical factor is the ratio. Making larger is like making smaller. It's about the signal-to-noise ratio.
Right. That wraps up the information-theoretic limits. We know the absolute best we can hope for. Now, how do we build an algorithm that actually achieves or gets close to these limits, especially without knowing the lines beforehand? That's section 3 algorithms on pages 5 to 7.
The core idea is the geometric hypergraph built using total least squares, TLS. Page 5 gives the definition. For 3 points x1, x2, x3, and R2, SOS-TLS x1, x2, x3 is the minimum sum of squared orthogonal distances from the points to any line L in the plane.
So SOS-TLS min L 1, 3, 2, it finds the line L that best fits the 3 points in terms of minimizing the sum of squared perpendicular distances, and SOS-TLS is that minimum sum. If the points are perfectly collinear, SOS-TLS is 0. If they're close, it's small.
Okay. And the hypergraph H is built using this measure. The vertices are just the data points x1 to xm.
A hyperedge I in JK exists if, and only if, the TLS score for those 3 points is below some threshold. SOT TLS XJ XJ K2, where is a positive threshold parameter we have to choose.
Figure 1 shows a nice illustration. A blue triple has low TLS, below 2, so it forms a hyperedge. A red triple has high TLS, above 2, so it doesn't.
Now, algorithm 1, the spectral method, page 6, uses this hypergraph. It takes the points x and the chosen threshold t as input.
Step 1. Construct the TLS hypergraph H using threshold t. This involves calculating SOT TLS for potentially all n choose 3 triples.
Step 2. Construct a similarity matrix W. This is an NXN matrix where the entry counts how many hyperedges contain both point E and point J. So we J E at J H A.
So if points I and J are part of many almost collinear triples, we shall be large. It captures a kind of pairwise affinity based on shared membership in collinear triples?
Exactly. Step 3. Compute the leading eigenvectors of this similarity matrix W. Specifically, find the eigenvectors v1 and v2 corresponding to the 2 largest eigenvalues, 1 and 2. Stack these into a matrix ULAR and U2.
Why the top 2?
As we'll see when we analyze the expected structure of W, if the data comes from 2 lines, the community structure, which point belongs to which line, is primarily encoded in the subspace spanned by the top 2 eigenvectors.
Okay. Step 4. Assign the final labels I by performing k-means clustering with k2 on the rows of U.
Right. Each point is now represented by its corresponding row in U, which is a 2-dimensional vector, UI1, UI2. K-means will group these 2D points into 2 clusters. Those clusters define the estimated labels MA.
So the pipeline is triples minus TLS hypergraph, similarity matrix W, top 2 eigenvectors, U k-means on rows of U labels.
That's algorithm 1. Now, theorem 2, page 6, gives its performance guarantees, assuming the specific setup of 2 perpendicular equal-length lines intersecting at the midpoint.
Result A. If the noise n and threshold Tn satisfy an error TNA1, then algorithm 1 achieves almost exact recovery.
This is great because it matches the information-theoretic threshold N1 for almost exact recovery. It says if noise is small enough, you can pick a threshold T, also small, but larger than SAW, and the algorithm works.
Result B. If neat log n error in log n, then algorithm 1 achieves exact recovery.
This is also strong. It matches the IT threshold and TNA up to those polylog factors, log n and log n. It says if noise is really small, you pick in this very narrow vanishing range, you get perfect classification.
But the discussion below theorem 2 points out a practical issue.
Yes. The optimal choice of the threshold Tn depends on the noise level sun, which is usually unknown in practice. If you knew, then you could potentially pick Tn to satisfy the exact recovery condition, if sun is small enough. But without knowing sun, how do you choose Tn appropriately?
This motivates algorithm 2, spectral method with threshold selection, page 6. This algorithm tries to find a good threshold directly from the data.
The core idea is clever. If the points come from 2 communities, lines, we expect roughly 14 of all possible triples to be within community, all 3 points from the same line, and 34 to be between community. Within community triples should have much lower TLS scores than between community ones on average.
So maybe we can pick a threshold T such that about 14 of the triples fall below it.
That's exactly the idea. Algorithm 2 takes the points x, a number m for how many triples to sample, and the target fraction, which they set to 14.
Step 1. Sample m triples, 1 to m, uniformly at random, with replacement is fine, from all possible, and choose 3 triples. Let m be the set of nodes involved in these m triples, and mech be the remaining nm nodes.
M should be large enough to get a good estimate, but much smaller than n for efficiency. They suggest 1 mn ma.
Step 2. Compute the TLS score C's TLS for each sample triple. Sort these must scores, S1 and SM.
Step 3. Threshold selection. Set K. Hover E around M4 to the nearest integer. Choose the threshold T as the K smallest score. Teise. This T is essentially the empirical 14 quantile of the TLS scores from the sample.
Step 4. Now, run algorithm 1, but only on the nodes in McKee, the ones not involved in sampling, to avoid potential bias, using this data-driven threshold T. This gives estimated labels IA for I in make.
Step 5. For the nodes I and M, the small set involved in sampling, the paper says assign their labels I uniformly at random, or potentially use another method, but random assignment is simple.
And the guarantee for this data-driven approach, theorem 3 on page 7.
Conditions. Perpendicular equal-length line setup, noise SMA1, sample size M satisfies 1 epi M, slightly tighter than N mentioned earlier, likely for proof reasons. Target fraction tell 14.
Result, algorithm 2 achieves almost exact recovery.
This is a really nice result. It means the algorithm can hit the optimal IT threshold for almost exact recovery
Yeah.
without needing any prior knowledge of SUPs or other model parameters.
just by choosing the threshold based on the 14 quantile of sample TLS scores.
What about the computational complexity? Remark 2 on page 7 breaks it down for algorithm 2.
Threshold selection involves calculating TLS for M triples and sorting OM log M. If M is small relative to N, like MAN-2 as required by Team 3, this part is negligible.
The main work is in algorithm 1 running on the Enio nodes. Step 1, constructing the hypergraph, requires checking sub-TLS for O and triples. Since each TLS calculation for 3 points is constant time, O1, this step is ON.
Step 2, constructing the similarity matrix W. You iterate through the ON hyperedges, and for each edge LJK, you increment WJK. This also takes roughly ONN time.
Step 3, computing the top 2 eigenvectors of the next and matrix W standard algorithms can do this in ON, or potentially faster like ON if using fast matrix multiplication, but ON is a safe bet.
Step 4, K means on endpoints in 2D. Can be done very efficiently, close to ON, using approximation algorithms.
So the overall complexity is dominated by the hypergraph construction and similarity matrix parts, making it ON.
Which is polynomial time. Maybe not super fast for huge N, but definitely feasible and polynomial.
Okay, one last piece before diving into the analysis proofs. What about recovering the lines themselves? Section 8, line recovery, algorithm 3, page 8, and theorem 4, page 8.
Right. Suppose we have run algorithm 1 or 2 and obtained an estimated label vector that achieves almost exact recovery. Now we want to estimate the parameters of L1 and L2.
Algorithm 3 takes the points X and the estimated labels O. For each estimated cluster K, say order 2, let IC be the set of indices.
Step 1. Calculate the sample mean and sample covariance matrix for the points in each cluster, XK. And
these are just the standard empirical mean and covariance for the points assigned to cluster K.
Step 2. Obtain the estimated direction vector VUC for line K by finding the leading eigenvector of the sample covariance matrix UC.
Why the leading eigenvector?
Because for points scattered around a line, the direction of maximum variance will correspond to the direction of the line itself. That direction is captured by the principal eigenvector of the covariance matrix.
Makes sense. And the guarantee. Theorem 4 on page 8.
Conditions. Works for arbitrary line segments L1 and L2, not just the perpendicular equal length setup. Data comes from GLMM L1, L2, the LMM1, the almost exact recovery regime. We assume we have an estimator O that achieves almost exact recovery. Let VK be the true direction vector for line LK, and K be the true mean XZ.
Result. For every AXIO, the probability that the angle between the estimated direction VIC and true direction VIC is small. DSE, the distance between the estimated center XK and true center ONC is small, goes to 1 as NEF.
In short, if you can cluster the points well, almost exact recovery, then the sample mean consistently estimates the true line center, and the principal eigenvector of the sample covariance consistently estimates the true line orientation.
Another strong consistency result. Okay, that covers the algorithms and their claimed performance. Now we need to understand the proofs. We already covered section 4, information-theoretic analysis, when we discussed theorem 1 and lemma 1.
Right, so the next step is section 5, bounds on hyperedge probabilities, pages 12-19. This is crucial because the whole spectral algorithm relies on the hypergraph structure being informative.
They define P and Q back in equation 3 on page 12. Let's revisit those definitions carefully. P is the probability that a randomly chosen triple of points, Misia, xj, forms a hyperedge, i.e. stu-TLS xk, given that all 3 points come from the same underlying line.
So P is the within-community hyperedge probability.
And Q is the probability that a random triple forms a hyperedge, given that they do not all come from the same line, i.e. at least one comes from a different line than the others.
So Q is the between-community hyperedge probability. For the hypergraph method to work, we need P to be substantially larger than Q. We need within-community triples to be much more likely to satisfy the TLS condition than between-community triples.
Exactly. The goal of section 5 is to derive bounds for P and Q, or rather for 1P, the probability A within triple fails the TLS test, and Q, the probability A between triple passes the TLS test, to show that for appropriate choices of T and I, we indeed have P close to 1 and Q close to 0.
Section 5.1, page 12, tackles the within-community probability bounding 1P. Consider a triple ijk where z's chase k1. WLOG, assume L1 is the x-axis, and the points are z's ui0 plus vy1, y2, where ui is uniform in L1 and y are standard normal in R2.
Now, they use the fact that SYLSX is always less than or equal to the sum of squared distances to any single line. Let's choose the true line, L1, the x-axis. The distance dSI-L1 is just the absolute value of the perpendicular component of the noise to y2.
So a useful upper bound is sweaty heel sx ili1 foi I thing down a regular 1-3 co.
Okay, Yakai-2 are independent standard normal variables. The sum of squares of 3 independent standard normals follows what distribution?
A chi-squared distribution with 3 degrees of freedom, often denoted chatho.
Right, so the probability of rejecting a within-community triple is 1p equals sweaty equals O2. This is less than or equal to O2.
Which is p12. This is the probability that a tri-random variable exceeds the value to sa.
Lemma 2 provides a bound for this tail probability using a standard chi-squared tail bound, equation 58 in the appendix. It states that for 3, 1 year is bounded above by an exponential decay term, specifically 1 year log, where ti and all is a constant.
The condition ensures that 1, which is needed for the bound. The key takeaway is that 1p decays exponentially as poilsec gets large. If it's just moderately larger than Oz, we'll be very close to 1.
Okay, so within community triples are very likely to form hyperedges if it's SAW. Now for the harder part. Section 5.2, pages 13 to 19, bounding Q, the between community acceptance probability.
We want to show Q is small. Consider a between community triple. WLOG, let G and XJ come from L1, say the x-axis, and XK come from L2, say the y-axis, assuming the perpendicular case for simplicity here. So EA, EUJ are on the x-axis, UK is on the y-axis.
The condition for this triple I to form a hyperedge is SOT TLS X23. This happens if and only if there exists some line L such that the sum of squared orthogonal distances ft is less than 2c.
A necessary but not sufficient condition for this is that the line L must pass reasonably close to all 3 points. Specifically, if E is Bruth C, it must be that DST for all Ka 1, 2, 3. Geometrically, this means the line L must intersect the open disks centered at each observed point Xi with radius d.
Okay, now they relate this to disks centered at the true points UA. Using the triangle inequality, the distance from the true point UA to the line L, DUAL, is bounded by DIL plus XUI, DIL plus Y.
If L intersects BSIT, meaning DSILT, then DUILT plus Y. Let's define a random radius Ri equals T plus Y. This means the line L must also intersect the enlarged disk BUI-RI centered at the true point UI with the random radius Ri.
So the event T+2 is contained within the event L such that L intersects BU1-R1, BU2-R2, and BU3-R3. This containment gives an upper bound on QQ-EL intersecting BU1-R1, BU2-R2, BU3-R3.
Where the problem becomes geometric. What's the probability that there exists a line intercepting 3 disks, where the disk hunters U1, U2 are random on L1 x-axis, U3 is random on L2 y-axis, and the radii R1, R2, R3 are random variables depending on the noise magnitudes EA?
This looks complicated. They seem to break it down further. Lemma 3, page 13, first looks at the probability that just the 2 disks B1 and B2 from the same line L1 intersect.
Right. Disks BU1-R1 and BU2-R2 intersect if the distance between their centers U1, U2 is less than the sum of their radii R1 plus R2. U1, U2 are uniform on O2, R1, R2 depend on noise. Lemma 3 bounds this probability. PD1 E of 2R is roughly bounded by O2 plus ohm. It's small if T and Rs are small compared to the line length there.
Lemma 4 provides a lower bound on Q, showing it's generally non-zero. They consider the event where X1 and X2 are close and show this implies the TLS might be small. The result is roughly Q or R and XC.
Okay, but the main effort isn't getting an upper bound on Q using that geometric condition about intersecting 3 disks. This happens on pages 15-18, involving properties of common tangents to disjoint circles.
Let's focus on the event E2, where the 2 disks B1 and B2 from L1, the x-axis, are disjoint. We know PECR PB1 E2 P2 is small by lemma 3, so we mainly need to bound PL intersecting B1, B2, B3, E2.
Now, lemma 5, pages 15-16, is a purely geometric result. If you have 2 disjoint circles A and B centered on the x-axis, Any line that intersects both of them must have a y-intercept less than or equal to the y-intercept of one of their common tangents.
That makes intuitive sense. The common tangents are the outermost lines that can touch both circles.
Corollary 1, page 16, generalizes this. For any line gx that intersects both disjoint circles A and B on the x-axis, the line must lie entirely below the upper envelope formed by their four common tangents. Let T max x be the pointwise maximum of these four tangent lines. Then gxa T max x for all x.
Okay, how does this help bound Q? Remember, QA at AO intersecting B1, B2, B3, condition on B1, B2 being disjoint, event E2. Any such line L must satisfy LX, where Tmax is the upper envelope of tangents to B1, B2. For L to also intersect B3, centered at U3 on the y-axis with radius R3, the disk B3 must overlap with the region XY, YA, Tmax.
This geometric condition puts a constraint on the position of U3, which is on the y-axis, and the radius R3. Specifically, it implies that U3, the y-coordinate of the center, must be less than some value B plus R3, which depends on the radii R1, R2, R3, and the distance U1, U2 via the geometry of the tangents. Equations 10, 11. See figure 4.
So the probability PE1, E2 equals is intersecting B1, B2, B3, and B1 your B2 is bounded by PE3 IB plus E2. Since U3 is uniform on R2T, this probability is related to EB plus E2.
Now comes the really technical part. Bounding EB plus E2. B plus depends on R1, R2, R3 noise, and U1, U2, line sampling. They have to integrate over all these random variables using the properties of the tangent slopes related to K in the proof, and radii conditioning on E2. It involves integrals of ratios involving square roots, expectations of logs, Jensen's inequality. It's quite involved.
Let's skip the goriest details of that integration, but what's the final result? Lemma 6.
Lemma 6 provides the upper bound for Q under the assumption that has are both much less than 1. The result is QA4 plus O1.
Okay, so Q is small if T and sut small. It vanishes roughly like T plus times a logarithmic factor. Importantly, it depends on the sum T plus.
Comparing this to the bound on 1p from lemma 2, which decays exponentially in tals, we see a separation. If we choose up appropriately relative to sig, p slightly larger than sub but both small, we can make 1p extremely small while q is also small, potentially vanishing slower than 1p but still small. This PQ separation is what the algorithm needs.
Great. So Section 5 establishes that the hypergraph does contain structural information distinguishing within and between community triples, provided 2 and SU are in the right regime. Now, Section 6, analysis of the spectral algorithm, pages 20-26. How do they prove algorithm 1 works? Theorem 2.
The overall strategy is standard in spectral clustering analysis, adapted for this hypergraph setting. First, show the observed similarity matrix W is close to its expected value, EW, concentration. Second, use matrix perturbation theory, specifically the Davis-Conlon theorem, to show that the eigenvectors of W are close to the eigenvectors of EW. Third, show that the eigenvectors of EW reveal the community structure. Fourth, use a k-means clustering guarantee to show that clustering the perturbed eigenvectors from W still recovers the communities accurately.
Okay, step 1, concentration of W, section 6.1, pages 20-23.
They start with some basic concentration results. Lemma 7, page 20, uses Chernoff bounds to show that the number of points in each true community, N1, N2, is very likely close to N2, assuming the balanced case, Z-Bernoulli 12.
Lemma 8, pages 20-21, shows that the number of within-community pairs and the number of triples of different types involving a given pair are also concentrated around their expected values, WHP, using Chernoff and union bounds.
Now, the main results are Lemma 9 and Lemma 10, bounding the difference WEW in Frobenius norm. The Frobenius norm AF is the square root of the sum of squares of all entries.
Lemma 9, pages 21-23, handles the exact recovery case. Slugs in A. NA. Under these conditions, they use the bounds from section 5, lemmas 2 and 6, to show that Q and 1P are very small, specifically Q, 1PA, AA.
The proof then bounds EW, EWFTA, AA. They decompose the variance varwi based on whether I are in the same community or not, and further decompose it based on variances and covariances of the indicator variables. A8, A0, and IJA is a hyperedge. These variance sescovariances, Vin, Vout, Sin, Kaut, C-Cross, and EQ1718, are shown to be very small, like O and OS, using the tiny q and 1p values. Combining with the concentrated counts from lemma 8, they show EW, EWFT, OC's ON. Markov's inequality then gives PW, EWF, ONNAA.
So W is close to EW with the squared error scaling like ONA.
Lemma 10, page 23, does the same for the almost exact recovery case, AT1. Here, Q and 1p are just O1, not necessarily vanishing faster. Following similar steps, the variance Kazuko variances are O1, leading to EW-EWF instead of ON. Markov then gives PW-EWF O1.
A weaker concentration bound error scales like O instead of ON,
Right.
reflecting the weaker conditions. Okay, so W is close to EW, step 2, perturbation theory, section 6.2, pages 23, 24.
First, they analyze the expected matrix, WEW. They show it has a specific block structure based on the true community Z, WEDE plus WOUT, 211 plus win out do a win on I equation 21. Here, 1 is the all ones vector, C is the vector of true labels, plus 1-to-1 form, and WINI Z, WINI, NI, GA.
What are win and no? Equation 22 gives them in terms of P and Q, win, N2P, WET, N2Q. It's the expected number of common neighbors K for a pair IJ, given their community relationship.
Now, this block structure means the eigenvectors of W are known. The leading eigenvector is the all ones vector 1, with eigenvalue AT on N2 win plus WOUT. The second eigenvector is the true community vector Z, with eigenvalue AN2. The remaining N2 eigenvectors have eigenvalue E3 F equals E and equals N equals win, equals 23, 24.
So the community information is perfectly encoded in the second eigenvector of the expected matrix.
Exactly. Let U be the n by 2 matrix whose columns are the normalized versions of 1 on Z. This U spans the true top 2 eigenspace. Let U be the n by 2 matrix of top 2 eigenvectors computed from the actual W from algorithm 1. We want to show U is close to U.
How do they measure closeness of subspaces?
Using the sign of the principal angles between them, specifically RG8 UAOF. The Davis-Kahan theorem provides a bound on this distance, it says, roughly. UAF ECWWA, where WW is the perturbation norm. We use Frobenius norm here. And UAE is the spectral gap between the eigenvalues we care about and the ones we don't.
Which gap is relevant here?
The gap between the second eigenvalue 2, associated with the community vector Z, and the third eigenvalue 3, URE2 EPT3, EQ26. Using the formulas N2, WIN-WOUT, and N24, PQ, this gap is large if P is significantly larger than Q, which we established in section 5.
Okay, so Davis-Kahan bounds the subspace distance using the spectral gap and the matrix concentration bound EF, EWWF. They then relate the subspace distance to the Frobenius norm distance between the matrices U and U up to an optimal rotation O. UUF to EOF combining gives you UOF to UF, EOEF, equation 28.
This is the key perturbation result. It shows the computed eigenvectors U are close to the true eigenvectors U times the rotation, with the error controlled by the ratio of the matrix perturbation EF to the spectral gap done.
Step 3 was understanding EW eigenvectors. Done. Step 4, K-means clustering guarantee, section 6.3, page 25.
We run K-means on the rows of the computed eigenvector matrix U to get the labels all. How well does this work? They use Lemma 11, page 25, which is a result adapted from prior work on K-means performance after spectral clustering.
What does Lemma 11 say?
It provides a bound on the number of misclassifications, ham, Z, based on how close the input matrix U is to the ideal matrix V, UO. The bound depends on UVFA, the minimum true cluster size N-min, and DOR, the square distance between the true cluster centers in the ideal V space.
Specifically, if a condition EQ29 holds 42 plus E via N-min, then the number of errors is bounded. Ham via UF, EQ40, EQ30.
The intuition is, if the computed eigenvectors U are sufficiently close to the ideal ones V, relative to how well separated the cluster centers are in V space and the minimum cluster size, then K-means on U will give a result close to the true cluster in Z's.
Okay, now we just need to plug everything into Lemma 11, section 6.4, pages 25, 26. Proof of theorem 2.
Said K2, the ideal matrix is VUO, where U's columns are proportional to 1 and Z. The true cluster centers in V space are the rows of X, 1, 1, and 1, 1. 1, that 1, O, the square distance between these centers is DEQ4N, EQ32. The minimum cluster size N-min is EQ32. The minimum cluster size N-min is AN2 by Lemma 7, EQ33.
The squared distance between computed and ideal eigenvectors is UVF 8 EDIF FF from EQ28. This is EQ31. The spectral gap squared ADISKISWI.
Plugging these into the key-means condition, EQ29, gives a condition on the perturbation norm squared. EF must be less than roughly NPQ, derived from EQ34.
And plugging into the error bound, EQ30 gives ham constant and EDFSK. Substituting AF gives ham N PQ3495. Since PQ1 in the regimes of interest, ham E is Shep.
Now we just need to use the concentration bounds for EF from Lemmas 9 and 10.
Section 6.4.1, proof of theorem 2F, almost exact recovery. Conditions. Lemma 10 gives Ia NWA substituted to ham. Ham is as 1 and N.
So the number of errors is bounded by NQ STSPOP. The fraction of errors ham is bounded by Ia. Since we can make I arbitrarily small, the fraction goes to 0 in probability. Almost exact recovery proved.
Section 6.4.2. Proof of theorem 2b, exact recovery. Conditions. Lemma 9 gives U of NOWH substitute into hammes no. Hamma no.
Wait, the number of errors is bounded by a. That's a constant. How does that imply exact recovery? 0 errors.
Ham test must be an integer. The result says that for any a of 0, the event a of he happens with probability 101. On this event, hem no. We can choose small enough so that cam more.
So with high probability, the number of misclassifications is less than 1. Since it must be an integer, it must be 0.
Exactly. PM no 1, PM on e plus PFE. If cam 1, the first term is 0. The second term PFA is O1. So PMO1, which means PMA1. Exact recovery proved.
Clever argument. That wraps up the analysis of algorithm 1 and proves theorem 2.
Now for section 7, data-driven threshold selection, pages 27-33. This proves theorem 3 for algorithm 2, the one that picks TO based on the sample quantile.
Recap. Algorithm 2 samples M triples to 1, computes TLS scores, C sorts them S1, SM selects TIA as area M4, runs algorithm 1 on the remaining nodes, mix each using TIA.
The core idea is that T should be such that FMT area F14, where FMT1M1C is the empirical CDF of the sample TLS scores, and 14 is the expected fraction of within-community triples.
Page 27-28 argues TLS scores are almost surely distinct, making the quantile well-defined. Lemma 12, page 28, shows the M-sample triples are likely disjoint if M, N, N, ensuring some independence for concentration bounds.
Section 7.1 provides the key concentration inequalities. Lemma 13, pages 28-29, uses Chernoff bounds to show that the empirical CDF FMT is close to its expectation EFMT W jot H pass, provided M is large enough but still small. And what is EFMT? It's the probability that a randomly chosen triple has CENTLS ed. Since P is within 14 and P is between 34, we have EFMT plus 34 QT.
Okay, so FMT concentrates around 14 PT plus 34 QT. Now, lemma 14 analyzes the behavior of this function. It has two parts.
Part 1. If SENU1 but Tn is bounded away from 0, say Tn or Tmin 0, then FMTN will be bounded away from 14 WHP. Why? Because if it's constant, Qt will be bounded below by some constant lemma 4, while 1 PT will be tiny, lemma 2, so EFMT1 plus 34 Qt will be significantly larger than 14.
Part 2, however, there does exist a vanishing threshold SNU1, specifically SNUR1, such that FMSN is close to 14 WHPY. Because if SN is small but still larger than SEN, both 1PSN and QN will be very small, lemmas 2 and 6. So EFMSN 1P plus 34 Q-F15.
So lemma 14 tells us that the threshold T chosen by algorithm 2, where FMTHE4 must be a vanishing threshold. If SENU, it can't be a constant.
Now, lemma 15 connects this back to the properties needed for algorithm 1 to work. It says, if Tn is chosen such that FMTN is close to 14 and also close to its expectation EFMTN, within some small error n at 1, and if the noise sun is small enough relative to this error, then the resulting hyperedge probabilities must be good. QCTN and 1PTN and 1PTN.
The proof is a bit intricate, using the condition EFMTN, 14 year n, which means negative 14 1p plus 34 key or n. They argue by contradiction, using the bounds from lemmas 2 and 6. If either 1p or q were significantly larger than n, it would force a relationship between t and sa that contradicts the assumption n log near n.
So if the algorithm finds a t where FMT or n14 and it's small enough, then that t must yield small q and small 1p.
Now, the proof of theorem 3, pages 33-34. We need to show algorithm 2 achieves almost exact recovery if saying area M1, n there.
Algorithm 2 selects t. By lemma 14, tell n, and FMT14 is small. By lemma 13, FMT is small. N tell n.
So FMT14 plus FMTM plus NTR, let n equals EM plus which is error.
Now we need to satisfy the conditions n log or n from lemma 15. The proof argues that if SENR1, we can always find such an n, which depends on m and n via n, that also satisfies this condition. For example, choosing m appropriately.
Okay, assuming that holds, lemma 15 tells us that the chosen 10 yields cotain and 1 PT, so Qt 1 and 1 PTA. Now, algorithm 2 runs algorithm 1 on the set mix S size n, using this threshold T. We need to check if the conditions for theorem 2a, almost exact recovery for alg1, are met for this run.
The conditions were SENA, Te1. We know 10a, 1 WHP by lemma 14 part 2. Do we know SENA Te? Lemma 14 part 1 implies Ti cannot be too small if sen is fixed, suggesting it stays larger than 10. Let's assume sen A T holds W at AP, and we just showed Q array 1 and 1 PP at 1 WHP.
So the conditions for theorem 2a are met for the run of algorithm 1 on MICLE WHAP. Therefore, algorithm 1 correctly classifies almost all nodes in MICLE.
Since MCAT contains almost all the nodes, Mn NG0 is MAN for iter, achieving almost exact recovery on McTay implies almost exact recovery overall. Theorem 3 holds.
Excellent. The data-driven threshold selection works. Finally, section 8, line recovery, pages 34-37, proving theorem 4 for algorithm 3. This assumes we already have labels that achieving almost exact recovery. Recall algorithm 3. Estimate center xk using sample mean of cluster hic. Estimate direction VOC using leading eigenvector of sample covariance EK of cluster hic. Theorem 4 claims consistency. Ekte euro dfk and virk improbability.
First, the sample mean, lemma 16, pages 34-36, proves xk in 0 improbability.
The proof idea is neat. Split the estimated cluster into the set A of correctly labeled points and the set B of incorrectly labeled points. The sample mean xk is a weighted average of the mean of A and the mean of B, xkn, xa plus, nbn, xb, where enc, naa, and bb.
By almost exact recovery, the fraction of incorrect points, nbn, xk, must go to 0 improbability since b ham, which is on, and n2.
The mean of the correctly labeled points xa converges to the true mean oi by the law of large numbers, since na, n2. The mean of the incorrect points xb is stochastically bounded. It's an average of points from the other line's distribution.
So xk 1k plus small bounded or near probability. Consistency of the sample mean holds.
Now for the direction BOOK from the sample covariance UK. Let DIC be the true covariance matrix for points from line k. For points on a line with variance store along the line and 6-star perpendicular, looks like mono vk plus anselp2. Its leading eigenvector is vk with eigenvalue tet plus tech. The other eigenvalue is tech.
We compute UK using the estimated cluster IC. Let sklink be the sample covariance computed using only the correctly labeled points A at Q5. Standard results say that sample covariance converges to true covariance. Sklink, DEEK, in probability, EQ50.
The key is to show that the difference introduced by the misclassified points B is negligible. Lemma 17 shows that A keys UK sklink atirvi in Frobenius norm W.HP.
The proof again decomposes UK based on points in A and B. A involves terms related to the covariance of B, SB, and cross terms involving the mean difference. Since the fraction NBN ORC, all these extra terms vanish in probability.
So, ik sklinkef plus sklinkiktef, both terms go to 0 in probability. Therefore, UK converges to crack in probability. Key 51.
Now we use Davis-Kahan again, but for the sample covariance matrix UK and the true covariance UK. The angle between the estimated leading eigenvector VOC from IK and the true leading eigenvector VIG from UK is bounded.
The spectral gap 1 note 2 plus ck sat, which is a positive constant, assuming the line has non-zero length variance. Since UK ck 0 in probability, the sign of the angle also goes to 0 in probability.
This means the angle itself goes to 0. The estimated direction VIC converges to the true direction VK. Theorem 4 is proved.
It relies heavily on the initial assumption of almost exact recovery for the labels all. But given that, the standard estimators work as expected.
And the appendix just lists the standard concentration inequalities used. Rayleigh CDF for noise magnitude, lemma 4, chi-squared tail bound, lemma 2, 3, and Chernoff bounds for binomial Bernoulli sums, lemma 7, 8, 13.
Plus a long list of references, showing this builds on substantial prior work.
Okay, let's try to summarize the whole journey. We started with this fundamental problem of line clustering, where traditional graph methods looking at pairs of points just don't work well because any 2 points define a line.
The key idea presented in this paper was to move to higher-order interactions, specifically looking at triples of points and checking if they are approximately collinear using the total least squares TLS measure.
This geometric information was encoded into a 3-uniform hypergraph, where hyperedges connect triples with low TLS scores. The challenge then became analyzing this hypergraph, particularly because the geometric nature introduces dependencies between hyperedges, unlike standard block models.
We then explored the fundamental information-theoretic limits for recovering the true line memberships in the presence of Gaussian noise. We found hard thresholds. Noise must vanish faster than 1n for exact recovery, and just vanish for almost exact recovery.
Next, we dissected the polynomial-time spectral algorithm proposed. It constructs the hypergraph, builds a similarity matrix W based on shared hyperedges, finds the top two eigenvectors U of W, and uses k-means on the rows of U to get the clusters.
In the theoretical analysis, using matrix concentration, Davis-Kahan perturbation theory, and k-means bounds showed this algorithm achieves performance remarkably close to the information-theoretic limits, matching them up to polylog factors for exact recovery and matching the almost exact recovery threshold.
A crucial practical aspect was algorithm 2, which selects the critical TLS threshold T in a data-driven way by looking at the 14 quantile of sampled TLS scores. This allows the algorithm to achieve the optimal, almost exact recovery guarantee without needing prior knowledge of the noise level.
Finally, we saw that if almost exact recovery of the point labels is achieved, then simple post-processing using the sample mean and sample covariance principal eigenvector allows for consistent estimation of the true line centers and orientations.
We really went through the details, the MLE analysis for the IT bounds, the geometric arguments and probability bounds for hyperedge formation, the step-by-step logic of the spectral algorithm analysis, the data-driven threshold justification, and the line parameter estimation proof.
So, for you, the listener, having gone through this deep dive, you've seen the rigorous foundation for tackling line clustering. You understand not just an algorithm, but the fundamental limits of the problem and why this hypergraph-based spectral approach, carefully analyzed, can work effectively even with the complex dependencies inherent in geometric data.
It provides a solid basis for evaluating similar methods, or maybe even thinking about adapting these ideas to related problems you might encounter.
And it really highlights how explicitly modeling the geometry, even if it complicates the theory, can lead to powerful results by capturing the true underlying structure better than simpler pairwise models.
Which brings us to a final thought to leave you with. This paper focused on lines in 2D. But geometric structures, of course, exist in higher dimensions. Think planes or general subspaces in 3D or more, and they come in other forms too, like circles, curves, surfaces.
So how could this general approach, using hypergraphs to model higher-order geometric consistency, maybe quadruples for planes, etc., and developing analysis tools that handle the resulting dependencies, be extended? Could this framework offer new ways to find and cluster more complex, latent geometric objects hidden within noisy, high-dimensional data?
Something to think about. Thanks for joining us for this deep dive.